Okay, let's unpack this. You know that feeling, that profound sense of bewilderment when a major economic prediction just completely misses the mark?
Not just by a little, but consistently.
Exactly. A growth forecast, an inflation projection, a policy analysis, and it's just systematically wrong. We often chalk it up to, modeling complexity or some unforeseen shock.
But for people whose job it is to make these calls, the real fear is something else. It's a hidden structural flaw that's undermining the very foundation of their work.
And that flaw, it's not just some random statistical anomaly, is it?
No, not at all. It's a fundamental mechanical failure. It has a name: omitted variables bias, or OVB.
OVB.
Today, we're doing a really critical deep dive into OVB. Our sources describe it, and I think this is a great phrase, as the silent saboteur of reliable modeling.
A silent saboteur, I like that.
We're going to expose not just what it is, but how its mechanics can corrupt every single number you rely on for future planning.
So our mission today is to move past that simple definition. We want to really grasp the complex mathematical conditions that create OVB, understand exactly how it contaminates results, and I think this is the most important part, explain why its presence fundamentally undermines the credibility of economic forecasting.
And, by extension, high-stakes policy analysis.
Absolutely. You shared sources that lay out the mechanics with really crystalline clarity, and we're going to dive straight into the engine room.
Precisely. To start, omitted variables bias happens when we're trying to estimate a relationship in the world, but we fail to account for a critical influence.
Okay.
And for OVB to actually exist and pollute your results, two very distinct conditions have to be met at the same time within your regression model.
Condition one is, I think, the intuitive one. Something important is missing.
That's right. The first condition is very straightforward. A relevant explanatory variable has to be excluded from the model.
So it has to be something that actually matters.
It has to matter. The missing factor has to have a real effect on the outcome you're trying to predict. If you're predicting wages and you leave out, say, years of education, that clearly matters.
That makes perfect sense.
Yeah.
If I forget a major driving force, my estimate is just incomplete. But as we were discussing, if the missing factor is totally irrelevant, then we're safe.
Right.
It only becomes a bias problem when that second condition kicks in, which to me feels like the truly insidious part.
Absolutely. The second condition is the mechanical trigger for the bias. The omitted variable must be correlated with one or more of the variables you did include in your model.
Okay.
So if you miss a piece of the puzzle and that missing piece is linked statistically, economically to the pieces you do have, your estimation is automatically flawed.
Why automatically?
Because the variable you kept is forced to take on the influence of the one you left out.
Okay, so let me try an example. If I'm trying to explain a change in GDP, let's call that Y, and I omit something like institutional quality, Z, that's condition one because we know institutional quality definitely affects GDP.
Right, it's relevant.
But then if I include interest rates, X, and it turns out institutional quality Z is correlated with interest rates, then my interest rate variable suddenly becomes a proxy for two things. It's representing its own actual effect and the missing effect of institutional quality.
That is the perfect conceptual synthesis. The sources are so clear on this. Only when both conditions are met, relevance and correlation, do you get this systematic distortion we call omitted variables bias.
And the key word there is systematic.
It is. The resulting estimates aren't just inaccurate in a random way. They are systematically skewed. They just do not reflect the true economic relationships.
That brings us right to the mechanism. We have to go from the definition to the complex math. How does omitting a correlated variable physically corrupt the numbers? Here's where it gets really interesting. How does that absorption actually happen?
To really see the corruption, we have to start with the difference between the hypothetical true relationship in the world and the one we actually estimate.
The one we can build with our limited data.
Exactly. So let's imagine a true data generating process. Let's say y equals beta naught plus beta 1x plus beta 2z plus u.
Okay, let's break that down. Y is our outcome, say, GDP growth.
Correct. X is the primary variable we're interested in, like our interest rates. Z is the relevant, powerful variable that we omit, our institutional quality.
And U.
U is the ideal, purely random error term, the stuff we can never know. In this true model, beta 1 is the genuine ceteris paribus effect of X on Y.
The true effect of interest rates, all else being equal.
Yeah.
Beta 2 is the separate true effect of our omitted Z. This is the ideal world.
This is the ideal. But now we estimate a simpler model where Z is missing. Maybe it's impossible to measure, or maybe we just didn't think of it. We just run a regression of y on x.
And that's where the problem starts.
It's where it all goes wrong. Because z is correlated with x, that's our second critical condition, the model we end up estimating, let's call it y hat, equals beta naught hat plus beta 1 hat x is fundamentally misspecified.
What happens to the effect of z? Where does it go?
It gets pushed into the error term, but crucially, the sources show the real problem is that because x and z are correlated, the variable x can't change without also capturing some of the systematic movement of z.
So mathematically, why does that lead to a biased estimate for beta 1 hat? Let's go beyond the analogy of x wearing z's coat. How do we prove that the expected value of our estimated coefficient is not equal to the true coefficient?
This is the core econometric mechanism, OLS, that's ordinary least squares estimation. It works best when a key assumption holds. It's called the zero conditional mean, or ZCM assumption. It basically requires that the error term, u, has to be entirely independent of your explanatory variables. In other words, the expected value of u given x has to be 0.
So the error has to be purely random noise with no relationship to the things you're measuring.
Exactly. In our true model, with z included, the true error u meets that condition. It's clean.
But when we omit z, the z term along with its own coefficient beta 2, it gets absorbed into the new error term of the model we actually run.
Precisely. So think of the true model as y equals beta naught plus beta 1x plus this whole other term in parentheses, beta 2z plus u.
Okay, I'm with you.
When we run the simple regression of y on x, our new estimated error term, let's call it e, is now equal to beta 2z plus u.
Ah, so it's not just random noise u anymore, it's got z baked into it.
And since we already established that x and z are correlated, we now have an error term e that is systematically related to our included variable x. The zero conditional mean assumption is violated.
And that violation is the mathematical source of the bias.
That is the source. Once that assumption is broken, the formula that OLS uses to calculate beta 1 hat, which relies on the covariance between x and y, produces a result that is just no longer centered on the true value, beta 1.
So can we formalize that? What does the expected value of our estimated coefficient actually look like now?
We can. This is the key piece of insight for a deep dive. We can formally derive what our estimated coefficient is actually measuring. And the derivation shows that the coefficient used to estimate is made of two parts, the true coefficient plus a whole bias term.
Okay, let's break down that bias term using the structure from our sources. How is the relationship between x and z formalized in this context?
We use something called an auxiliary regression. It's a hypothetical regression that just models the relationship between the omitted variable z and the included variable x.
So it's a model within a model designed just to quantify their correlation.
Exactly. Let's call the coefficient from that auxiliary regression delta zx. So delta z quantifies how much z changes, on average, when x changes by 1 unit.
So delta zx is basically the mathematical measure of how much x is carrying the weight of z.
Precisely. Now, if we substitute the true model into the OLS estimation formula and calculate the expected value, the result reveals the precise OVB formula.
This is it, the core of the mechanism.
The expected value of beta 1 hat is equal to the true beta 1 plus beta 2 times delta zx.
Okay, that is the core insight. The expected value of our estimated coefficient, what we get from our regression, is equal to the true coefficient we want, plus that entire bias term, which is beta 2 multiplied by delta zx.
And this mathematical relationship confirms it. The estimated coefficient is polluted. The bias is the product of two elements. First, beta 2, the true impact of the omitted variable on the outcome.
How much z actually matters for y.
And second, delta zx, the relationship between the omitted variable and the included variable.
A correlation between z and x.
And if either of those terms is 0, if beta 2 is 0, meaning z is irrelevant, or if delta zx is 0, meaning z is uncorrelated with x, the whole bias term vanishes.
The product becomes 0, and the expected value of beta 1 hat just equals the true beta 1.
And you get an unbiased estimate.
I see. That's the formal proof of the two conditions we started with. For the bias to exist, both factors in that product have to be non-zero. It really moves OVB from just a concept to a derived statistical proof.
It also does something else that's crucial for forecasting. It allows us to understand the direction of the bias.
Whether we're overestimating or underestimating the effect.
Exactly. The direction of the bias, positive or negative, is determined by the combined signs of those two factors in the bias term.
So we have two signs multiplying together. We need the sign of beta 2, which tells us if the omitted variable z positively or negatively affects our outcome y.
Mm-hmm.
And we need the sign of delta z's, which tells us if z is positively or negatively correlated with our included variable x.
That's it. If the signs of beta 2 and delta z are the same, both positive or both negative, the bias term is positive.
Which means our estimated coefficient beta 1 hat will be systematically larger than the true effect beta 1. We overstate the impact of x.
We overstate it.
Okay, let's use the classic example from the literature. Wages, y, education, x, and something like innate ability.
Yeah.
Ability is really hard to measure, so we often omit z.
Right.
Beta 2, the effect of ability on wages is clearly positive.
More ability, more wages.
Correct. And delta zx, the correlation between ability and education. Well, that's almost certainly positive too. More able people tend to get more education.
So in that scenario, the bias is positive times positive, which is positive.
Meaning our estimated coefficient for education will be higher than the true effect of education alone.
Because it's secretly capturing the positive effect of ability. We're falsely crediting education for benefits that actually stem from innate talent.
But what if the two signs are opposite? Say beta 2 is positive, but delta zx is negative.
Then the bias term is negative. Your estimated coefficient beta 1 hat will be systematically smaller than the true effect, beta 1. You understate the impact of x.
This dual dependency makes interpreting coefficients completely unreliable, doesn't it?
Utterly unreliable. Imagine a policymaker sees a positive estimated coefficient for some policy variable x. They have no way of knowing if that's the true positive effect, or maybe a huge true positive effect that's been dampened by a negative bias, or, and this is the scary one, a true negative effect that's been completely overwhelmed and flipped positive by a massive positive bias.
That structural ambiguity is genuinely crippling for any kind of evidence-based prediction. If the model is built on coefficients that are just structurally wrong, any forecast that projects the future behavior of x is fundamentally unreliable.
Right.
The model is essentially useless for anything beyond the specific data set it was trained on.
It becomes a descriptive tool that has lost all its prescriptive power. It can describe the correlation you saw in the past, but it cannot tell you the true causal relationship or predict what happens if you intervene and change x. The structural integrity is just compromised at the most basic mathematical level.
This moves us right into the real-world impact. We get the mechanism that bias formula, beta 2 times delta x, is poisoning our estimates. So if the coefficients are wrong, the forecasts are systematically wrong. Why is this so critical in economic prediction, where we're often dealing with these high-stakes, long-term trend projections?
Well, economic forecasting really relies on the assumption that the relationships we estimate today, the coefficients, reflect some kind of stable underlying structure. OVB just shatters that assumption.
So if our estimated coefficient beta 1 hat is biased,
Any prediction you make based on future values of x will carry that systematic bias forward with it. It just leads to these systemic misses over and over again.
and the key here is that these errors are systematic. This isn't just random noise that might balance out over time.
Precisely. Because the error is based on this persistent mathematical bias built into the coefficient, the prediction errors are not random. They follow a predictable pattern that's derived from that bias term. And this leads directly to a problem we call poor out-of-sample performance.
The moment we step outside the specific time period or the specific region used to train the model, the forecast starts to just systematically deviate from reality.
Yes.
But why? Why does that systematic nature mean the bias persists outside the training data?
Think back to the formula. Our coefficient beta 1 hat is biased because it's carrying the weight of the omitted variable z. So when you use that biased coefficient to project a trend, say, predicting next year's inflation based on interest rates, you are, in effect, projecting next year's inflation based on interest rates plus the assumed effect of the missing variable z.
Ah, I see. Since the bias is inherent in the number itself, the incorrect trend projection just keeps propagating that error forward.
So yes, the model's projection curve is fundamentally angled incorrectly from the start.
Let's apply this to the big structural economic trends mentioned in the sources, like technological change, institutional quality, demographics. These are often the hardest to measure, and so they're frequently omitted. What's the impact when these immense, slow-moving forces are missing from a model?
This is where OVB moves from being, an academic concern to a potential policy catastrophe.
Okay.
Structural factors like shifts in the global distribution of capital or changes in the labor force because of an aging population or exponential advances in AI, These things influence almost all the cyclical indicators we watch.
Right.
If we omit them, the model has no choice but to try and explain those massive long-term changes using the variables we do include. And those are typically shorter-term things like fiscal spending or consumer debt.
This sounds a lot like the debate around the Great Moderation. That period of low macroeconomic volatility in many developed countries that started around the mid-1980s. Was that because of clever monetary policy, RX, or was it driven by these deep structural factors like globalization and financial innovation, RDs, that were just really hard to model?
That is an excellent real-world illustration of potential OVB. Many of the early models focused heavily on the role of central bank policy, better interest rate setting, as the main explanation for that newfound stability.
They took the credit, essentially.
They did. But if the real driver was the omission of, say, a global savings glut, or a series of benign technology shocks, those being our Z's variables, then the policy coefficient for X was biased upward. It appeared that monetary policy was far more effective than it truly was.
Because it was secretly carrying the hidden weight of those global structural changes.
Exactly.
And the consequence is that policymakers then overstate the effect of their own tools. They think they have this incredibly powerful lever, but that lever only looks powerful because it was correlated with an underlying invisible structural tailwind.
And when that tailwind reverses or just disappears,
The policy fails spectacularly.
they systematically overstate the cyclical effects and they misinterpret long-run trends. If demographics are slowly driving down the natural rate of interest, but we omit demographics from our model, then the coefficient on short-term fiscal stimulus might look incredibly powerful.
Right.
But when the demographic trend stabilizes or shifts, that same fiscal stimulus relying on the same old estimated coefficient suddenly underperforms. The hidden support is gone.
This brings us back to what I think is a critical distinction. OVB is a bias problem, not just a statistical precision issue, like having high variance or large standard errors. This point needs to be absolutely clear.
It absolutely must be. When we have large standard errors, that's a variance issue. Our estimates are noisy, they're imprecise, but they are still, on average, correct. They're centered around the true value.
And the solution there is usually simple.
Usually, yes. You collect more data, increase the sample size, the standard errors shrink, and your precision improves.
Okay, but I want to challenge you on that based on our reading. If OVB is systemic, why doesn't gathering, say, 100 years of economic data, a massive sample size, eventually help average out the bias? It seems like it should.
And this is the most dangerous misunderstanding of the problem. The source material is explicit in its warning here. Increasing the sample size does not eliminate omitted variables bias.
It does not.
The bias is structural, it's systematic. The problem isn't random measurement error or noise. The problem is that you are using the wrong mathematical formula to describe reality in the first place.
So if I'm using a formula where that bias term, beta, 2 times delta zx, should be 0, but it's not, feeding it a billion data points, it just tightens my confidence interval around the wrong number.
That's it exactly. You achieve greater and greater precision in your estimate of the biased coefficient.
So you might produce a forecast that looks incredibly precise, with tiny little standard errors, lending it this immense false credibility.
But that forecast is systematically and structurally wrong. You're just becoming more and more certain about the wrong answer. This is why OVB is so much more dangerous than simple estimation error.
Let's move this to the final, critical implications for policy. We're talking about central banks, governments, all relying on these forecasts. How does this kind of structural error lead to tangible, real-world policy mistakes?
Policy analysis, at its core, has to rely on credible, unbiased coefficients to establish the expected impact of an intervention.
Right, the what happens if we do X question.
Exactly. If the coefficient linking your intervention X, say a carbon tax, to an outcome Y, say a reduction in emissions, is contaminated by an omitted factor Z, like a pre-existing shift in consumer tastes towards sustainability, then the entire policy evaluation will fail.
Okay, let's run through 2 scenarios based on the direction of the bias. What happens with positive bias?
Scenario 1, positive bias. Let's say the government implements a fiscal stimulus, or X. If the true impact is actually quite modest, but the estimated coefficient, beta hat X, is positively biased,
Because it's carrying the weight of a missing positive structural tailwind, RZ.
then the policy appears immensely successful. So the next time a crisis hits, policymakers, confident in their big coefficient, implement a smaller stimulus package, thinking they'll get the same big result.
But they don't. The true small effect kicks in, and the economy fails to recover properly.
And that's a misallocation of resources due to under-intervention, all based on a biased estimate.
Okay, scenario 2, negative bias.
Yeah.
The opposite happens. The true impact of a policy X is actually very strong, but the coefficient beta at X is negatively biased.
Maybe because it's correlated with some omitted factor Z that is simultaneously depressing the economy, so the policy appears weak, or maybe even completely ineffective.
And what's the outcome there?
Policymakers dismiss the policy X as useless, when in reality it was hugely powerful. They might shift to more expensive, more complex, or completely different interventions.
So you get an abandonment of effective tools, a massive misallocation of political and economic capital.
Yes. It just demonstrates how policy decisions based on biased forecasts inevitably lead to unintended outcomes and resource misallocation, simply because the policymakers don't know the true elasticity of their own tools.
The lesson here seems crystal clear. Recognizing and addressing OVB isn't just an option, it's a fundamental prerequisite for credible policy analysis. We're not just debating statistics, we're debating the efficacy of governance itself.
It's that serious.
Okay, we've spent a lot of time diagnosing the severity and the structural nature of OVB. And since we've established the problem doesn't just go away with more data, we need to turn to the conceptual approaches for correction. How do researchers actively try to restore unbiased estimation when they know they're facing this kind of contamination?
The primary conceptual goal of any remedy is always to zero out that bias term, the beta 2 times delta's x.
To get rid of the pollution.
To get rid of the pollution. And since the problem is omission and correlation, the solution has to involve either, well, including the omitted variable, or somehow statistically neutralizing the effect of its correlation with the variables you kept.
All right, so let's start with what is arguably the most powerful conceptual remedy in modern applied econometrics, especially for these complex data sets that track units over time: fixed effects regression.
Fixed effects, or FE, is absolutely essential when you're dealing with panel data. That's just observations collected over time for multiple distinct entities, countries, companies, people, whatever.
Right.
The source material really emphasizes FE as a primary remedy because it tackles OVB by controlling for unobserved variables that are time invariant.
Time invariant. So characteristics that are inherent to the unit and remain constant throughout the whole observation period.
Exactly. For a panel of countries, this could be things like geography, its foundational legal structure, or some deep-seated cultural norms. For a corporate panel, it might be the fixed aspects of its management culture or brand equity that was established decades ago.
And these fixed, unobserved factors are almost always correlated with our explanatory variables, so they're a huge source of OVB.
A huge source. So how does fixed effects mechanically neutralize them?
That's the question.
Fixed effects works by transforming the data. It removes the unit-specific mean from every observation. You're essentially calculating the deviation of each observation from that unit's own average over time.
So you're not comparing firm A to firm B anymore.
Not directly. This process, we call it the within transformation. It effectively sweeps away the influence of any variable observed or unobserved that does not change over the sample period.
I see. So if I'm looking at R&D spending X and profitability way across 100 firms for 20 years, I know some firms are just inherently better run. That's my unobserved Z.
A classic time invariant omitted variable.
The FE transformation would eliminate that high baseline profitability of the well-run firm. It then only looks at the relationship between changes in R&D spending and subsequent changes in profitability, all within that same firm over time.
That is the conceptual genius of it. You're isolating the effect of changes within each unit. By eliminating that fixed heterogeneity between units, you significantly reduce the potential for OVB that comes from those static, unobserved characteristics.
Which is vital for forecasting because it helps you separate a true dynamic response from just a fixed structural advantage. But you mentioned there's a critical caveat. Fixed effects is not a complete solution. OVB can still be caused by unobserved variables that do change over time.
Yes, the time-varying omitted variables. This is the persistent nightmare for applied econometricians.
Because fixed effects only solves half the problem.
The half involving static, unobserved characteristics. But if your omitted variable Z is something like the pace of global trade integration or a time-specific technology shock, well, that's changing over time, and it affects all the units in your sample, probably to varying degrees.
And the fixed effects transformation can't control for it because it's not fixed.
It can't. So if I use FE to look at the effect of some policy X on growth Y, but I omit a time-varying factor like the diffusion rate of artificial intelligence Z, and that factor Z is correlated with my policy X.
Which it probably is, because AI could drive up the measured effectiveness of the policy.
Right. Then the bias persists. The model still suffers from OVB, but now we've at least narrowed the source down to factors that are dynamic.
And this leads us to the other conceptual strategies for dealing with this problem of endogeneity, which OVB is a primary form of, especially when we can't measure the true variable Z. Our sources list three main conceptual approaches: adding controls, using fixed effects, which we just covered, and employing instrumental variables. Let's move to that advanced technique, instrumental variables, or IV.
Instrumental variables techniques are deployed when we believe a key explanatory variable, Rx, is correlated with the error term, which is just the residual contamination from Z. We can't measure Z, we can't control for it directly.
So what does the IV approach try to do?
It attempts to find a new variable, let's call it WO, that acts as a clean proxy for the relevant variation in X.
This sounds conceptually brilliant, but in practice, very, very difficult. What conditions does this new variable W have to satisfy to be a valid instrument?
It has to satisfy two extremely stringent conditions. These conditions are the entire foundation of the IV methodology.
Okay, what's the first one?
First is the relevance condition. The instrument WM must be highly correlated with the problematic explanatory variable X. If W isn't related to X, it can't explain any of the variation in X, and so it can't help us estimate the impact of X.
Makes sense. It has to be relevant. What's the second, and you said far more challenging, condition?
The second is the exogeneity condition. It's also known as the exclusion restriction. The instrument WH must be uncorrelated with the error term U.
What does that mean in plain English?
It means that W can only affect the outcome Y through its relationship with X. If WU is also correlated with the omitted variable Z that's polluting our error term, the instrument is invalid. The IV estimate will also be biased.
This is the practical hurdle that makes IVs so difficult. It seems easy enough to find a variable that's relevant to X, but how can researchers truly know that their chosen instrument W is only affecting U through X and isn't secretly correlated with some other omitted factor Z?
It's untestable.
Untestable.
You've hit on the central conceptual challenge of applied econometrics. Exogeneity cannot be proven statistically. It has to be justified entirely through careful, convincing economic reasoning, institutional knowledge, and theoretical argument.
So the researcher has to be able to argue, this instrument W acts like a random assignment mechanism for X, and it affects nothing else that drives Y.
That's the argument they have to make, and it has to be a very strong one.
So let's use that education example again. I'm trying to estimate the true effect of education on wages, Y, but I know ability Z is an omitted factor. I need an instrument W that is correlated with education, but completely unrelated to ability.
Right.
Maybe something like a change in compulsory schooling laws that forces some people to stay in school longer, regardless of their ability.
That is a classic example used in the literature. The argument is that the shift in the law forces people to get more education, so W is relevant to X. But the law change itself is random with respect to their innate ability, so W is exogenous to Z and U.
And if that argument holds up under scrutiny?
The IV method can produce an unbiased estimate of beta 1. But if the law change was, say, enacted at the same time as a massive public awareness campaign that changed people's general attitude toward work ethic, another omitted factor, then the instrument would be invalid.
We should also briefly mention proxy variables.
Yeah.
That's often the first conceptual attempt at fixing this, right? When we can't get the perfect measure of Z.
Yes. If we can't measure the true factor Z, like institutional quality, we tried to find a variable P that measures it imperfectly, like a bureaucracy ranking or something similar.
So it's a stand-in.
It's a stand-in, a necessary compromise, but it introduces its own set of problems. If the proxy P is a very good measure of Z, then we have successfully mitigated OVB. Great.
But if it's not?
If the proxy P only captures Z weakly, then P itself might be correlated with the error term, and we can reintroduce a form of bias known as attenuation bias, where the estimated coefficient gets biased towards 0.
So every solution we discuss, fixed effects, instrumental variables, proxy variables, it's all a series of trade-offs.
Every single one. They are all attempts to solve OVB, but each introduces new theoretical challenges or measurement limitations.
It seems like the pursuit of an unbiased estimate is less about running software and more about philosophical and economic integrity.
It really is. The ultimate objective is always the same: Restore unbiased estimation by eliminating that corrosive product of beta 2 times delta zx. And the solution requires careful economic reasoning about what variables should be in the model, not just statistical testing for correlation, because sometimes the most important omitted variables are the ones that are least measurable.
This has been an extremely rigorous deep dive into omitted variables bias. So to summarize for you, OVB is not just a mistake, it's a mechanical failure. It's defined by missing variables that are relevant to your outcome and are systematically correlated with the variables you kept in the model.
Which leads to those structurally and mathematically biased coefficients.
And we established that this bias is non-random, it persists no matter how big your sample size is, and by generating these systematic errors, it severely compromises all long-term trend projections and ultimately policy credibility.
Which can lead to massive economic misallocation. We also saw that remedies like fixed effects can handle the static, time-invariant, unobserved factors, but the bias remains persistent when those big structural factors are changing dynamically over time.
We really pushed the technical envelope by explaining how that bias is formally defined as the product of the omitted variable's true effect and the correlation between the included and omitted variables. Understanding that formula is really the key to seeing why advanced techniques like instrumental variables must satisfy that near-impossible criterion of exogeneity.
So what does this all mean for you as someone who relies on forecasts? We highlighted that the most impactful structural factors in our economy, the pace of technology, institutional evolution, demographic shifts, are often the hardest to measure accurately, and they change dynamically. That makes them the most likely candidates for time-varying, omitted variables that even fixed effects can't fully catch.
Which raises a final and, I think, provocative question for you to consider based on the material we've reviewed today. If the core challenge here isn't running the math, but achieving the theoretical rigor you need to prove the exogeneity of your factors.
And if human behavior and technological progress are inherently so difficult to isolate cleanly.
Should we view an unbiased economic forecast not as an expected outcome, but as an unattainable ideal that the best analysts can only ever strive to approximate?
The analyst's job, then, is to minimize the bias, not to pretend they can eliminate it entirely. Recognizing OVB is the essential first step in understanding the true uncertainty that is just inherent in economic prediction.
Okay, let's unpack this. We are diving deep today into really the core machinery of economic risk analysis. We're focusing on what is probably the most high stakes, but also the most simple question in the world of finance and policy. It's not about degree, it's about existence.
Yeah.
It's the simple if.
That's right. I mean, when you are sitting in the Federal Reserve or, managing billions at a hedge fund, the most critical uncertainties, they often just boil down to a binary outcome.
Right, a yes or a no.
Exactly. Will the economy enter a recession next quarter? Is this major trading partner going to default on its sovereign debt? Those are the questions.
So we're moving beyond the kind of forecasting you might see on the news, predicting how much GDP will grow or what the inflation rate will be.
Right.
And we're stepping into the realm of forecasting discrete events. And that, I assume, requires entirely different statistical tools.
It's a whole different ballgame. These are the tools built around what we call binary outcome variables. If the outcome can only take two possible values, yes or no, 1 or 0, you need a specialized regression model to accurately calculate that risk.
And our mission today is really to provide you, the listener, with a genuine shortcut. We're going to walk through the failure of the simple, sort of intuitive approach.
Which a lot of people try at first.
Oh, absolutely.
Yeah.
And then we're going to introduce you to the sophisticated nonlinear methods, the logit and probit models that central banks, global financial institutions, and expert analysts actually rely on.
Right.
We want you to understand not just what they use, but why they have to use it.
And to start, let's just establish that core concept. A binary outcome variable it's just a variable that takes only two values.
Super simple.
Super simple. Conventionally, we code the occurrence of the event, like a recession or a default, as a woman, and the non-occurrence, so an expansion or a successful payment, as 0.
So it's just a switch.
It's a switch. This 10 switch is the absolute foundation of modern economic risk modeling.
I think when most people picture economic data, they picture, line graphs.
Right. Continuous line.
The continuous flow of money or prices or growth.
Yeah.
So why is it that the most important questions, the ones that trigger these massive policy shifts, are fundamentally discrete? A yes or a no?
Yeah, that's a great question. It really comes down to the nature of economic decision-making and risk assessment.
Okay.
While those continuous variables like the unemployment rate or the GDP level, they give us the background noise, the magnitude of the
The
change.
texture of it all.
The texture, exactly.
Yeah.
The discrete variables define the critical boundaries. Economic systems often have these tipping points or regime switches that necessitate a 10 classification.
So it's not just the subtle slowdown that matters. It's crossing a defined threshold.
Yeah.
Can you give us some concrete examples that really drive this home for the listener?
The most prominent example is the one we started with, recession forecasting. An economy is either in a recession, a one-mit, or it is not, a zero.
Okay. Right.
You can have 0.1% growth or 2.5% growth, and statistically, both are in the expansion regime. Both are a zero. But the moment GDP contracts for 2 consecutive quarters, the regime flips to 1.
And everything changes.
Everything changes. That flip triggers automatic responses. It changes market sentiment. It completely reshapes policy narratives.
And these discrete variables are really the language of risk, aren't they? If you're managing a portfolio of, say, corporate bonds, your primary concern isn't whether company X's profits drop by 10% or 15%.
No, not at all.
The existential question is, will company X default on its obligations, yes or no?
Exactly. Firm default is the classic microeconomic binary outcome. It's not about loss severity. That's a continuous problem for another day. It's about loss occurrence. You either default or you don't. And another key example is found in central bank policy around inflation.
Okay, this is interesting because inflation control is all about percentages, which sounds totally continuous. How does that turn binary?
Well, central banks often set explicit policy targets. For example, if the inflation rate exceeds the 2% target by a certain margin for too long,
A line in the sand.
a line in the sand, it can trigger a mandatory review or specific, very rapid policy tightening actions. So the binary question becomes, does inflation exceed the policy target, a 1, or does it remain within the acceptable range, a 0?
And the moment that one flips on, the whole policy toolkit opens up, whether it's triggering social safety nets or activating emergency liquidity facilities.
Precisely. We see this with unemployment, too. Whether unemployment rises above some defined critical threshold, say the long-term non-accelerating inflation rate of unemployment, or NARU,
Right.
that can trigger specific legislative or automatic stabilization programs. The policy response often hinges on the occurrence of the event, not just the magnitude of the movement toward it.
So the analyst's ultimate goal here isn't to forecast an absolute value, it's to construct a measure of, conditional likelihood. They're trying to quantify uncertainty.
That is the core function. Binary outcome models are designed to specifically forecast the likelihood, the probability of these critical economic events happening, given a set of current economic conditions.
Okay, so you're modeling the conditional probability, the classic P of y equals 1 given x.
That's the one. PY1 X seal, where Y is the event, the 1 or 0, and X represents all our explanatory variables.
And that x vector is doing all the heavy lifting. It includes everything from high-frequency financial variables to broader macroeconomic trends.
Absolutely.
So if you're predicting a recession, your X might include the yield curve spread, consumer sentiment, durable goods orders,
Yeah.
all that stuff.
Yes, exactly. The input variables are continuous and they're constantly changing, but they're all pushing the needle on the probability output. And this output, the probability, must, by definition, be constrained between 0 and 1.
Which is key.
It's everything. And it makes the model absolutely central to modern early warning systems, particularly in global finance, where risk management is paramount.
It seems like if so many of the most important questions are binary, the answer to how do we model this should have been immediately obvious and simple. But that simplicity, as is so often the case in econometrics, is a trap.
It is a huge trap. When analysts first started working with these 10 outcomes, their first, most intuitive step was to just use the workhorse of econometrics, standard linear regression.
OLS, ordinary least squares.
Ordinary least squares. And when you apply OLS to a binary dependent variable, you get what's called the linear probability model, or LPM.
Okay, let's establish the structure here. The LPM is basically saying that the probability of the event occurring, this PMEOPR, is just a straight line function of your inputs.
A simple straight line, PR1x equals 0 plus beta 1 by 1 plus dots, and so on.
And that explains the model's huge initial appeal, right? The interpretation is just wonderfully simple. Since the predicted value of y is now the predicted probability, the coefficients, the betas, directly measure the marginal effect on that probability.
It's so clean. So if I find that my coefficient, my beta eta $1 on the unemployment rate is 0.04, I can confidently tell a policymaker. A 1 percentage point increase in the unemployment rate raises the probability of the event by 4 percentage points.
Wow. That's clean, policy-ready information. It's beautiful.
Yeah, it's the dream of simple interpretation, but here's where it gets really interesting.
The catch.
The big catch. This simplicity renders the model statistically invalid and, frankly, logically nonsensical for any serious use. The limitations of the LPM are not minor technical quibbles. They are fundamental, crippling flaws.
Okay, let's start with the failure that's easiest to grasp. The impossibility of the output.
This is the glaring logical inconsistency. Since the LPM uses a straight line to relate the inputs to the output probability, there is absolutely nothing in the math to prevent that line from producing values outside the valid probability range of 0 to 1.
So you could feed in an extreme economic scenario. Maybe the yield curve is severely inverted, consumer confidence has just hit rock bottom, housing starts have collapsed.
All the red flags are flashing.
And the linear model just keeps going in a straight line, extrapolating way past the observable data range.
Exactly. The model might spit out that there is a 115% chance of a banking crisis.
Which is meaningless.
It's meaningless. Or, conversely, if things are extremely good, you might get a predicted probability of negative 10%. A negative probability is mathematically absurd. A 115% probability violates the fundamental axioms of statistics.
So if a model cannot guarantee that its output is a valid probability, you just can't trust it for anything high stakes. It's fundamentally broken as a forecasting tool.
It fails the litmus test of logical consistency. You can't base billion-dollar decisions on a model that can spit out nonsensical percentages. This failure alone forces economists to look for functions that mathematically constrain the output.
Okay, so that's problem one. And the second reason is deeper, right? It's rooted in a statistical assumption failure, the issue of heteroscedasticity.
This is the statistical rot inside the LPM. Standard OLS regression relies on the assumption of homoscedasticity, that the variance of the error term is constant across all your observations.
The error term being the difference between the actual outcome and what the model predicted.
Exactly. But with the LPM, the dependent variable can only be 1 or 0, so the error term variance is directly tied to the probability itself.
How does that work?
Well, the error variance mathematically has to be heteroscedastic by construction. For a binary outcome, the error variance is $t$ times 1 p-day, where p is the predicted probability.
Okay, let's use an analogy to slow this down. Imagine you have a weighted coin. If your model predicts the probability of heads, which is R1, is, say, p equals 99.
So you're almost certain.
I'm almost certain the result will be 1. The variance there, 99 times 0.011, is tiny. You're highly certain.
Right. Now contrast that with the most uncertain scenario, a fair coin, where the model predicts p equals 0.5.
A 50-50 shot.
The variance is 0.5 times 0.55, which is $2.55. This is the maximum possible variance. The outcome is highly uncertain, which leads to a large error term.
So the error term isn't a constant spread around the line. It's a systematic function of the predicted probability. The uncertainty is low when the probability is near 0 or 1, and the uncertainty is at its maximum when the probability is 0.5.
This is the definition of heteroscedasticity. The error variance changes systematically, and the critical consequence of this for standard OLS is that while your coefficient estimates might still be unbiased, they are no longer efficient.
Meaning they're not as precise as they could be.
Exactly. But more importantly, your standard errors, which are calculated based on the assumption of constant variance, they become unreliable. They're just wrong.
And if the standard errors are unreliable, you lose the ability to perform valid statistical inference. That's the devastating consequence for the analyst, isn't it?
It is the death knell for the LPM in any serious policy analysis. If the standard errors are wrong, your t-statistics are wrong, and you cannot confidently assess whether an explanatory variable, say, a 20 basis point change in the term spread, significantly affects the probability of recession.
You might conclude a factor is highly important when it's just statistical noise, or vice versa.
You're flying blind.
So we have two fatal flaws. The model produces illogical outputs, probabilities greater than 1 or less than 0, and even when the output is logical, we can't trust its statistical significance because of the inherent error structure.
Right.
This basically mandates the transition away from linear models and towards something much more complex. Okay, so the LPM failed because it was a straight line that couldn't respect the boundaries of 0 and 1. So the mathematical necessity is pretty clear. We need a nonlinear function, something that can take all the inputs, combine them, and mathematically force the resulting probability into that valid 0 to 1 box.
That's the necessity of nonlinearity. We have to employ a function that transforms the linear combination of predictors, which we call the linear index, into an output that smoothly approaches 0 and 1, but never actually reaches or crosses them.
That S-shaped curve.
We need an S-shaped curve, or a sigmoid function.
And this brings us to the famous workhorses that every financial institution uses for risk scoring and binary forecasting.
Exactly. The two main nonlinear models are the logit model and the probit model. Structurally, they're very similar. They really only differ in the precise mathematical curve they use for this transformation.
Let's talk about that mechanism. They use something called a cumulative distribution function, or CDF. How does a CDF fundamentally solve the LPM's impossible probability problem?
Well, a CDF, whether it's the standard normal distribution for probit or the logistic distribution for logit, is designed to map any real number, from negative infinity to positive infinity, to a value strictly between 0 and 1.
So the process still starts linearly, deep inside the model. The model first calculates the linear index.
Right, the simple beta dollars plus beta 1 by 1 plus dots.
We can think of this index as the underlying latent variable, which conceptually measures the propensity or the strength of the forces driving the event.
That's a crucial distinction. The linear index, which we can call sex beta da, is not a probability. It's a measurement of propensity. And this index can still range from negative infinity to positive infinity.
Okay.
So if the index is highly negative, the propensity for default is low. If it's highly positive, the propensity is high.
And the CDF is the mathematical gatekeeper. It takes that raw propensity score and just translates it into a legitimate probability, squashing the ends of the distribution.
Yes. For example, if the linear index is, say, -5, indicating a very low propensity, the CDF translates that to a probability very close to 0, maybe 0.007. If the index is +5, the CDF translates that to a probability close to 1, maybe 0.993. This S-curve geometry is the elegant solution that fixes the logical failure of the LPM.
That S-curve also captures a much better intuition about risk than a straight line does. As you approach certainty, either 0% or 100%, it becomes exponentially harder for additional news, positive or negative, to move that probability needle further.
That's a key economic insight modeled by the curve. For example, if a company is already at a 99% probability of default, even a massive increase in its debt load can only marginally push that probability to, say, 99.9%.
The effect dampens.
It dampens as you approach the boundary. Linear models simply cannot replicate this ceiling effect.
Now let's get into how these models are calculated. We mentioned OLS is out and something called maximum likelihood estimation, or MLE, is in. This is a very different beast from just minimizing squared errors.
It's a totally different philosophy. OLS seeks to minimize the vertical distance between the actual data points and the fitted line.
Right.
MLE, conversely, seeks to find the set of coefficients, the betas, that maximizes the likelihood, or the joint probability, of observing the specific sequence of outcomes, the ones and zeros, that we actually see in our data.
Okay, so MLE looks at the entire data set and asks, given that we saw this firm defaulting away and this other firm not defaulting, a zero low, what parameters make this specific history the most statistically likely outcome under our logit or probit function?
That's the core concept. It treats the observed data sequence as fixed, and it calculates the parameter set that makes that sequence the most probable outcome. And because logit and probit models are nonlinear, MLE provides consistent and efficient parameter estimates.
And consistent means the more data you feed it, the closer your estimates get to the true underlying economic parameters.
Correct.
And efficient means you get the smallest possible variance in those estimates, giving you the highest precision.
And that precision is vital, particularly when we are trying to differentiate between factors that genuinely drive a rare event like a crisis and factors that are just correlated noise. MLE provides the statistical rigor required for high-stakes forecasting.
That then leads us to inference. Even with MLE, we still need reliable standard errors to assess the significance of our inputs. Are the standard errors from MLE automatically reliable, or do we still need extra checks?
For logit and probit, the standard errors that come directly from the MLE output are generally consistent, provided the model is correctly specified.
The big if.
The big if. However, especially in macro time series forecasting, we often employ robust standard errors, sometimes called heteroskedasticity consistent standard errors, just as a safeguard.
Why the safeguard if the functional form already addresses the error structure better than the LPM?
Because economic data often features complex dependencies, like serial correlation in the error terms over time, or subtle forms of misspecification. Using robust standard errors ensures that our statistical tests, our assessment of whether the yield curve spread is truly a significant predictor, are valid, even if minor violations of the ideal statistical assumptions persist.
So it's an added layer of certainty.
It's an added layer of certainty required when policy action is on the line.
This brings us to what is probably the most complex and arguably most important interpretation challenge. We love the LPM because the coefficients were the marginal effects.
So easy.
So easy. But now we've moved to logit and probit. They are structurally sound, but the interpretation of the raw output coefficients gets incredibly murky.
That is the biggest trap for the new analyst. And we have to issue a clear warning here. The raw coefficients, the betas calculated by the MLE and logit and probit models, do not directly represent the marginal effects on probability.
So you can't just read them off the table.
You cannot. If you mistake them for a change in percentage points, your forecast will be wildly inaccurate.
Okay, so why can't the coefficient be the change in probability, like it was in the LPM?
It goes right back to that S-shaped nonlinearity. The coefficient measures the change in the underlying linear index, or the latent propensity for a unit change in the explanatory variable. It does not measure the change in the probability itself.
Let's try an analogy. Imagine the S-curve is a steep hill. A 1-unit change in your input, your X, is like a certain amount of engine power. If the car is sitting on the steepest part of the curve, say around a 50% probability,
Right in the middle.
a lot of engine power translates into a large change in probability. You shoot up the hill.
But if the car is already near the top of the hill where the curve flattens out, say, at a 95% probability of recession, that same amount of engine power, the same unit change in X, translates into a tiny, almost negligible increase in probability.
The slope is nearly zero.
The slope is nearly zero. The impact of the variable is conditional on the current state of the economy. The raw coefficient is constant, but the real-world impact is constantly changing based on where you are on that curve.
Exactly. The effect on probability is non-constant. Therefore, economists must perform an extra crucial step. They must calculate the marginal effects on probability.
This is the step. This calculation finds the instantaneous slope of the S-curve at a chosen point, and that provides a meaningful, policy-relevant measure of impact.
So the marginal effect tells you, at this specific point on the curve, how much does a 1-unit change in X change the probability of the event?
Precisely. It is the derivative of the probability function with respect to the explanatory variable. Without this calculation, the coefficient is essentially uninterpretable for economic forecasting. It might tell you which way the wind is blowing, but not how fast.
And since the effect changes, analysts have to choose the scenario at which they evaluate that effect. And there are, 2 primary scenarios for evaluation.
That's right. The first and most common method, especially in academic literature or large-scale descriptive modeling, is calculating the marginal effect at the mean, MM.
Okay.
This involves calculating the effect when all explanatory variables are set to their sample mean values.
Which gives you a nice single number, a representative average impact of a variable across the entire data set. It's useful for just understanding the overall relationship.
It provides a typical or representative impact. But for a policymaker, the average impact might be less relevant than the impact during a crisis.
Of course.
And that brings us to the second, more policy-focused approach, evaluating the marginal effects at specific economic scenarios.
This is where the model truly becomes powerful for crisis management. Instead of calculating the effect at the mean, you calculate the effect when the variables reflect a stressed environment.
Imagine a central bank is designing a new regulatory stress test. They want to know, if interest rates rise and consumer confidence falls, what is the resulting marginal increase in the probability of a major bank failure? They would plug in those specific stressed values for their X variables and calculate the marginal effect right there.
The crucial insight here is that the policy advice shifts dramatically based on this evaluation point. For example, a minor monetary policy adjustment might have a negligible marginal effect on recession probability during a boom.
When the curve is flat near zero.
But that same minor adjustment might have a massive marginal effect when the economy is already balanced precariously at a 40% recession probability.
The steepest part of the curve. Policy efficacy itself is nonlinear, and these models allow us to actually quantify that.
So the bottom line for you, the listener, is if you're relying on binary forecasts, you must look for the marginal effect calculation, not the raw coefficient. That step separates sophisticated, reliable economic analysis from, well, misleading statistical malpractice.
It really does.
Moving from the theory of logit and probit, let's see this in action. The most critical application is forecasting economic turning points, predicting when the economy will switch from the zero regime, expansion, to the one regime, recession.
Yes, this process of identifying regime switches is essentially what the business cycle is all about. These models give us the probability of the next major switch, which is the primary tool for proactive fiscal and monetary policy.
I can imagine. Think about the Federal Reserve's long-standing focus on this. They aren't trying to predict if next quarter's GDP is plus 2% or plus 1%. They are focused on the probability of a downturn that would necessitate immediate drastic action.
Absolutely.
So we need to talk about the inputs. What data are proven to be effective in driving these binary models? What makes a good X variable for a recession model?
We tend to rely on a mix of standard measures and specialized leading indicators. General measures like current GDP growth and unemployment trends are useful as context, but the real power comes from indicators that look forward.
Things that rely on market participants' collective foresight.
That's the idea. And when we talk about market foresight, the financial variable that dominates this conversation is almost always the yield curve spread.
The famous yield curve.
It is the gold standard for many probit models of recession risk, and for good reason. The yield curve spread measures the difference between long-term interest rates, say the 10-year Treasury bond, and short-term rates, like the 3-month Treasury bill.
And the logic is, when long-term rates are higher than short-term rates, the spread is positive, signaling a healthy economy. But when the short-term rates jump higher than the long-term rates, an inversion, it signals that the market anticipates economic trouble ahead.
And future rate cuts, right? So plugging this spread into a probit model allows analysts to translate the market's expectation directly into a quantified probability. Historically, this model has performed exceptionally well.
How well?
Well, the probability generated by probit models using just the yield curve spread has successfully spiked ahead of most U.S. recessions since the 1970s.
Wow. So that makes for a very clean, testable model. If the spread drops below zero, the model registers a high propensity for recession, which the CDF then translates into a high probability of Y equals 1.
Exactly. Other critical leading indicators include things like consumer confidence indices, manufacturers' new orders, and sometimes measures of financial stress, like volatility indices or interbank lending spreads.
The selection of the right inputs is paramount, though.
It's everything.
And this leads us directly back to the concept of model specification risk. It doesn't matter if you use the most sophisticated logit model with perfect MLE estimation. If your explanatory variables are flawed, your output is, well, it's useless. Garbage in, garbage out.
Specification risk is the silent killer of predictive performance. And the most common pitfall is omitted variables bias.
Okay.
If you fail to include a crucial driver, say a new emerging source of systemic risk that the model just isn't calibrated for, the coefficients of the variables you do include will incorrectly absorb the effect of that missing variable.
So if I run a model predicting a housing market collapse, but I forget to include mortgage underwriting standards as a variable.
A big one to forget.
A big one, yeah.
Yeah.
Then the coefficient on interest rates might look artificially huge because it's trying to account for both the rate pressure and the absent risk from all that subprime lending.
Precisely. The model assigns explanatory power where it doesn't belong. This leads to a skewed interpretation and, more importantly, very poor out-of-sample predictive performance.
So it works great on the past data, but fails the moment you try to use it for the future.
Right. Analysts have to continuously validate their inputs, ensuring the model is forward-looking and captures the evolving sources of economic risk.
Let's wrap this section up by reiterating the output philosophy. These complex models do not generate certainty. They generate quantifiable uncertainty.
The output is strictly probabilistic, never deterministic. A successful forecast isn't the recession starts in Q3.
No.
It's the probit model estimates a 45% probability of the economy entering a recession within the next 3 quarters.
And why is that 45% so much more valuable than a simple yes-no prediction?
Because it shifts the whole policy framework to risk management. If a firm has a 10% probability of default, you might allocate some reserves. If it has a 70% probability, you start unwinding your exposure.
It allows for a graduated response.
A graduated response, exactly. The probabilistic output allows policymakers to implement tiered responses based on quantified risk, which enables superior scenario analysis. The decision maker can weigh the cost of a false positive acting prematurely against the cost of a false negative, which is failing to act during an impending crisis. That nuance is the model's greatest contribution to proactive economic governance.
We've established that logit and trobit models are robust, necessary tools for handling these binary outcomes.
Yeah.
But even the most sophisticated quantitative tools are not infallible. We need a balanced view of where these models can fall short.
Absolutely. The primary vulnerability of these models lies in their sensitivity, especially when you apply them to macroeconomics. They are exquisitely sensitive to their original specification and the parameters estimated from past data.
And this vulnerability is laid bare whenever the economy experiences a structural break. What exactly do we mean by that in this context?
A structural break is a major, often unpredictable shift in the fundamental relationships that govern the economy. Think of the 2008 financial crisis, or the sudden global shock of the COVID-19 pandemic.
Okay.
The estimated coefficients, the betas that you derive from pre-2008 or pre-COVID data, they may just cease to accurately describe the economic dynamics afterward.
So the model might be predicting risk based on the rulebook of the last expansion, which suddenly becomes completely irrelevant in the new regime of, say, high sovereign debt or persistent supply shocks.
Exactly. The assumption of stationary relationships breaks down. The model that was calibrated on a stable regime performs very poorly during and immediately after a period of high volatility or fundamental change.
So what do you do?
This necessitates constant recalibration. It requires analysts to use moving estimation windows or adopt even more complex regime-switching models that specifically account for shifts in variance and parameters.
The other major limitation we touched on earlier is the problem of rare events. High-impact crises are, thankfully, infrequent. How does the rarity of the event being predicted reduce a binary model's accuracy?
Well, if the event, the one, only occurs 5 times in a 50-year dataset, the maximum likelihood estimation process has very few successful observations to learn from.
Not a lot of data to train on.
Not at all. The model struggles to reliably distinguish the tree drivers of those 5 rare occurrences from all the surrounding economic noise.
It makes the prediction of a financial crisis, for example, inherently challenging, because there just isn't enough historical data featuring that specific outcome to robustly train the algorithm.
Right.
The scarcity of ones relative to the overwhelming abundance of ones, the periods of stability, means that even small changes in input variables can sometimes lead to overly dramatic shifts in the predicted probability. It can reduce your confidence in the model's performance during periods of low risk.
Okay, here is the crucial insight we have to leave the listener with. The limitation that no logit or probit model by its very design can overcome. What is the fundamental gap in their forecasting ability?
Binary outcome models only capture occurrence. They predict the probability of the event switching to 1. They fundamentally cannot capture the severity or the intensity of that economic event.
So the logit model might use the yield curve and consumer sentiment to output a 65% probability of recession, and that's hugely informative.
Very informative.
But the model is blind to whether that 65% chance corresponds to a mild 3-month contraction, what we might call a soft landing, or a multi-year catastrophic financial depression. That is the defining line. A crisis prediction is only half the battle. Policymakers require models that can estimate both the likelihood of a crisis and the size of the potential economic damage. Logit and probit models only provide the probability of the switch itself.
Yet, despite this massive limitation, the policy relevance of these tools remains absolutely central to global governance and risk management. Why do these models still sit at the heart of central banks?
They are the foundation of sophisticated early warning systems, or EWS. These systems are designed to monitor dozens of financial and economic variables simultaneously. When the aggregate probability calculated by the probit model exceeds some predefined danger threshold, say 30% for recession, the system flashes red.
And that compels immediate policy discussion.
It does. They move governance from relying on backward-looking data to risk-based policy planning, which allows for genuine contingency preparation.
Right.
Major institutions, the IMF, the World Bank, the Fed, they structure their contingency plans around the quantified probabilities these models generate. They can establish clear, tiered triggers. Low probability, maybe below 20%, means status quo. Medium probability, say 20 to 50%, means you start planning and preparing stimulus packages. High probability, above 50%, means you start implementation of proactive measures.
So this probabilistic framework turns the uncertainty into a management input. It means that even private risk units, managing vast pools of capital, are using these same tools to assess systematic risk, guiding decisions on hedging, on capital reserves, portfolio allocation.
It's everywhere. They provide the essential, statistically rigorous first step. Knowing the probability of the occurrence of a major event is simply non-negotiable for managing volatility in the modern economy. The challenge then becomes bridging that gap between probability and magnitude.
What a fantastic journey into the statistical backbone of high-stakes economic forecasting. We started with that really fundamental question, will it happen?
Yeah.
And we saw the spectacular failure of the simple linear probability model, which violated logic by producing impossible percentages and ruined inference through that unavoidable heteroscedasticity.
That failure forced us to adopt the robust complexity of the logit and probit models. We learned that these nonlinear workhorses use maximum likelihood estimation and that S-curve geometry of the CDF to guarantee that forecasts are logically sound, constrained, and efficiently estimated.
And crucially, we nailed the interpretive challenge. Analysts must calculate marginal effects on probability because the raw coefficients are, frankly, meaningless. The impact of an economic factor changes drastically depending on the current risk level of the economy.
And that's what separates reliable policy advice from error.
We established their critical role in forecasting regime switches, driven by powerful leading indicators like the yield curve spread, providing the quantitative risk estimates necessary for all those early warning systems. But our final provocative thought has to be about that major limitation we just discussed. These powerful models only forecast occurrence, not severity.
Right. So if a central bank's model forecasts a 50% probability of a financial crisis, a true coin flip of systemic disaster, how should policy weigh that risk?
A 50% chance of what, exactly?
Exactly. The model cannot distinguish between a significant but manageable market correction and an outright catastrophic economic collapse.
So the ultimate challenge moves beyond the initial statistical task of predicting the event. It moves to the far more difficult subsequent policy challenge of planning for the potential magnitude.
How much risk is acceptable when the downside could range from mild turbulence to global depression?
This is a huge question.
That gap, quantifying the probable cost of the probabilistic event, is really the next frontier for economic analysis. It requires integration with loss models, with regime-switching frameworks. It's an ongoing evolution in the fight against uncertainty.
Something to mull over as you see those financial headlines predicting the next slowdown. Thank you for joining us for the deep dive.
Welcome back to the Deep Dive. Today, we are wrestling with one of the most fundamental challenges in economics.
Predicting the future.
Exactly. But not just any future. We're talking about those absolute shifts.
The massive yes or no questions, the ones that, really dictate the health of an entire economy.
Things like, will the central bank raise rates?
Or the big one.
Yeah.
Will we enter a recession? Will this policy actually pass? He's just flipping a switch.
And your traditional statistical tools, they kind of fall apart when you ask them a question like that.
You really do.
So when you have billions of dollars, policy decisions, all of this risk management hanging in the balance, economists need something more rigorous.
Something that doesn't just guess. It needs to deliver a calculated, bounded probability.
And that's our deep dive for today. We're going into the heart of that framework, the logit model.
This is really the statistical architecture that turns all these complex indicators into an objective likelihood.
Our mission today is, well, it's ambitious. We want to give you a full but still conversational understanding of the logit model.
Right. We'll look at its structure, why it's necessary, the often very counterintuitive way you have to interpret its results.
And crucially, how it's actually used in the real world to forecast economic turning points. We've synthesized a lot of the core foundational research here.
The goal is that by the end of this, you'll have a clear shortcut to being well-informed about how this kind of serious risk-based decision-making actually happens.
You'll get that subtle but critical difference between just a simple linear prediction and a robust probabilistic forecast.
And to start, I think we have to establish its core identity. Logit is what we call a binary response model.
Binary, meaning the outcome you're trying to predict can only be one of two things.
Exactly. It can only exist in one of two states. We usually code them as a 0 or a 1.
So 0 could be, business as usual, and 1 is crisis.
Precisely. And here's the single most important concept to get right away. Logit models do not model the event itself.
Okay, what do they model then?
They model the probability of that event happening.
So we're not predicting a recession will happen.
No.
Yeah.
We are calculating the percentage likelihood that the system shifts into that recession state based on all the variables we're feeding it.
Which, when you think about it, is really the only intellectually honest way to talk about the future, right?
No one has a crystal ball.
The best you can do is assign a probability you have high confidence in.
And this whole approach is necessary because these critical outcomes, crisis versus stability, recession versus no recession, they're just inherently discrete, probabilistic events.
Okay, so let's dig into that foundation. I mean, the workhorse of stats is the linear model, the linear probability model, or LPM.
Simple, intuitive.
Very easy to interpret. So if we're just trying to map variables like unemployment to a 0 or a 1 outcome, why can't we just stick with that? Why all this extra complexity?
That's the perfect question to start with. Because if you understand the flaws of the LPM, the brilliance of the logic model becomes crystal clear.
So the LPM has problems.
It has two major debilitating theoretical problems when you apply it to binary outcomes. They make its forecasts not just unreliable, but frankly, often nonsensical.
Okay. Before we get to the flaws, let's talk about the need.
Yeah.
Beyond a recession, what other kinds of high-stakes questions demand a model like this?
Well, you're dealing with any event where the outcome is just yes or no. Think about, will a company default on its debt? Yes or no?
Will a consumer take out a loan they're offered?
Yes or no? Will inflation surge past a certain target? It's all about an abrupt change in state. So you need a model that actually respects the basic rules of probability.
Okay, so let's say I ignore that. I try to force a simple linear model onto one of these problems. What's the most obvious disastrous flaw that I'm going to see?
The boundary problem. That's the most immediate and fatal one.
Boundary problem.
The LPM assumes a straight line relationship. It treats probability like any other number that can go up or down forever.
So, let's imagine a crisis is brewing. You plug in some extreme stress factors.
An unprecedented yield curve inversion, massive sovereign debt, you name it.
The model, just following its straight line, will just keep predicting higher and higher probabilities.
Exactly. Since the linear model doesn't know that 100% is a hard limit, it might confidently predict a, say, 120% probability of a financial crisis.
Or on the other side, in a really stable period, it might spit out a negative number.
A minus 10% chance of default.
Which is, 120% probability of anything isn't a probability at all.
It violates the fundamental axioms. The sum of all possible outcomes has to be 1.
So if your model can't even guarantee a prediction between 0 and 1, it's basically useless for any real risk management.
Precisely. And that is the logic model's core reason for being. It provides a mathematically rigorous structure that inherently guarantees your probabilities are stuck between 0 and 1.
But I have a question there. Couldn't a user just fix that? If the model says 120%, you just report 100%. If it says never 10%, you say 0%. Just cap the numbers.
That's a great point, and it's what people sometimes try to do. But no, it doesn't solve the problem. It just creates a new, subtler one.
And what's that?
This brings us to the second major flaw, the failure to account for what we call nonlinear effects.
Okay, let's unpack this.
If you just cap the results, you're pretending the relationship is a flat line at the extremes. But the real world is almost never linear like that.
Give me an example.
Think about the impact of unemployment on the chance of a recession.
Okay, so if unemployment is, say, low, maybe 4%, and it jumps up to 5%?
That 1-point increase might push the recession probability from, 10% up to 25%. Pretty big jump.
Right, the marginal impact feels really significant there.
It is when you're in that middle range of uncertainty. But now, what if unemployment is already at 9% and the economy is basically already in a recession? Probability is, say, 90%.
Yeah, if unemployment goes from 9% to 10%, that same 1-point jump?
It won't push the probability from 90% to 105%. It might just nudge it from 90% to 92%. The impact of that same change has shrunk dramatically.
I see the issue with the straight line now. Linearity assumes the impact is always the same. But in reality, when an event is already very likely or very unlikely, the system is kind of saturated.
Saturated is the perfect word for it.
It's like a dimmer switch, right?
Okay.
A small twist makes a huge difference when the light is halfway on. But once it's at 99% brightness, that same twist does almost nothing you can see.
That saturation effect, that diminishing return near the boundaries.
Yeah.
That's exactly what a linear model misses and what the logic model is mathematically engineered to capture.
Which gives you that characteristic S-shaped curve.
Yes, and it's why logic is a conceptually sound approach, not just a simple fix for a bad linear prediction.
Yeah.
So if the problem is these flawed probabilities and this flawed linearity, The logic solution is found entirely in its functional form. It's a mathematical design to enforce those constraints.
And we're about to show you the equation. Don't worry about memorizing it, but pay attention to the components, because this is where that logic guarantee really lives.
The probability of our event, which we call y1, occurring given all our data, x, is defined by this function.
P of y1 given x equals, well, it's a fraction with a lot of exponents.
It looks dense, I know.
Yeah.
It's the exponential of your linear combination of variables divided by 1 plus that same exponential.
Okay, so if I'm a policy analyst looking at this, what is the single most important part of that equation that creates the magic of that 0 to 1 boundary?
It's the exponential function,
Oh,
the x-bin part. You can think of it as a gatekeeper.
why?
Because for any real number you can possibly imagine, a massive positive number, a huge negative one, 0, when take e's raised to that power, the result is always a positive number. It can get very, very close to 0, but it can never be 0 or negative.
So no matter how wild our predictor variables get, that whole combination inside the exponent, the numerator of our fraction, the x part, can never be negative.
Correct. And the denominator is just that same positive number, plus 1.
Which means the denominator is always exactly 1 bigger than the numerator.
And since the numerator is positive and the denominator is strictly larger, the whole fraction, our predicted probability, has to be a number between 0 and 1.
It's a mathematical necessity. The model just cannot fail that test.
That's the structural rigor. That is the aha moment. The function isn't just designed to fit the data. It's designed to respect the rules of the universe. It's modeling. You literally cannot get a probability outside the bounds.
And it's that design that also enforces the S-curve, the non-linearity we were talking about.
Exactly.
Here's where it gets really interesting. Let's visualize that curve.
Okay, so if the combined effect of all your variables, that linear combination in the exponent, happens to be exactly 0.
Then the probability is 0.5, 50, 50.
Right. Now, as that linear combination becomes more and more negative, meaning your predictors are signaling stability, the exponential part gets closer and closer to 0.
And the whole probability approaches 0.
But never quite touches it. Conversely, if the linear combination gets really positive, signaling high risk, the numerator and denominator both become huge numbers.
But they're still separated by exactly 1, so the ratio gets closer and closer to 1.
But again, can never actually reach it. And this is the genius of the S-shape in application. It forces those diminishing returns we talked about.
The curve is steepest in the middle.
Right, between maybe 25% and 75% probability. That's where a change in a variable can cause a big swing in the probability.
But at the extremes, the curve flattens out.
Representing that saturation point. A massive change in your inputs might only produce a tiny, tiny change in the final probability.
So the math itself is an elegant model of reality. It's, relatively easy to move the needle from 40% to 60%, but it takes an enormous amount of new information to push it from 98% to 99%.
Precisely. And because of this elegance and this conceptual soundness, the logic model has really become the default binary choice model in many fields, but especially in econometrics and finance.
Is it the only one?
There is a close relative, the probit model, which uses a different function to get the same S-shape. But logic is often preferred in applied work because its algebra is a bit simpler and its coefficients can be translated into something called odds ratios, which we should probably get into next.
Okay, so the logic model solves the boundary problem beautifully. But that very mathematical elegance introduces a new challenge.
Interpretation. This is where the jargon can get really dense.
It is.
Because when you run a simple regression, the coefficient is everything. A coefficient of 1.5 means a 1-unit increase in x gives you a 1.5 unit increase in y. It's direct. That intuition is broken here.
Completely broken. The first rule of interpreting a logic model is that the coefficients, the betas, do not directly represent changes in probability.
So if I see a coefficient of, say, 3.0 on GDP growth.
That does not mean a 3 percentage point increase in probability. Not at all.
So what am I looking at when I see those raw coefficient values? What do they mean?
They represent the effect of your variables on the log odds of the event.
Log odds. Okay. This means we have to take a quick detour into what odds are and then what the logarithm of the odds are.
Let's start with odds. We use that term all the time, especially in sports or gambling. What's the formal economic definition of the odds of a recession?
The odds are just the ratio of the probability of the event happening to the probability of it not happening.
So P divided by 1P.
Exactly.
Give us an example with some real numbers.
Sure. If your model predicts a 75% probability of recession, so P is 0.75.
Then the probability of no recession is 25%, or 0.25.
Right. So the odds are 0.75 divided by 0.25, which is 3. We'd say the odds are 3 to 1 in favor of a recession.
And if the probability was 20%?
Then the odds are 0.20 divided by 0.80, which is 0.25, or 1 to 4 against.
Okay, so odds are a measure of relative likelihood. Now, what about the log part?
This is the key mathematical property of the logit model.
Yeah.
It is designed to be linear in the logarithm of the odds. When we take the natural log of that odds ratio, we basically turn that nonlinear S-curve relationship back into a straight line.
So the coefficients, the betas, are telling us how a 1-unit change in a variable impacts the logarithm of the odds ratio.
That is the correct formal interpretation. If the coefficient is 0.5, a 1-unit increase in x increases the log odds by 0.5.
But this is where the results become totally opaque to anyone who's not an econometrician.
Right. What does an increase of 0.5 on the log odds scale actually feel like? What does it mean for risk?
I have no intuitive sense of that. I know if the log odds are 0, the probability is 50-50. If it's positive, it's above 50%. Negative, it's below.
But converting a log odds of, say, negative 1.5 back into a probability is cumbersome. It's not something a policymaker can do in their head during a meeting.
So at best, you can use the sign of the coefficient for direction. Positive means more likely, negative means less likely.
Yeah.
The magnitude is locked away.
It's locked in that log odds framework. And this difficulty is why economists almost never stop at the raw coefficients when they present their findings.
I can just imagine the frustration. If I'm the Fed chair, I'm asking my team, how much more likely is a crisis now that the yield curve has inverted this much? I don't want an answer in log odds.
You need a percentage. You need something concrete to inform a multi-trillion-dollar decision.
So how do they bridge that gap?
This is where the entire field pivots to the concept of marginal effects.
Marginal effects.
They are the essential translation device. They take us from the mathematical complexity of logit back to the intuitive world that policymakers and regular people can understand.
So if log odds are the model's internal language, marginal effects are the universal translation, what's the formal definition?
A marginal effect measures the change in the predicted probability that results from a small change in one of your explanatory variables while you hold all the other variables constant.
So it takes us back to the question I want answered. If X changes by 1 unit, how many percentage points does the probability of Y change?
Precisely. But there's a huge catch.
Of course there is.
Unlike in a simple linear model, the marginal effect in a logit model is not constant.
Right, because of the S-curve. Tell us why these effects are so contextual.
The size of the marginal effect depends on 2 critical factors, and they both flow directly from that S-shape. The first is your current position on the curve.
Meaning the current probability level.
Exactly. The slope is steepest right in the middle, at 50% probability. So if the chance of recession is currently 50-50, a 1-unit change in a variable will have its biggest possible impact.
It might give you a 5 percentage point jump in probability.
But if the probability is already 95%, the curve is nearly flat. That same 1-unit change might only nudge the probability by, say, 1 percentage point.
So the existing economic conditions fundamentally determine how much power any new piece of information has to move the needle.
That's a perfect way to put it. This is why you'll hear economists talk about the marginal effect at the mean, or the average marginal effect. They have to specify the baseline they're using.
And what's the second factor?
The marginal effect of any one variable also depends on the values of all the other variables in the model.
How does that work?
Well, because all the variables are added together inside that exponent. So the impact of, say, a change in GDP is conditional on the current state of unemployment and the yield curve.
So if the yield curve is already steeply inverted, the economy is already stressed.
Right. And in that high-stress environment, a small negative GDP reading might have a much larger marginal effect on the recession probability than it would during a period of normal economic health. The variables all interact.
This sounds incredibly complex to report accurately.
It is. It's the unavoidable price you pay for the theoretical soundness of the logit model. It demands very careful reporting and contextualization.
So understanding how these complex coefficients and marginal effects are derived, that brings us to the estimation process itself. You said logic models don't use the standard ordinary least squares, or OLS, method.
That's right. Because the relationship is nonlinear, we need something more sophisticated. We use a method called maximum likelihood estimation, or MLE.
OLS is pretty intuitive. You're just drawing a line that minimizes the distance between the line and your data points. How is MLE different in its philosophy?
MLE has a totally different goal. It's not about minimizing errors in that geometric sense. Instead, MLE chooses the set of coefficients, the betas, that would maximize the likelihood of seeing the exact data sample that you collected.
So it works backwards from the data you have.
In a way, yes.
Yeah.
It looks at your historical data, the sequence of economic conditions, and the sequence of zeros and ones that actually happened, and it asks a question.
What question?
It asks, what set of coefficients would have made the probability of this specific history, these exact ones and is, as high as it could possibly be?
Ah, so it's finding the parameters that provide the most likely explanation for what already happened.
That's the perfect way to think about it. If you had 100 data points and 10 were recessions, MLE finds the parameters that make the logit function predict the highest probability for those 10 specific instances and the lowest for the other 90.
Is there a risk that it's too focused on fitting the past perfectly and maybe not as good at predicting novel situations?
That's a fundamental critique of any model based on historical data. But MLE is preferred here because, under the right conditions, its estimates are statistically robust. They're what we call consistent and efficient.
Meaning they get closer to the true value as you get more data, and they have the lowest possible error.
Exactly. It's the mathematically optimal way to estimate the parameters for this kind of function.
Okay, let's switch to application. This is where the rubber meets the road. Where does this model shine most brightly in the real economy?
Its primary strength, without a doubt, is in forecasting key turning points in the business cycle. This is really the cornerstone of modeling at central banks.
So, specific uses.
They are absolutely crucial for forecasting business cycle turning points. Identifying that moment the economy flips from expansion to contraction, and maybe most famously, for estimating recession probabilities over a certain time horizon.
Like 6, 12, or 24 months out.
Right. And beyond macro, it's used for systemic risk modeling, estimating the probability of a bank failure or a sovereign debt default.
What are the common predictors, the variables that are consistently fed into these big economic logic models?
They're almost always variables that tend to lead the business cycle. There are 3 staples that are in almost every model.
Which are?
First, GDP growth, or rather deviations from its long-term trend. Second, changes in unemployment, especially sudden increases. And third, and this is often the most critical one, the yield curve spread.
Let's pause on the yield curve. It's such a canonical predictor. Why does that spread between long-term and short-term interest rates work so well in this specific probabilistic framework?
It works well because it's a measure of market expectation about a discrete change in the future.
Explain that.
An inverted yield curve, where short-term rates are higher than long-term rates, means that the bond market is essentially betting on poor economic performance and lower interest rates down the road.
It's a signal of pessimism.
A powerful leading indicator of pessimism. So in the logit framework, as that spread tightens and then inverts, the model translates that growing market stress into an exponentially rising probability of recession. It perfectly uses that steep part of the S-curve.
So once we have our estimated model, we plug in the current yield spread, the latest unemployment figures, and the final output is a formal probability. Why is that so much more valuable for a policymaker than a simple, yes, recession is coming, alarm?
Because policy and finance are all about risk management. A simple yes-no gives a central bank no information about urgency or the scale of an intervention.
But a probability does.
A probabilistic output, like the model predicts a 70% chance of recession in the next 12 months, gives you an objective metric for risk-based decision-making.
It allows policymakers to set thresholds for action.
Exactly. The Fed might have an internal rule that if the model crosses a 35% probability, they automatically shift their policy stance. It gives them a quantified trigger point.
Which allows for proactive intervention, which is always better than reacting after the crisis has already hit.
Almost always more effective and far less costly. Logit translates all that complexity into a single, actionable risk metric.
All right, so we've established the logit model's theoretical superiority. Let's try to formalize its scorecard. If you had to summarize the key advantages, why is it still the standard?
First and foremost, it's that theoretically sound probability structure. The guarantee that your predictions will always be between 0 and 1 is, frankly, non-negotiable for serious modeling.
And second,
Its ability to capture those nonlinear effects, it makes it a much more realistic model of how economic systems and people actually behave. That saturation effect is real.
and the sources also emphasize its strength with rare events.
Yes, it's particularly well suited for forecasting rare but important events. Things like financial crises that don't happen often in your data but have massive consequences when they do.
Okay, that all makes sense. But no model is a crystal ball. What are the major caveats, the limitations that users have to constantly be aware of?
The primary weakness is how much it depends on the user's judgment. It's highly sensitive to what we call model specification.
Getting the equation right in the first place.
Right. If you misidentify a key driver or you get the timing of its effect wrong, your results are going to be misleading, no matter how elegant the framework is.
And that's directly tied to the variables you choose to include.
Absolutely.
Yeah.
Sensitivity to the choice of explanatory variables is huge. If you omit a crucial leading indicator, your model will consistently underestimate risk.
Garbage in, garbage out.
Exactly. And then there's the other big drawback, which is inherent in its binary nature.
It only predicts the flip of the switch.
Not the intensity of the event. It does not measure the severity.
So whether it's a short, shallow recession or a catastrophic depression.
Both are coded as 1. It's the same outcome to the model, which is fine for predicting the turning point, but for deciding on the size of the policy response, it doesn't give you enough information.
So the logic model can tell the Fed that it needs to act, but not whether they need a $100 billion intervention or a $1 trillion one.
Precisely. It's a risk trigger, not an intervention calculator. You need other models for that.
And finally, there's the big one. What if the economy itself changes? You mentioned structural breaks.
A structural break is a permanent, fundamental change in the relationship between variables, and it's the biggest threat to any forecasting model.
Because the model is trained on historical data, assuming those relationships are stable.
And if that underlying reality changes, the model breaks down. A famous example is the Volcker shock in the 1980s, which fundamentally changed how monetary policy and inflation worked.
A model trained on pre-1980s data would have been useless after that.
It would have performed very poorly. The same thing happened after the 2008 financial crisis. The old relationships between interest rates and growth just didn't hold up in an era of quantitative easing.
So you're constantly fighting the assumption that the past is a perfect guide to the future.
It's why this is as much an art as it is a science. You're always balancing the theoretical elegance with a messy, evolving reality.
So let's bring this all home with the so what. These aren't just academic toys. They are the bedrock of global financial risk management.
Absolutely. These models are used extensively by the highest stakes institutions in the world. We're talking about central banks like the Fed and the ECB and international financial institutions like the IMF and the World Bank.
And why are they so indispensable to them?
Because they allow policymakers to assess the likelihood of adverse scenarios with a quantified, objective metric. And because they provide a timeline, they can track the probability of a crisis rising from 10% to 20% to 40% over several months.
Which gives them the lead time they need for preventive action.
Exactly. Time to act before it's too late. It can save trillions of dollars. The logic model forces an organization to define its risk tolerance in a quantitative way. It's the trigger that moves policy from talk to action.
So we've been on quite a journey here. We started with this fundamental challenge of a yes-no economic forecast.
Move through the flaws of a simple straight-line model to this, elegant S-curve from the logit function.
Then we went into the weeds with log odds and learned that the real meaning is unlocked by these highly contextual marginal effects.
I think you, the listener, now understand the statistical architecture that's behind a lot of the major economic headlines you hear.
When an analyst on TV talks about elevated recession risk,
They're talking about a quantified probability from a robust, non-linear framework, likely estimated with maximum likelihood estimation.
and we also clarified that its greatest strength, its focus on that binary outcome, is also its greatest weakness. It can't tell you how bad the crisis will be.
And its accuracy depends completely on the economic relationships of the past holding true for the future.
So what does this all mean?
It means that while the logit function itself is mathematically perfect for what it does, its output is only ever as good as the inputs you give it.
And that leads us to a final provocative thought.
Given how extremely sensitive these models are to the choice of variables, the biggest improvement in economic forecasting might not come from more complex math,
But from what?
from the discovery of novel, uncorrelated indicators. The next frontier is finding variables that can signal systemic risk before the traditional ones like GDP and unemployment even start to move.
So finding ways to measure changes in human behavior, technology, maybe even environmental stress.
And translating those into effective inputs for these models, that's what will truly refine our ability to see the next big turning point coming.
Welcome back to the deep dive. If you are here, it means you, our dedicated listener, the learner, have shared a truly fascinating stack of sources with us. Today, we are strapping in for a high-altitude tour of the world of economic prediction. We're looking far beyond the simple models, venturing into the statistical deep end where, these really sophisticated tools are used to measure the messy, chaotic reality of global finance. Our sources today are all about advanced regression methodologies and economic forecasting. This isn't just about drawing a trend line on a chart, it's about building a robust statistical scaffolding, a complex machine designed to translate historical data into reliable, forward-looking insights. Insights that, at the end of the day, support trillion-dollar policy decisions. You want a shortcut to understanding how the world's most advanced analysts manage all this complexity, bias, and even time itself. Our goal for this deep dive is to take everything you shared and really provide those fundamental aha moments. We'll explain exactly how these models work, why they're so essential, and crucially, what their limitations are when the real world throws a curveball. Okay, let's unpack this.
And that unpacking is absolutely essential because the starting point really is to just acknowledge the foundational impossibility of the task. Economic forecasting is critical for everything. Government stability, corporate strategy, you name it. Yet the economy itself isn't governed by the laws of physics. It's a constantly shifting system. It's dynamic. It's driven by human psychology, sudden shocks, feedback loops. So if you try to predict this chaos using a simple method like a basic linear model that assumes everything moves in a straight proportional line, you're guaranteed to fail. The entire body of work covered in your sources, all these advanced regression methodologies, they exist for one reason. They exist because the simple models are just chronically insufficient. So our mission for this deep dive is really focused on the gain. What specific features do these advanced tools give us that the simple ones lack? We're looking for methods that deliver more accuracy, more robustness against changing conditions, and real policy relevance. We're moving beyond just describing what happened in the past and into the art and science of reliable prediction.
Absolutely. And when we say prediction, we're often talking about these high-stakes, discrete events, not just a smooth trend line. I mean, how do analysts look at this mountain of conflicting data and forecast the probability of a recession hitting next year? Or what statistical tools allow a central bank to estimate the likelihood of a major financial crisis erupting in the next quarter? That's not a straight line problem. And yes, we promise to translate the jargon. By the time we're done here, terms that sound intimidating now, like endogeneity, unobserved heterogeneity, and the power of channel data, they will be clearly defined. So get ready to ditch the straight line. The economy is much curvier and certainly much stickier than that. So let's start at the beginning then, a diagnosis. If basic regression is the statistical equivalent of a hammer, solid foundational tool, why has the field spent decades building these entire workshops full of specialized complex methods? Where does that hammer just, break down when it hits economic reality?
The failure is structural. Simple linear regression, the standard model, is based on a set of assumptions that are just. They're almost never true in economics. It assumes stability, isolation, and linearity. Your sources confirm that the moment we apply this to the real world, we run into three insurmountable problems. First, we have what's called structural heterogeneity.
Okay.
This just means the relationship between two variables, say government spending and GDP growth, isn't universal. It varies across different groups, different sectors. The effect of a tax cut on a small business in Montana is just structurally different from its effect on a multinational tech firm in Silicon Valley. A simple model tries to average all of these different relationships together.
So you end up with a single blended answer that's really true for nobody.
Exactly. Yeah. It completely distorts the unique economic landscape of all these different units.
Okay, so that's problem one.
Precisely. The second major clash is with what we call dynamic adjustment processes. Economics is fundamentally sluggish. Things don't happen instantly. Policy changes, interest rate moves, shifts in consumer confidence. They don't have an immediate full effect. They trickle through the system. We often see effects peaking 6, 12, even 18 months after the event that caused them.
Right. So a simple static model that assumes cause equals effect right now, it misses that whole journey.
It misses the entire adjustment path. It just can't model the inertia of the system. And third, and this is maybe the most challenging for policymakers, are discrete events and regime changes. Simple models are built on an assumption of continuity. They project incremental change.
But economies aren't like that. They're defined by sudden breaks, a global pandemic, a war, a new technology.
Or a sudden change in governing philosophy. Exactly. A simple linear model, it just can't predict a catastrophic non-incremental shift because it's only looking for those steady linear relationships.
Yeah.
This inability to forecast true black swan events is why these advanced applications are, they're completely non-negotiable for serious forecasting.
That structural reality, that the economy is fragmented, delayed, and prone to falling off these sudden cliff edges, that really highlights the limitations of simplicity. But what are the specific statistical flaws we see when we try to force that complexity into a straight line?
We can point to three critical factors that simple models just invariably miss. And addressing these is, well, it's the whole reason sophisticated econometrics was developed. The first one is persistence.
Stickiness?
Stickiness, exactly. Economic variables are sticky. They don't just change based on current policy. They're heavily influenced by their own recent history.
Yeah.
Think about housing prices. Even if the Fed raises rates today, prices are not going to crash instantly. Market psychology, inventory levels, existing loan structures. All of these things create inertia. Last quarter's high price influences this quarter's price, regardless of what's happening outside. A simple regression, which only looks at current factors, it ignores this crucial history. This leads to forecasts that either react way too sharply or snap back to some theoretical average way too quickly. They're just volatile and unreliable.
That persistence is often psychological too, right? Things like inflation expectations or wage demands. They become these entrenched beliefs that take a long time to unwind, even if the underlying conditions change.
Exactly. The economy is a feedback loop, not a single snapshot in time. The second factor simple models just butcher is nonlinearity. We use that phrase a lot, but let's be concrete. It means relationships are rarely straight lines. Your source material really highlights that the effect of a change often depends on the level of the variable itself.
Okay, give me an example.
Think about government debt. If a country has, say, 50% debt to GDP, adding another 1% might have a mild, pretty linear effect on growth. But if that country is already at 150% debt to GDP, adding that same 1% could trigger a catastrophic loss of investor confidence.
Right, leading to a non-proportional, nonlinear spike in bond yields and a sudden recession.
Precisely. The magnitude of the response changes depending on the context or the regime you're in. Simple models, because they assume proportionality, dramatically understate the risks in these extreme scenarios.
It's the statistical equivalent of saying that the strength you need to snap a twig is the same as the strength you need to snap a massive oak branch. You're just ignoring the context of the system.
That's an excellent parallel. And the third, and maybe the most elusive threat to a model's credibility, is unobserved heterogeneity.
The hidden variables.
The hidden variables. These are the important factors that are influencing the results that we just got. Yeah, we can't measure them, or we haven't collected the data. For instance, if you're modeling economic growth across the 50 U.S. states, you might include measured variables like tax rates, population, infrastructure spending. But you can't easily measure things like the historical institutional quality of a state government, or the entrepreneurial spirit unique to a specific region, or its proximity to a critical supply chain.
And if those unmeasured hidden things influence both your measured variables and the outcome, your conclusion is tainted.
It's completely tainted. The model might attribute all the growth to low tax rates, your variable X, when in reality the low tax rates are just correlated with a strong, unobserved regional work ethic, your unobserved factor Z. Advanced regression is the deliberate attempt to isolate and neutralize that unobserved factor, to stop it from corrupting the causal story.
So if simple models are constantly missing this inertia, these critical breaking points, and they're being polluted by hidden variables, the advanced goal is to build models that are explicitly structure-aware, time-aware, and bias-aware.
That is the entire goal. The advanced applications are designed specifically for these complex data structures and dynamic relationships. This commitment to incorporating the actual messiness of the real world is how we build predictions that are genuinely robust and, actually useful.
Okay, so building on that, let's talk about how economists actually structure their data to capture both the who and the when of the economy at the same time. This brings us to a concept that's just absolutely central to modern empirical work: panel data models.
Right.
Panel data is this critical innovation that allows analysts to compare, apples to oranges, but in a very structured, measurable way. So if you have 20 countries and you observe their GDP, their inflation, and their interest rates over 30 years, you now have this massive data set that combines both cross-sectional variation
The differences between the countries.
and time series variation.
How each country changes over those 30 years.
It's a multidimensional lens that just dramatically increases the quality and the quantity of information you have to work with.
And panel data is so powerful because it allows us to control for factors that would otherwise lead to that unobserved heterogeneity we just talked about. The ability to track the same unit over time, that's what enables the use of fixed effects models.
Okay, fixed effects.
This is maybe the most elegant solution to that unobserved time invariant problem. Think back to our U.S. state example. We said that a state's geography or its deep-seated institutional history influences its economy, but we can't put a number on it. Fixed effects solves this by controlling for all those unique, unmeasured characteristics that stay constant for that state across the whole sample period.
How does the model actually control for them, though? Does it need a separate variable for institutional quality or something?
Conceptually, no. The technique often uses a mathematical trick called demeaning, or a within transformation. For every state, we calculate the average of all its variables over that 30-year period. Then, we only look at the variation from that specific average. By doing this, we basically strip away all the unique constant differences between, say, Texas and Massachusetts.
So you're filtering out the static starting point.
Exactly. You're left only with the differences within Texas over time and the differences within Massachusetts over time. We're essentially modeling only the changes.
That is incredibly valuable. So if I'm studying the impact of education spending on growth, fixed effects automatically filters out the impact of things like, say, historical, culture, or climate, which don't change. That lets me isolate the true impact of the spending increases that did change over those 30 years.
Precisely. You isolate the causal effect by removing the persistent unique noise. But, and this is an important trade-off for you, the listener, to remember, by using these entity fixed effects, we implicitly sacrifice the ability to study the impact of any variables that don't change over time. If a state's tax laws never changed in your sample, a fixed effects model can't tell you the impact of that specific law, only the impact of changes in that law. That's a limitation analysts have to manage. And on top of that, we also use time-fixed effects in these panel models.
Okay, so that's another layer.
Right. While the entity fixed effects control for things unique to the state, time-fixed effects control for things that affect everyone in the data set equally in a specific period. Think of the 2008 global financial crisis, or the oil shocks in the 1970s. These are factors that hit all entities, no matter what their individual structure was.
You get maximum clarity.
You get maximum clarity. By including both types entity and time-fixed effects, we filter out the unique starting point of the unit, like Texas, and the common shock of the period, like the 2008 crash. What's left is a high-resolution, unbiased picture of the true dynamic relationship we're trying to forecast.
That structure helps us sort the who and where of economic activity, but we're still missing the how fast. Since the economy doesn't run on these instantaneous reactions, we have to build that inertia, that lag time into our equations. Here's where it gets really interesting, because once we have our dual-dimension panel data, we move into the realm of dynamic regression models.
And dynamic regression is the explicit recognition that the system has momentum. We can't assume immediate adjustment. We have to model the delayed response. So to capture this realism, dynamic models are built with lag relationships right at their core.
Lag relationships.
The most direct way to do this is by incorporating lag-dependent variables. This just means using yesterday's value of the thing we're trying to predict, say last month's inventory level, to predict today's inventory level. For highly persistent variables like inflation or unemployment or corporate debt, the best predictor of the future is its immediate past. This is how we model that inertia without needing to know every single microfactor driving the stickiness.
But the cause itself can be delayed too.
Right, which brings in lagged explanatory variables. Consider the effect of a big infrastructure bill. The bill might pass today, but the actual spending and stimulus won't peak until maybe 18 or 24 months down the line when projects actually start.
So we'd model the policy change not just as it is now, but as it was 6 months ago, 12 months ago, and so on, to trace that full delayed impact.
Precisely. We're modeling the gradual adjustment to the shock. Analysts will use what are called distributed lag models to figure out not just the total long-run impact, but the specific path of adjustment. how much of the effect hits in month 1, month 6, and month 12. Forecasts from these dynamic models are way more stable and reliable because they reflect the actual measured speed at which people and markets react.
Now, panel data and dynamic models are fantastic for structuring our data and incorporating time, but they don't solve these fundamental issues that threaten the integrity of the whole thing. We have to address omitted variables, bias, and endogeneity. These are the twin threats to achieving credible causal inference, and so credible forecasting.
They are the biggest hurdles in establishing causality, without a doubt. Omitted variables bias, or OVM as we mentioned, happens when you forget to include a key variable, z, that's correlated with both your cause, x, and your effect, y.
Right, the ice cream and shark attacks example.
The classic example. If you measure ice cream sales, x, and shark attacks, y, over the summer, you'll find a strong positive correlation. A simple model might suggest eating ice cream causes shark attacks. The omitted variable is, of course, the temperature, z. High temperature causes both high ice cream sales and more people to go swimming, which leads to more shark encounters. If you omit temperature, your coefficient for ice cream is totally meaningless.
And in economic terms, if I'm studying how capital investment X affects growth Y and I omit technological innovation Z, which drives both investment and growth, I'll vastly overstate the impact of just simple investment.
Absolutely. The advanced solution often starts with just better data and using control variables. But OVM is actually simpler than the other problem, endogeneity. Endogeneity is truly complex because it suggests the arrow of causality runs both ways, or that our measurement errors are all tangled up with our explanatory variables.
So simultaneity.
Primarily, yes, simultaneity. X influences Y, but Y is simultaneously influencing X. Your sources discuss the link between government spending, X, and GDP, Y. A simple model says spending boosts GDP. But governments often increase spending because GDP growth is predicted to slow down. So the predicted GDP is influencing the spending decision. They're jointly determined, and modeling it as a one-way street makes your forecast totally biased and unreliable.
This sounds like a philosophical problem as much as a mathematical one. I mean, how do you untangle chicken and egg situation with statistics?
That's where we have to deploy some highly sophisticated methods, primarily what are called instrumental variables, or IV techniques. The concept is really clever, but it's very technical to execute. We need to find an instrument, a variable, let's call it Z, that does two very specific things. One, Z has to strongly influence our explanatory variable, X, the potentially endogenous one. And two, Z must influence the dependent variable, Y, the effect, only through X and not through any other side channels. It acts as an external nudge that lets us isolate the truly random exogenous variation in X.
That sounds notoriously difficult to find in the real world. I have to challenge this a bit. The sources noted that finding a truly valid instrumental variable is, well, it's really hard. If the instrument is weak, doesn't that complex technique actually introduce more bias than a simple model?
That is a critical point and a massive area of debate in empirical economics. If the instrument Z is weak, meaning it doesn't really correlate with the cause, X, or if it violates the exclusion restriction, meaning it does influence Y directly, then yes, using instrumental variables in that case can dramatically magnify the existing bias or even introduce new, larger biases. So you have to be very careful, very careful. This is why IV methods, while essential for credible causal inference, are treated with great caution. For example, if we wanted to study the causal impact of crop supply, X, on food prices, Y, we might use regional rainfall, Z, as our instrument. Rainfall affects the supply of crops, but presumably rainfall in Iowa doesn't directly influence consumer demand for bread in New York. If that assumption holds, rainfall filters out the noise. But the credibility of the entire forecast rests completely on the quality of that instrument.
So by addressing these bias issues, we drastically improve the credibility of the forecast. Policymakers have to be confident that the effect being measured is real and not just some statistical artifact.
That's the whole game, credibility.
We've built the scaffolding accounting for complex structure, time lags, cleaning up bias. But as we previewed, not all economic questions are continuous. What happens when the forecast isn't about how much GDP will grow, but will the economy tip into a new regime? This is the domain of limited dependent variable models, a fundamental shift in forecasting.
That's right. When a key decision rests on a binary outcome, will the country enter a recession? 1 or not? 0. Will the policy pass? 1 or fail? 0. Standard linear models are useless. A linear regression line can predict probabilities of, 120% or minus 30%, which are mathematically absurd for a real-world probability.
Doesn't make any sense.
It makes no sense. So advanced regression deploys specialized models to constrain the predicted outcomes within that logical 0 to 1 range, interpreting the result as a probability. These are the logit models and probit models. Conceptually, instead of a straight line, these models use an S-shaped curve. As the explanatory variables say, the spread between short-term and long-term interest rates, a classic recession predictor move from low to high. The model's output smoothly transitions from a probability near 0, meaning no recession, to a probability near 1, meaning a recession is highly likely. It compresses the prediction into that 0 to 1 interval.
So the output is immediately actionable for risk managers. They get a percentage chance.
Precisely. These models are foundational for forecasting critical discrete events. Recessions, financial crises, major policy changes. They shift the entire conversation away from point estimates like GDP will be 2.5% to a probabilistic risk assessment. Based on the yield curve, there's a 75% probability of a recession in the next 12 months. That difference transforms forecasting from just predicting a path to actually assessing systemic risk.
That probabilistic approach is essential for risk management. But sticking with the reality of economic complexity, we have to go back to nonlinearity. If we accept that a small shock is treated differently than a big shock, what specific tools let us map the curves of the economy?
We use specialized nonlinear regression applications that explicitly model the idea that the impact of a shock changes depending on the current economic state. This is how we model nonlinear responses to economic shocks.
There's different regimes.
Different regimes, exactly. These models can recognize, for example, a regime of high capacity utilization versus a regime of low capacity utilization. The impact of a new corporate tax break during a recession when capacity is low might be large and sustained, but that same tax break deployed when the economy is already booming at high capacity might just lead to temporary price inflation.
And what's a tool for that?
A simple example of such a tool is a threshold autoregressive model, or TAR model. This model calculates one relationship, one set of coefficients. If a variable is below a specific threshold, say unemployment is below 5%, and it calculates a completely different relationship if that variable crosses the threshold when unemployment is above 5%.
So instead of one single equation for the entire economic cycle, we have two or more equations that kick in depending on whether we're in a high-growth state or a slow-growth state.
Exactly. And this allows us to capture asymmetric effects, which are central to realistic economic modeling. The economy does not respond symmetrically to positive and negative impulses. Layoffs tend to accelerate faster than hiring, and investment tends to seize up much quicker during a sudden downturn than it accelerates during a boom.
That makes intuitive sense.
Right. And by using these nonlinear models, we gain crucial realism. The model can anticipate that, for instance, interest rate hikes are felt much more acutely in a downturn because debt burdens are already heavy, or that positive shocks have diminishing returns once the economy hits its resource limit. This provides a far more nuanced picture for anticipating crises.
We've incorporated complex structures, time lags, bias correction, and non-straight lines. That is a lot of extremely messy real-world data being forced into these highly sophisticated equations. How do we ensure that the statistical conclusions we draw from this incredibly complex process are actually valid? I mean, how do we trust the reported uncertainty?
That is the final structural hurdle, validating the statistical inference. Economic trend data is notoriously noisy. It's characterized by two massive statistical headaches: serial correlation and heteroscedasticity. If we ignore them, we end up drawing conclusions using standard errors that are just flat out wrong.
Okay, let's break those down. Serial correlation first.
As we noted, economic errors are often related across time. If the model systematically overpredicts consumption growth this quarter because of some unmodeled noise, it's likely that noise will persist and cause an overprediction next quarter too. This dependence in the error terms violates a core assumption of standard regression, that all errors are independent, and the result is that your calculated standard errors are artificially small.
So you end up thinking your coefficients are much more precise and certain than they actually are.
Exactly. You might declare a policy intervention to be statistically significant with 99% confidence, when in reality the true confidence interval is much, much wider.
And the second one was heteroscedasticity.
Heteroscedasticity. This just refers to changing volatility over time. The noise in the forecast isn't constant. Consider investment volatility. During stable periods, the error around your investment forecast is small. During a financial panic, the error is massive. If your model assumes the volatility is constant, which is the definition of homoscedasticity, it will produce misleading standard errors. There'll be too high in stable periods and way too low in volatile periods.
So what's the fix?
The solution provided by advanced applications is to use robust standard errors and other adjusted inference methods. These are critical. They don't change the estimated effect, the coefficient. They change the calculation of the uncertainty around that coefficient.
How does that adjustment work, basically?
Instead of assuming the errors are all independent and identically distributed, which is the classic assumption, robust standard errors recalculate the variance based on the observed pattern of the errors. It accounts for the fact that volatility changes and that errors are correlated over time.
So the whole point is to make sure we can trust the results.
The whole purpose is to ensure valid statistical conclusions. You have to be able to trust the magnitude and the reported uncertainty of the effects. Or the most complex, unbiased, nonlinear model in the world is, well, it's useless for genuine decision-making.
We've built the advanced model, checked for every form of bias, incorporated nonlinearity, and corrected the statistical noise. Now comes the moment of truth. How do we actually test if this complex piece of machinery is a good forecaster and not just some elaborate way to describe the past?
This shifts our focus entirely away from how well the model fits the historical data, which is the easy part, to how well it performs when making true forward-looking predictions. Advanced regression applications place paramount importance on out-of-sample forecasting performance.
That's the gold standard.
It is the gold standard. A true test involves training the model on, say, data from 1980 to 2010, and then asking it to predict the data points from 2011 to 2020. Data the model has never seen before. If the model has just been overfitting the historical noise, it'll perform beautifully on the training data, but then fail miserably on the unseen data.
It's the difference between memorizing the historical answer key and actually understanding the underlying mechanism. A student might ace a test using memorization, but then fail when asked to apply the principles to a new problem.
A perfect analogy. A model that focuses on persistence, dynamics, and real causality, all the features we discussed, that should generalize well to future periods. A model that explains 95% of the past, a high R-squared, but consistently predicts unseen data poorly. That's dismissed. A model that explains 80% of the past but consistently produces accurate, stable, out-of-sample forecasts is invaluable.
Okay, so there's more to it than just that.
Oh yeah. Advanced model evaluation also requires rigorous testing of its sensitivity to model specification. This is crucial for policymaker confidence. It asks the question, how much does the forecast change if we tweak one minor parameter, say, changing an assumed time lag from 6 to 7 quarters or using a slightly different definition for a variable? If a forecast changes radically based on a tiny arbitrary change in a structure, the model is inherently unstable and unreliable.
The goal, then, is robustness. We want models that produce stable forecasts across different samples and different slight variations in their structure. This stability is what gives a central bank governor the confidence to act on its output.
Absolutely. And once we have that robust, stable forecast, the way we interpret it also changes drastically. It's no longer just about superficial model fit.
Right.
The interpretation moves into a much richer, more contextualized space. Forecasting results have to be grounded in both strong economic theory, it has to make sense how people and markets behave, and verifiable statistical evidence. So analysts shift their focus away from purely statistical measures like R-squared. They prioritize 3 other factors. First, the direction of effects. Does the policy move the economy up or down, and is that sign consistent with theory? Second, the magnitude and uncertainty. How large is the effect, and what's the range of possible outcomes? And critically, predictive relevance. Does this result genuinely help us anticipate the future, or is it just describing the past perfectly? This emphasis on predictive relevance over fit alone is the hallmark of sophisticated forecasting.
So let's tie this all back to the initial mission. What does all this deep mathematical complexity actually translate into for the people making decisions in the Treasury Department or a central bank?
Advanced regression directly supports the highest level of economic policy design by providing the operational detail they need for effective intervention.
Okay, how so?
First, these forecasts enable countercyclical policy design. By accurately modeling persistence and incorporating indicators for regime shifts, policymakers can time their interventions. Whether that's raising rates to cool inflation or deploying stimulus, they can do it to smooth the business cycle effectively. If you have an 80% probabilistic forecast for a recession, you can intervene before it gains momentum, making the intervention smaller and more effective.
And the second way?
Second, it supports comprehensive risk-based economic planning. Policymakers are not given a single deterministic number. They're given a full distribution of risk and uncertainty.
So they don't just see a line that says GDP will grow by 2.5%. How is that translated for them in practical terms?
Policymakers rely heavily on two specific outputs that summarize this complexity. First, probabilistic forecasts powered by those logit and probit models we talked about. A central bank might state in its policy minutes, "Our model indicates a 15% chance of a severe contraction over the next 2 years." That percentage is then used to justify hedging strategies, contingency planning, or even triggering extraordinary measures like QE to mitigate that specific risk.
Even if the main forecast is still positive.
Exactly. And second, and maybe most valuable, are scenario-based regression outputs. This is the critical counterfactual analysis. It answers the question, if X happens, what happens to Y? A corporate CFO isn't interested in the average forecast. They want to know a specific scenario. If the Fed raises interest rates by 50 basis points, what is the impact on our borrowing costs and projected unemployment over the next 18 months, assuming our key commodity price stabilizes? This structure is powered entirely by the sophisticated causal structures built into advanced regression, allowing for a detailed comparison of different policy options. However, the ultimate takeaway cannot be pure technological triumphalism. We have to acknowledge that even these highly advanced models have significant weaknesses and limitations. Complexity does not equal infallibility. The source material is very clear about this. These models rely on strong, often rigid assumptions. If those assumptions about causality or functional form or how errors are distributed are violated in the chaotic real world, the forecast just collapses. And moreover, we're back to the data problem. They require extremely high-quality data. Garbage in, garbage out. If we rely on poor measurements, the sophisticated model just produces sophisticated errors.
And the deadliest threat you alluded to earlier is when the underlying rules of the economic game change, rendering all our historical data basically useless.
Yes, the structural threat. Structural breaks. If the underlying rules of the economy fundamentally change, like the massive shift in labor participation during the 2020 pandemic, or the sudden shift to remote work, the relationships we derive from past data, the coefficients we calculated, they instantly become irrelevant. These advanced models assume that relationships from the past will generally hold in the future. If that assumption is broken, forecast accuracy degrades dramatically and often catastrophically quickly. And finally, the very complexity we celebrated, the hundreds of parameters, the multiple fixed effects, the choice of nonlinear forms, it introduces its own risk, the increased risk of misspecification. It's much easier to build a model incorrectly when you have 10 different technical choices. How long a lag, which instrument, which fixed effects. Building the statistical house wrong can be just as damaging as using bad data or facing a structural break.
That is a crucial counterpoint to leave with. We've seen how advanced regression is absolutely necessary to grapple with the messy reality of economics, incorporating persistence, nonlinearity, discrete events, and inherent bias. It fundamentally shifts forecasting from simple historical trend fitting to a sophisticated risk-based policy scenario planning tool.
It does.
These tools give us incredible insight into why the economy behaves the way it does, but we are still ultimately operating within the confines of our assumptions and the quality of the data we can measure. The high confidence they provide is powerful, but that confidence is inherently conditional.
And that leads us to our final thought for you, the learner, to explore. If structural breaks constantly threaten accuracy, requiring us to constantly rebuild our models, and if the increased complexity heightens the risk of misspecification, how much confidence should policymakers truly place in even the most advanced probabilistic forecasts when designing interventionist economic policy that affects the livelihoods of millions?
Food for thought indeed. That's all the time we have for this deep dive. Thank you for sharing your sources with us. We'll see you next time. Welcome back to the deep dive. You know that feeling, right? You're trying to figure out if the economy is actually slowing down or if the headlines are just, screaming for clicks.
It's everywhere.
Yeah, you see one article citing a GDP number, another one's all about inflation, a third is referencing unemployment.
And they're all using slightly different data or different time periods.
Exactly. The whole landscape is just completely fragmented. But what if you could cut through all that noise and get right to the exact verified source, the actual foundation that every serious economist, every policymaker, every big forecaster is building their analysis on?
There is one place for that.
There is. And today we are taking a deep dive into it. The Federal Reserve Economic Database, which everyone just calls by its acronym, FRED. FRED.
Yeah.
We've been completely immersed in institutional guides, academic papers, just really digging into Friends' architecture, its data standards, all the special features. And our mission for you today is pretty simple. We want to take FRE from this vague concept you might have heard on the news
Right.
and turn it into a powerful tool you actually understand and can use. We want you to walk away from this not just knowing what it is, but why it's the indispensable bedrock of global economic thought.
And that word bedrock is so crucial because FRD, which is just meticulously maintained by the Federal Reserve Bank of St. Louis, it serves this vital stabilizing function.
A stabilizing function? How so?
Well, it's a huge online library for what we call economic time series data. And its purpose is incredibly focused. It's there to support serious research, to provide the raw material for forecasting, to underpin policy analysis at the highest levels.
And for teaching, right.
And it's a fundamental resource for teaching economics globally.
Right.
Think of it as the ultimate curator. It's not just, collecting numbers. It's standardizing all these different streams of data from hundreds of sources all over the world and forcing them to speak the same statistical language. So if you really want to engage with what the consensus view of the economy is, you have to look past the commentators.
Yeah, past the headlines.
You have to understand the precise, standardized data that creates that consensus. And all of that data, it's centralized and vetted by FRXit.
Okay, so let's unpack that. I mean, when we say it's the essential tool for global economic analysis, why specifically the Federal Reserve Bank of St. Louis? It seems a bit random.
It's not a coincidence, actually. It really connects to a historic mission of the St. Louis Fed. For decades, they've had this specialized focus on economic research and data management.
Oh.
They saw this growing problem, this fragmentation of all the official statistics, and they realized that creating a centralized standard repository was just essential for efficiency, for transparency.
Both inside the Fed system and for everyone else.
And for everyone else globally.
Yeah. And a huge part of its dominance, and we really can't stress this enough, is that it's accessible. This isn't some, proprietary service locked behind a 5- or 6-figure subscription.
Exactly. It's completely free. It's publicly accessible. It basically functions as a global public good.
Which is huge.
It is. This accessibility guarantees that everyone gets the same high-quality, curated data. It's a democratization of knowledge.
So you're saying an undergraduate student working on a class project?
Yes. That student running a simple analysis on inflation is pulling the identical, vetted, standardized data series that the chairman of the Federal Reserve is reviewing before a policy meeting.
That's incredible. It creates a level playing field.
It does. It prevents that fragmentation, and it ensures that the entire economic conversation is, at its core, grounded in the same set of facts.
The scale, though, the sheer scale is almost unbelievable. How do they stop that much data from so many different places from becoming this unmanageable mess? Or worse, getting corrupted by conflicting methods?
And that gets right to the core of its reliability, is what we call the source integration strategy.
Okay.
What's really fascinating here is that the St. Louis Fed, they don't generate most of this raw data themselves.
Oh, I didn't realize that.
No, their value is entirely in the curatorial process. Centralizing, standardizing, and just providing access to official statistics produced by the world's most trusted agencies. They're a definitive repository, not a producer.
Got it.
And if you look at their strategy, it's this systematic effort to just gather the primary official numbers. So domestically in the U.S., they pull from what you could call the big 3 statistical agencies.
Okay, who are they?
First, you've got the U.S. Bureau of Economic Analysis, the BEA. That's the source for all our national income accounts, GDP, consumer spending metrics, all that big picture stuff.
Right.
Then there's the U.S. Bureau of Labor Statistics, the BLS. Absolutely essential for employment, unemployment, and of course, inflation figures like the CPI.
Okay, BEA and BLS.
And then the U.S. Census Bureau. They provide the critical demographic data, housing statistics, industry figures.
And those 3 alone produce just a staggering amount of information. But you mentioned its global reach, too. How do they keep that same rigorous standard when the data is coming from other countries?
That's where the strategy really shows its depth. They reach far beyond just U.S. data. To really work as a global resource, they have to integrate critical inputs from organizations like the International Monetary Fund, the IMF.
Okay, and what does the IMF provide?
They provide standardized financial statistics, balance of payments data for different countries. Then they use the World Bank, which offers development indicators, global macro stats, and also the OECD, the Organization for Economic Cooperation and Development.
Right. They specialize in comparing metrics across developed countries.
Exactly. And this exhaustive aggregation strategy, that is the fundamental reason why users trust the data on F4D. It's not based on some proprietary model. It's not secondary analysis. It's definitely not that alternative data you hear about. It is a one-stop shop for primary, vetted, official source data.
But I have to ask, is the standardization really perfect? I mean, when you're merging data from the IMF and the U.S. Census Bureau, aren't there known, trade-offs or even political issues in how that data gets consolidated?
That's a very sharp question.
Because, for example, the U.S. definition of unemployment might be subtly different from how the IMF standardizes it across, say, emerging markets.
You're right. And it speaks to the caution you need when you're doing that kind of comparative analysis. No, the standardization isn't magically perfect. The FRD team works incredibly hard to reconcile these differences, apply common units where they can. But the user is always required to read the notes. The documentation for each series is right there. If you're comparing U.S. GDP growth from the BEA to, say, Eurozone growth from the OECD, you have to acknowledge those potential methodological differences.
So the transparency is key.
Transparency is everything. The trade-off EFRI makes is this. They provide the best available, most reliable primary source data, even if perfect harmonization across 100 countries isn't always possible. But by clearly identifying the source, BLS, IMF, whatever, right there next to the data series, they give you the transparency you need to do your own homework on the methodology.
And that's what keeps it credible.
That's what maintains its credibility as the definitive source.
Okay, so now we can really appreciate the scale. When you say FRE has hundreds of thousands of economic time series, what does that actually look like in practice? It sounds overwhelming.
It is massive. And to put that into perspective, the sheer breadth of it often exceeds what you'd find on even the most expensive professional financial data terminals.
Really? Why is that?
Because EFRI aggregates so much government data, which, often isn't a priority for private vendors. And while its roots are obviously in the U.S. Federal Reserve System, its geographical coverage is just vast.
So it's not just U.S. data?
No, not at all.
Yeah.
It meticulously covers the U.S. economy, that's its main focus, but it also provides crucial data for tons of international economies. And that's what allows researchers to do really robust comparative analysis.
So you could, for example, look at how U.S. interest rate policy affects, the Brazilian exchange rate.
That's a perfect example. You need both sets of data standardized side by side, and FRD provides that. It lets you map out those modern global economic interdependencies.
To manage all of this staggering volume, there must be a clean structure.
Yeah.
How is it all organized? What are the main categories?
Right. To help users navigate, it's all organized into 5 main data categories. They act as the basic framework.
Okay, what's the first one?
First, you have macroeconomic indicators. This is the big picture stuff, the aggregate information that tells you about the overall health and growth of an economy.
Like national output consumption.
Exactly. National output, consumption, savings rates. It's where economists start when they're gauging growth in business cycles.
Okay, second category.
Second, you've got financial market data. This is crucial for anyone in investing or corporate finance. It gives you insight into how money is priced and how it's moving through capital markets.
So stock indexes, bond spreads, that kind of thing.
All of it. Equity indexes, volatility measures, corporate bond spreads, credit market indicators, you name it.
What's third?
Third is monetary and banking statistics. This is the Fed's home turf. This category is critical for understanding central bank policy and the mechanics of the financial system itself.
Bank reserves, money supply.
Bank reserves, the size of the monetary base, M1 and M2 money supplies, and really detailed stats on credit expansion and contraction.
All right, that's 3. Number 4.
Fourth, we have labor market indicators. So essential metrics on employment, wages, and the overall participation of the population in the workforce.
These are often seen as lagging indicators, right?
They often are, but they're absolutely indispensable for gauging economic strength and, frankly, social well-being.
And the last one.
And finally, number 5 is international economic data, which, like we said, lets you do those cross-country comparisons. This is everything from foreign trade balances and exchange rates to global commodity prices and foreign direct investment. It ensures the analysis has that necessary global perspective.
I think giving some concrete examples is the best way to move this from just abstract categories to, real-world applications. So let's dive into some specific data types.
Absolutely. Let's start with the big one, national income data. When you hear people citing GDP, gross domestic product,
Right.
they are pulling that from FRI, which gets it from the BEA. But what's really vital here is that FRI often gives you two parallel series, nominal GDP and real GDP.
And why is having both of those instantly available so crucial?
Because nominal GDP measures output using current prices. Real GDP uses constant prices from a base year.
Okay, so
So if nominal GDP grows by, say, 5%, but inflation was 3%, the real growth was actually only 2%.
so you just strip out the inflation.
You have to. Economists analyzing the actual health of the economy must use the real inflation-adjusted series to avoid being fooled by price changes. And FRD makes accessing both super easy. You also find things here like the PCE index, personal consumption expenditures.
Which the Fed famously prefers over the CPI for inflation targeting.
Precise.
Okay, let's move on to price and inflation itself. This is probably the most talked about topic right now. We hear CPI and PPI thrown around all the time. What's the difference a listener should know between, say, the CPI and the broader GDP deflator?
That is a perfect point of nuance. The CPI, the Consumer Price Index, which comes from the BLS, tracks price changes for a fixed basket of goods and services that urban consumers buy.
A fixed basket.
Right, and its main limitation is something called substitution bias. So if the price of beef skyrockets, you might switch to chicken, right?
Sure.
But the CPI basket doesn't immediately reflect that switch. In contrast, the GDP deflator from the BEA is a much broader measure. It includes all goods and services produced domestically.
Including things consumers don't buy, like capital goods.
Right, and government purchases. And crucially, it excludes imports, which the CPI includes.
So a spike in oil prices would show up differently.
Exactly. If oil prices rise, the CPI reflects that immediately through gas prices. But the GDP deflator will only show the change in the domestic component of that oil production. Understanding these differences is mandatory for good analysis, and FRI lets you pull up CPI, PPI, and the deflator all instantly.
Okay, shifting gears to monetary and financial data. This is where you see the central bank policy levers. FRD gives us historical data on interest rates, but let's talk about that really technical but essential feature we hear about, the yield curve data.
Yes, specifically the spread between the 10-year Treasury yield and the 2-year Treasury yield.
The 10s-2s spread.
The 10s-2 spread, yeah. It's a widely followed predictor of economic health, and FRD provides this spread as a ready-to-use time series.
And why does everyone watch it so closely?
It's simple, really. When that spread becomes negative, when short-term rates are actually higher than long-term rates.
An inverted yield curve.
An inverted yield curve. It has historically preceded nearly every single U.S. recession by about 12 to 18 months.
So FRDs isn't just giving you the raw interest rates, it's providing the pre-calculated analysis tool, the spread, that forecasters are using to signal recession risk.
Exactly. It's providing the analytical inputs. Things like daily data on the Fed funds rate, the detailed composition of M1 and M2 money supply, breakdowns of commercial bank balance sheets, all crucial for monitoring how monetary policy actually gets transmitted into the real economy.
Okay, next. Labor market figures. The unemployment rate is the big headline number, but if you go deep on FRE, you get a much more granular picture. What are the key distinctions a savvy user would look at?
A savvy user would immediately look beyond the headline unemployment rate, which is technically designated as U3.
U3.
They would dive into the alternative measures, especially U6. U6 is the total unemployed, plus all persons marginally attached to the labor force and those employed part-time for economic reasons. Basically underemployment.
So it captures people who want a full-time job but can only find part-time work.
Precisely. The U3 rate might be really low, suggesting a healthy labor market. But if the U6 rate stays stubbornly high, it signals significant labor market slack. People who have given up looking, but would come back if things got better. FRE's detailed categories allow for that necessary deep dive into the health of the workforce, not just joblessness.
And finally, let's touch on housing and real estate. Housing starts are important, but when we talk about housing prices, you always hear conflicting reports.
That's because there are competing methodologies for tracking house prices, and FRA hosts the time series for the most important ones. The Case-Shiller Home Price Index is famous because it tracks repeat sales, which minimizes the impact of, say, changing house sizes or quality.
Okay.
But FRAD also hosts the FHA House Price Index, which specifically uses mortgages that are purchased or guaranteed by Fannie Mae or Freddie Mac.
And the differences there are significant.
Very significant. The FHFA Index excludes jumbo loans and cash sales. Case-Shiller includes them. So you get different perspectives on the market. By providing both, side by side, FRD lets you analyze the trends of the entire market and also the trends specifically within the federally backed mortgage sector. And this depth across every single sector is why it's the definitive map of the economy.
So we've established the what and the where of the data. Now we need to focus on the how, the structure of the data and its inherent limitations.
Exactly. The information is organized specifically as time series, meaning each data point is tracked over a set period. And this organization is the core design choice that makes FRD so ideal for economic modeling, for forecasting, and for rigorous historical analysis.
The utility of that is really maximized by the different frequencies available, right?
It is. Depending on what you're studying, you can pull data annually, quarterly, monthly, weekly, or even daily. For instance, the Treasury yield curve data we talked about is tracked daily. You need that to capture rapid market reactions.
Whereas something like GDP is inherently quarterly.
Right, it's collected via these massive comprehensive surveys. You can't do it daily.
So why does that frequency matter so much to, say, a policy analyst?
Well, if you're analyzing how the stock market reacted to a specific speech by the Fed chair, you need daily data.
Sure.
If you're studying broader inflationary pressures from consumer behavior, monthly data like the CPI is essential. But if you're trying to understand long-term demographic shifts affecting labor participation, annual data is usually enough. Pulling the data at the right frequency is just essential for good model design.
And what really elevates FRAD beyond some of the simpler data tools is the support for these incredibly long historical spans, especially for U.S. data.
This isn't just a convenience. It's absolutely crucial for any kind of sophisticated analysis. It allows us to perform proper trend analysis. When you have, say, 70 or 100 years of data on something like inflation, you can clearly distinguish between short-term noise, a seasonal spike, and a long-term structural shift.
Like the changes in inflation expectations after the 1970s.
Exactly, the Great Inflation period. Without that historical depth, analysts can easily mistake a temporary fluctuation for a fundamental trend.
And those long spans are also the bread and butter of business cycle analysis.
Absolutely. To figure out where we are in a cycle, is an expansion peaking? Is a contraction bottoming out? You have to compare current movements to past cycles.
So you can compare today to 2008 or the early 80s?
Exactly. FRD lets analysts look at the Great Recession, the Volcker recession of the early 80s, even earlier post-war cycles. By comparing how different variables, consumption, industrial production, housing starts, how they all co-moved during those historical periods, analysts can build empirical models that can help forecast the next turning point. That depth is non-negotiable for serious macro work.
Okay, since this whole deep dive is about being well-informed, about getting to that expert-level understanding, we have to spend some serious time on the caveats.
Oh, absolutely.
You can't just pull a number from FRD and assume you know what it means. Using this tool requires a mandatory understanding of the fine print.
It absolutely does. And the first hurdle is just fully grasping the definitions of the series you're pulling. Take something as simple as money supply. The definitions of M1 and M2 have changed significantly over time.
Because of changes in banking practices.
Right, especially in the last few decades.
Yeah.
If you pull M1 data from 1975 and compare it directly to M1 from 2023 without checking the FRAD notes on the definition change,
your analysis is going to be flawed.
Fatally flawed. The details here are the difference between insightful analysis and just amateur error.
And similarly, the units of measurement are critical. Is the data in millions of dollars or billions? Is it a seasonally adjusted annual rate or quarter-over-quarter percentage change?
Yes, and if you're trying to compare two different series, say the dollar level of durable goods orders to a percentage index of consumer confidence, you have to make sure the units are correctly reconciled or transformed.
And critically, we have to talk about that data transformation that's in almost every major series, seasonal adjustments.
We do. Listeners need to understand that the raw data from the BLS or census is, well, raw. And nearly all economic variables have predictable spikes or dips tied to the time of year.
Like construction. Housing starts naturally plummet in January in cold climates.
Right, because of the weather. So the adjustment process tries to filter out that predictable rhythm of the calendar.
But how reliable is that filtering process, especially when we hit a huge economic shock like a pandemic or a massive hurricane?
That is exactly the nuance a professional acre user has to grasp. The seasonal adjustment process is complex. It uses sophisticated statistical techniques.
Some kind of algorithm.
Right, something called X13 ARIMA seats, which is basically a heavy-duty filter that's based on historical patterns. But it relies entirely on the assumption that past seasonality is a good predictor of future seasonality.
And when something like 2020 happens, that assumption goes out the window.
Completely. When you get those massive, unprecedented swings in hiring and spending, the seasonal adjustment factors can actually introduce more distortion than they remove.
How so?
A sudden, massive, non-seasonal change gets misinterpreted as a seasonal pattern. It can lead to over- or underestimation in the months that follow. Fred always tells you which version you're looking at, and for sophisticated analysis, you sometimes want the raw, unadjusted data, just to see those structural breaks clearly. That understanding of how the data was cleaned is non-negotiable.
We also mentioned a limitation tied to the global data, while the U.S. data goes back decades.
That's not always true globally. Correct. While FRD aggregates the best available international data, global data standardization is a much newer phenomenon.
So the time spans are shorter.
Exactly. The historical window for a really robust apples-to-apples comparison of, say, GDP growth across 50 different economies might only start in the early 90s or even the 2000s, not the post-war era. You just have to accept that limitation.
This brings us to the biggest reliability question of all. What happens when the data changes? We've all seen those headlines about GDP numbers being revised weeks or months after the first release.
Yes. The reality is that almost all major economic indicators, GDP, inflation, employment, they all undergo routine and sometimes dramatic data revisions.
So the first number that comes out is just a preliminary estimate.
It is. It's based on limited survey data, estimates, sometimes incomplete reports. Later, as more comprehensive information comes in tax receipts, full corporate filings, those numbers are revised.
And the problem this creates isn't just academic, it's profound.
It is. Data revisions can fundamentally change how we interpret historical events. Imagine in 2008, a preliminary GDP report showed a shallow recession.
Okay.
Policymakers, based on that data, might have implemented some modest stimulus measures. But if that number was later revised to show the recession was actually deep and protracted,
It changes everything. It fundamentally alters our perception of whether the policy decisions made at the time were adequate.
because the fact is, policymakers made decisions on incomplete information. The revised data, the definitive history, it didn't exist yet.
Exactly. This requires users to not just be aware that revisions happen, but to actively manage that fact. If you're assessing past policy, you can't use the final revised numbers from 2023 to judge decisions made back in 2008.
And this leads us directly into why FRED's specialized features for forecasting are so essential, because they specifically tackle this revision problem.
Okay, so if the data and the structure are the engine, then these specialized tools for forecasting are the transmission. Why do professional forecasters at investment banks, central banks, universities, why do they live and breathe FRED?
Because the entire database is engineered to support what they do, which really boils down to three core tasks. First, they need to identify leading and lagging indicators.
Okay, what does that mean?
Forecasting is all about pattern recognition. You need to know which data series tends to move before the general economy turns, those are leading indicators, and which move after the turn, the lagging ones.
Like building permits are a leading indicator.
A strong leading indicator, because construction comes before the economic activity, and the unemployment rate is notoriously lagging. FRED's structure makes spotting these correlations possible.
And the second task?
Second, forecasters have to be able to build and test forecasting models. You have to take these variables, plug them into an econometric model, whether it's a simple regression or something complex, and then test how accurately your model would have predicted the past.
And FRED's compatibility with statistical software makes that easier.
It makes it seamless. It provides clean, ready-to-import data so you're not spending all your time cleaning it up.
And the third core task?
They use FRED to monitor current economic conditions with extremely high frequency. In real time, they're tracking things like consumer confidence surveys, purchasing manager indices, high-frequency financial market data.
This looks like a dashboard.
It's a customizable dashboard that gives them this constantly updated view of the economy's trajectory so they can spot any deviations from their forecast right away.
This all translates into some very common forecasting applications then.
It does. Primarily, professional teams rely on FRD for GDP growth forecasting, trying to predict the rate of expansion or contraction. They use it heavily for inflation forecasting, anticipating whether price pressures are building or easing.
which obviously informs what the central bank is going to do.
Exactly. And that leads to the highest stakes questions: interest rate and recession analysis. When will the Fed hike or cut? When will the economy officially tip into recession? These predictions rely entirely on comparing current data to decades of historical precedent, all housed and standardized in FR rate.
This brings us back to that revision problem we were just talking about. How does FR resolve it?
It resolves it using what I think is one of its most advanced and necessary features:
Oh.
the provision of real-time data, which economists often call vintage data sets.
Okay, let's clarify this because this concept is the real deep dive insight here. Vintage data isn't the number we use today. It's the number they used yesterday.
That's a great way to put it. FRED archives not only the final revised historical data, the official number we accept today, but also these vintage data sets. A vintage data set is essentially a time-stamped snapshot of the economic data as it was known on a specific release date in the past.
Can you give an example?
Sure. If the initial estimate of Q3 2020 GDP released on October 29, 2020 was, say, 33.1%, but that number was revised a year later to 33.4%.
FRC stores both.
FRI stores both.
Yeah.
The initial 33.1% as the vintage and the final 33.4% as the current series.
And the why this matters is all about academic rigor and professional accountability, right? You can't grade a historical prediction using future knowledge.
Exactly. Real-time data is critical for evaluating forecast performance. If an economist in 2018 predicted inflation would hit 2.5% based on the preliminary numbers available at the time, you have to judge their prediction against those numbers.
Not the number that came out 2 years later.
Right. Using the final revised number would unfairly penalize the forecaster for data they couldn't possibly have known. Vintage data ensures an honest evaluation.
And you also mentioned it helps with understanding revision bias. That sounds like a meta-analysis of the data itself.
It is. Economists use vintage data to study whether major data series are systematically revised in one direction. For example, some analysts have found evidence that initial estimates of GDP growth often tend to be slightly lower than the final revised numbers over time.
So if a forecaster knows that, they can adjust for it.
Exactly. If you can identify that predictable bias, that the first numbers are always a bit too modest, you can build that predictable error into your models and produce a better forecast. This is the gold standard for robust economic evaluation.
So FRD isn't just this passive library of data, it's an analytical environment, which brings us to its built-in analytical and visualization tools. You don't have to be a coding wizard to start seeing patterns.
That's right. The interface is really designed for instant analysis. The built-in tools let you quickly graph time series right in your browser, easily compare multiple variables on the same chart, and, importantly, transform data instantly without downloading a thing.
Let's talk about that transformation piece. Why would a user click a button to take the logarithm of a time series or calculate the difference?
Transformation is fundamental to econometrics. Economists often use logarithms to model the percentage change in a variable. It helps smooth out exponential growth and makes the data easier to use in linear models.
So if you're plotting something like the national debt, which grows exponentially,
Plotting the log value helps you see the rate of acceleration, not just the ballooning absolute size.
and taking the difference.
Taking the difference or calculating the year-over-year change transforms a level series, like the total number of unemployed people, into a change series. How many more or fewer people are unemployed this month? Economists often prefer to analyze changes because it strips out some statistical noise.
And these transformations and visualizations, they immediately support high-level analysis right in the browser for things like trend identification and cycle detection.
The visual tools let you instantly spot the peaks and troughs in the business cycle, or see if a variable is accelerating or decelerating.
And for the advanced user,
They support structural break analysis. The visualization tools help you spot points in time where the fundamental relationship between economic variables suddenly shifted.
maybe because of a financial crisis or a big regulatory change.
Exactly. And those breaks fundamentally alter the predictive power of a model. FRD's graphing tools make those break points clear to the eye, signaling where the analysis needs to be segmented.
So if we connect all this detail back to the bigger picture, FRD's advantages really boil down to three main pillars, right?
I think that's a great way to put it. 3 pillars that ensure its status as the definitive resource. First, its core strength is still that high-quality, curated data.
From official sources only.
Strictly. By drawing only from the BEA, BLS, IMF, and so on, the integrity is just consistently maintained.
Yeah.
You are getting the most vetted data available anywhere.
Pillar number 2.
Second, The broad coverage across economic sectors is truly unmatched. You can access deep dive details on really niche areas like regional bank liquidity, right alongside the big macro aggregates. This breadth allows for holistic analysis without having to piece together data from fragmented sources.
And the third pillar.
And third, it marries that authority and breadth with a highly user-friendly interface that is specifically designed to be compatible with all statistical and econometric software.
So it's easy to get the data out of FRD and into a specialized program.
It's seamless. And that is a massive time saver for researchers who would otherwise spend days or weeks just cleaning and formatting data.
Let's shift the focus now to the learner, our core listener. How is FRD used in education? Because it really is the academic cornerstone of economic instruction worldwide.
Its adoption is pervasive. It's used in every level of university economics undergrad courses, macro seminars, specialized programs in forecasting and econometrics. It gives students real-world, high-stakes data to test the theoretical models they learn in class.
So you learn about the Phillips curve.
And then you immediately pull 60 years of free data on unemployment and inflation to see if that relationship actually holds up empirically.
That practical application moves the learning from just a theory to an applied skill.
Absolutely. And the key benefit for academics and students is that Freed actively supports reproducible research and transparency.
Right. If a paper is published, other people need to be able to verify the results.
They do. And if the researcher just cites the FRE series ID codes, anyone in the world can go to the database, pull that exact vintage of data, and reproduce the analysis. That ability to verify findings is just non-negotiable for academic progress.
So if we bring this all back home to our listener, what does this all mean for you, the learner, the curious individual?
It means you have the same level of informational access as Janet Yellen, as Jamie Dimon, as any Nobel-winning economist.
That's a powerful statement.
It's true. You have free, immediate access to the exact vetted data sources that inform global policy and major financial decisions every single day.
It's an equalizer. You're operating on the same level playing field of knowledge. So whether you want to model recession probabilities with the yield curve or just track your local housing market, FRAD gives you the definitive data to do it responsibly.
And with professional rigor. It allows you to move beyond just reading the headlines and the opinions of others,
Right.
and instead start interpreting the underlying numbers and patterns for yourself. And that ability to derive your own informed conclusions is the greatest power FRAD offers.
We have covered a tremendous amount of ground today, from the philosophical importance of centralized data all the way to the specific mechanics of transforming a time series. Our deep dive absolutely confirms the indispensable role of FRD as the comprehensive, definitive source for economic data.
And it's all driven by that powerful aggregation strategy, pulling from top global institutions like the BEA, the IMF, and of course the Fed itself.
We also spent a lot of time emphasizing that using FR correctly means acknowledging its nuances, the definitions, the seasonal adjustments, and most importantly, the reality of data revision.
Yes, and we highlighted the importance of those vintage or real-time data sets which store the data as it was known when policymakers were actually in the hot seat making decisions.
So let's end with a provocative thought on that.
Given that IFRIT allows us to track how historical numbers change over time through these vintage archives, consider the profound implications for decision-making. If we know that preliminary economic estimates are systematically revised, sometimes years later, to fundamentally alter our perception of past events,
Then how much faith should current policymakers put into the preliminary data they're receiving today? That's a powerful question. I mean, if the GDP number that justified a massive interest rate hike today is later revised down, does that fundamentally change our understanding of whether that policy action was warranted at the time?
it suggests we are always, in effect, driving the economic car while looking through a slightly fogged rearview mirror.
It really forces you to ask, is current economic analysis truly objective, or is it just the best possible educated guess based on what will always be incomplete and provisional data?
And that is something for you to mull over as you begin exploring the incredible wealth and complexity of information that FRE has to offer.
A deep thought to end on. Thank you for diving deep with us. We'll see you next time. Okay, let's unpack this. Think about the economic stories dominating the headlines right now. You've probably seen the cycle. A state passes a landmark law, maybe a major tax reform for corporations, perhaps a significant increase in the federal debt ceiling, or even a local effort to boost vocational training. And then, The numbers start changing, employment goes up, or regional investment plummets. The politician who pushed the law claims immediate success, or their opponent points to the downturn as proof of failure. But here is the fundamental problem facing every economist, every serious policymaker, and frankly, every person trying to make sense of the news. How do we prove that this specific policy or this specific event actually caused the resulting change? Because we live in a constantly shifting environment. Distinguishing correlation things happening at the same time from true causation when dozens of macroeconomic variables are shifting simultaneously it's incredibly difficult. We need a rigorous mathematical way to filter out the noise of general trends. We need a shortcut to being well informed on measuring real-world policy impact when a true lab experiment is impossible.
And that challenge, which is the core problem of causal inference in applied economics, is precisely why we are dedicating this deep dive to difference in differences, or DID, analysis. This method isn't just some academic curiosity. It is the absolute workhorse of modern applied economics and public policy research, specifically designed to tackle that causal inference problem head-on in messy, real-world situations. DID is formally categorized as a quasi-experimental econometric method.
Quasi-experimental. That tag is really important, isn't it?
It's critically important as it immediately tells you what we are trying to do, mimic the statistical power and rigor of a randomized controlled trial, an RCT, which is the gold standard of scientific proof.
Even though we can't actually do one.
Even though we cannot ethically or practically randomize an entire state or country to receive a policy change.
Right. You can't put half of California into a control group and half into a treatment group for a new infrastructure bill. That just doesn't work.
Precisely. So DID gives us the best available framework to get around that. Our mission today is to break down exactly how DID transforms simple observation into credible proof. We need to understand how it systematically isolates the true causal effects of an intervention, be it a tax cut, a major institutional reform, or an external economic shock from the underlying trends. By delivering this purified estimate, DID fundamentally improves the reliability of economic forecasts that must follow major policy shifts because it provides the best possible credible estimate of the counterfactual.
So let's start at the beginning by outlining why the most intuitive approach, which we hear constantly in public discourse, simply doesn't cut it. The simple before-after comparison. I mean, if we look at, say, the implementation of a new state-level training program, and 3 months later the number of skilled workers increases, the program's advocates will pound the table and say, look, it worked, it's causation. But that simplicity is a mirage.
That simple analysis suffers from a massive, fatal flaw. It ignores the general background economic reality. Let's stick with that example. If that state's economy was already in a natural national upswing, maybe due to massive common macroeconomic shocks, like, say, the national or global supply chain issues finally resolving themselves and manufacturing booming everywhere.
Then the increase in skilled workers might have happened anyway.
It might have been going to happen regardless of the specific training policy.
So the simple before-after comparison is inherently biased because it assumes that if the policy had not been implemented, the outcome variable, the number of skilled workers, would have remained exactly at its pre-intervention level.
And that's never the case. Never. Not in a dynamic economy. Economies are always trending up or down, always evolving, and always subject to those common shocks. This leads to what economists call omitted variable bias in simple time series analysis.
The omitted variable being that general trend.
The omitted variable is the general trend, the common shift that would have occurred anyway. This is where DD steps in as an essential innovation. D corrects this fundamental problem by introducing a crucial element that absorbs the noise, a control group. This control group has not received the policy, but critically, it is subject to those same general economic trends and common shocks that are affecting the treated area.
So DEED isn't just one comparison across time, it's a disciplined, systematic comparison of two differences, a difference across groups and a difference across time.
Exactly. D systematically organizes its data around two components. First, it measures the changes over time in a treated group, the group that experienced the policy or intervention. Second, it measures the simultaneous changes over time in a control group, a similar, comparable group that did not experience the policy. The control group thus serves as our proxy for the counterfactual general trend.
But what if?
It's a mathematical way of answering the impossible question, what if? Whatever magnitude of change occurred in the control group during that time period gives us the best estimate of what would have happened to the treated group in the total absence of the policy.
And this capability is what shifts Didi from being a historical accounting tool to a powerful forecasting tool.
Yeah.
I mean, if you're trying to forecast the long-term health of a specific industry after a new sector-specific regulation is introduced, you need absolute confidence that the change you observe is due to the regulation, not simply part of a global commodity price fluctuation or a cyclical downturn affecting the entire industry.
That's right. Didi helps isolate the true signal of that specific intervention from the general economic climate.
If we visualize this, the structure becomes much clearer for the listener. Didi requires data organized across two crucial dimensions. First, the groups. You must have data for the treated group and the control group. And second, the time. You must have data for the period before the intervention and the period after the intervention.
You absolutely must have data for all 4 cells of that matrix to perform a valid Didi calculation.
Okay, so with that framework in mind, let's move to the mechanics, the intuitive mathematics behind the double difference itself.
Right. The logic is surprisingly robust and transparent. We can break the calculation down into 3 sequential steps, starting with the treated group. Step 1. Calculate the change in outcomes over time for the treated group. You take the average outcome after the policy and subtract the average outcome before the policy for that group.
And that gives you the total observed change.
The total observed change. This number is a mix of the policy effect and the general trend. Step 2. You calculate the change in outcomes over time for the control group using the exact same 2 periods.
And this is the crucial step.
It is. This calculation, this change in the control group, represents the pure general trend, the magnitude of the common shocks that affected both groups equally. This becomes our counterfactual baseline for the general movement of the economy.
And then the magic happens in step 3.
Exactly. Step 3 is the key idea. You subtract the result from step 2, which is the change of the control group.
Right.
From the result of step 1, the total change in the treated group. What is left over, the remainder, is the estimated causal effect of the policy intervention.
That remainder is the difference in differences.
It is.
Let's run that through the concrete example we touched on earlier, focusing on minimum wage policy and employment, which is historically where Didi really proved its merit. Imagine State A, our treated group, raises its minimum wage on January 1st. State B, a bordering state with a similar...
Exactly. That's step 2, the observed change in the control state. That represents the general economic tailwind, the common trend, the seasonal factors, the national growth.
So if we had only looked at State A, the politician might declare a 0.5% success. But State B's parallel experience shows us that 0.2% of that drop is going to happen regardless of the policy.
Just because of the common economic tide.
So we do the final subtraction.
We'll perform the final subtraction. We take the treated change, the 0.5%, and subtract the control change, the 0.2%.
And the result is 0.3%.
The resulting difference is 0.3%. That remaining 0.3 percentage point drop is the estimated causal effect, the change that is truly attributable to the minimum wage policy. It's the change net of the general economic movement.
That is incredibly powerful. And if unemployment had fallen equally in both states, say, by 0.5% in State A and 0.5% in State B, then the double difference would be 0.
It would be 0.
And we would conclude the policy had no measurable effect on employment because the control group already accounted for all of that general trend.
That's right.
This double comparison is what constructs our counterfactual, what would have happened to State A without the policy.
And this intuitive setup, this breakthrough in establishing causality without randomization, is exactly what catalyzed the widespread adoption of Didi in the 1990s. Particularly following the groundbreaking work by economists David Card and Alan Kruger. They famously used Didi to study the effect of a minimum wage increase in New Jersey, comparing fast food employment there to employment in neighboring Pennsylvania, which did not raise its minimum wage.
And their findings were pretty shocking at the time, right?
They were. They're finding that the wage increase did not cause the expected drop in employment, shocked the field, and cemented Didi as the gold standard for policy evaluation.
That intuitive subtraction using a simple 2x2 table is fantastic for understanding the concept. But as you mentioned, real-world economic data analysis is far more complex. I mean, it uses multiple observations across dozens of firms, states, or individuals, often measured over many time periods. Analysts can't just use simple averages. They need to move to the formal statistical model.
Absolutely. The regression framework is necessary to incorporate the rich structure of the data and crucially, to allow us to statistically control for other variables that might be simultaneously influencing the outcome. The standard DID specification translates that intuitive double subtraction into a linear regression equation. It is the backbone of the analysis. Let's walk through it slowly. The equation is y equals beta 0 plus beta 1 times treated plus beta 2 times post plus beta 3 times the interaction of treated and post plus an error term.
It looks daunting, but every piece of that formula has a specific, understandable role.
It does. Let's start with y. That's the outcome variable. It could be the employment rate, GDP growth, or perhaps a measure of educational attainment for a specific unit, like a state, at a specific time. The u at the end is our error term, capturing all the random, unobserved factors we don't explicitly measure.
Okay, and then we get to the coefficients, beta terms, which tell the true story of the data. Beta 0 is our starting point.
Beta 0 represents the baseline outcome for the control group before the intervention. If state B's unemployment rate before the policy was 5%, beta 0 would be approximately 5%. It sets the overall context. Next we have beta 1, which is associated with the treated term. Treated is just a simple indicator variable. It's 1 if the unit is in the treated group, like state A, and 0 if it is the control group, state B.
So beta 1 is capturing the difference between the two states before anything happens.
Exactly. Beta 1 captures the inherent time-invariant difference between state A and state B before the policy ever occurred.
So if state A, even before the minimum wage hike, always had an unemployment rate 0.5 percentage points lower than state B, beta 1 would be negative 0.5. It accounts for those perpetual baseline differences in levels.
Precisely. It mathematically controls for the fact that state A might be fundamentally wealthier, or have a more educated workforce, or better natural resources than state B, regardless of the policy. Following that is beta 2, which multiplies the post term. Post is the time indicator, set to 1 for all periods after the intervention starts, and 0 before.
And this coefficient, beta 2, captures the general time trend.
Yes, the magnitude of that common national shock or cyclical movement we discussed. It tells you what happened to the outcome variable for everyone, including the control group, just because time passed.
So if the national economy improved so that unemployment would have dropped by 0.2% everywhere, beta 2 absorbs that 0.2% change.
Correct. Beta 0, beta 1, and beta 2 collectively set the entire baseline, the overall starting value, the fixed difference between the groups, and the common evolution over time. This structure is what allows DID to effectively control for a huge class of potentially biasing factors, specifically unobserved time-invariant heterogeneity, which is controlled by beta 1, and common time-varying shocks, controlled by beta 2.
This brings us to the ultimate prize, the reason we ran the regression in the first place, which is the interaction term.
Yes. We center our entire analysis on the coefficient beta 3, which is attached to the interaction term, treated multiplied by post. This term is the only one in the equation that is switched on, it's only equal to 1, for the treated group after the policy has been implemented.
Right, because if the unit is a control group, treated is 0, and the whole thing is 0.
And if the time is pre-intervention, post is 0, and again, the term vanishes.
So its placement is what gives it its power.
This specific placement means that beta 3 must capture the remaining difference, the change that is unique to the treated group after the intervention, net of all the baseline levels and common trends.
So beta 3 is the entire show.
It is the coefficient of interest. Beta 3 is interpreted as the average treatment effect, or AE. It explicitly represents the change in the outcome variable that is attributable only to the intervention, after systematically purging the effects of baseline differences and the general time trends.
And for forecasting, this coefficient is paramount. If you are an economic analyst trying to project how employment will evolve over the next 5 years in State A after the minimum wage hike, you must have a credible, non-biased estimate of beta 3. You take your general long-term growth projections, and you add the beta 3 policy bump to the treated area's forecast. If beta 3 is inaccurate because your control group was poorly chosen, for example, your long-term forecast for State A will be skewed.
Completely skewed. Its accuracy is everything. Which brings us to, well, the most crucial point in DAD analysis. This is the foundation upon which the entire statistical exercise rests, and it's the primary source of all critique, the parallel trends assumption.
You've alluded to it repeatedly. Why is this specific assumption that the trends must be parallel in the absence of treatment so much more important than the other factors the regression controls for?
Because if this assumption is violated, the DAD result, that beta 3, is meaningless. It's biased. The key identifying assumption states that in the absence of treatment, the treated and control groups would have followed parallel trends.
And notice the careful phrasing there. You're talking about trends, the rate of change, not the absolute levels.
That's the critical distinction. We are talking about trends.
Wait, If the regression already includes beta 1 to control for the baseline difference in levels, why do we need to worry about parallel trends at all? Shouldn't the regression just clean that up?
That is an excellent probing question, and it gets right to the heart of the matter. Beta 1 controls for time-invariant differences in levels. Think of it this way. State A might perpetually have 1% higher GDP growth than State B. That's a constant gap. Beta 1 accounts for that. A violation of the parallel trends assumption, however, means that the rate of change for State A was already fundamentally different from State B, and this divergence was happening before the policy was ever passed.
I see.
For instance, State A might have started accelerating its GDP growth 3 years before the policy was announced, while State B was slowing down. That divergence is a difference in trend, not a fixed difference in level.
Ah, so if State A was already naturally pulling away from State B before the policy hit, the Diddy estimator will mistakenly attribute that pre-existing acceleration to the policy itself.
Exactly. The coefficient beta 3 would be capturing both the true policy effect and the natural, non-parallel growth rates that were already diverging. The violation of this assumption fundamentally undermines forecast credibility.
So how do credible analysts prove that the trends were parallel? Or at least that they didn't diverge right before the intervention? You can't observe the counterfactual, so how do you test it?
You can't test it directly, but you can build a strong case for it. This is where practical econometrics comes in, and analysts rely on what are often called placebo tests or falsification tests. If you only have 2 time periods, one before and one after, you can't prove parallel trends definitively. But when you introduce multiple pre-treatment periods, you can run a regression that maps the pre-treatment trends side by side.
So you can actually chart it out visually.
You can. If you see the lines for the treated and control groups tracking closely together in the years leading up to the policy, the assumption is credible. If you see them clearly fanning out or crossing just before the treatment date, you have evidence of a violation, and the DID results are likely biased.
What's a falsification test then?
A common falsification test is to run the DID regression, but pretend the policy happened a year earlier than it actually did. If you find a significant beta 3 effect in that placebo test, it means you are capturing divergence that had already started, proving the parallel trends assumption is violated.
That's a true deep dive insight. It moves the analysis from saying this assumption exists to showing how researchers actually defend their use of the model. Now let's look at robustness. Even when we have confidence in the parallel pre-trends, the real world is messy and statistical controls are necessary. We mentioned fixed effects earlier. Let's expand on how they bolster the credibility of the findings.
Right. Fixed effects are mathematical ways to absorb unwanted variation, strengthening the model's focus on the causal link. We must use them because while we rely on the control group to capture the trend, we know treated and control units have unique, time-invariant differences that are not part of the common trend. Let's start with unit fixed effects. These are essential because State A and State B have inherent perpetual differences. State A might have a perpetually higher baseline growth rate due to its access to the Pacific Ocean or superior higher education infrastructure. These are differences in level that are constant over time.
And we established that beta 1 controls for that, right?
It does, but when we incorporate unit fixed effects into the regression, we effectively achieve the same goal, often more flexibly in a multi-period model. Unit fixed effects mathematically absorb any inherent fixed characteristic unique to each unit.
So it's a more powerful way to do the same job.
In a way, yes. If you include a fixed effect for every state, that fixed effect term absorbs the beta 1 term entirely. It ensures that any difference remaining to be captured by beta 3 is a change over time that is unique to the policy. It is a powerful structural control. Then we have time-fixed effects. These are equally vital. They control for all those common macroeconomic shocks that affect all groups simultaneously.
Like a national recession or a big change from the Fed.
Exactly. If the U.S. Federal Reserve unexpectedly implements a national quantitative easing program, that is a common shock that hits both State A and State B at the same moment.
And we want that shock to be accounted for so we don't mistakenly attribute its effect to the state-level minimum wage policy.
Precisely. The time-fixed effects absorb the beta 2 term. They ensure that all common changes that occur in a specific year, the national shock, are mathematically removed from the calculation before the interaction term is estimated. By combining D with both unit fixed effects and time fixed effects, we isolate beta 3 with much greater confidence, significantly enhancing the reliability of our forecasts.
So this rigorous structure allows economists to separate policy-driven changes, the signal from natural economic evolution, the overwhelming noise.
That's the goal. When policy forecasters look at, say, employment patterns after a major tax change or project growth following new trade policies, they absolutely must rely on DD models bolstered by these fixed effects to isolate the policy signal. Without this isolation, their long-term projections risk being entirely skewed by temporary national factors or baseline differences that the model failed to absorb.
This method is clearly robust, which explains its popularity. Moving to the practical side, where do we see DD analysis shining brightest in government, academia, and private forecasting?
The utility is vast because its core requirement, a non-randomized real-world intervention with a comparable, untreated control group, is the defining feature of almost all major public policy changes. As we discussed, it's foundational in labor economics for evaluating minimum wage policies, assessing the causal effect on employment, hours worked, or local poverty rates.
But it goes way beyond that.
Oh yes, we see it everywhere else too. In public health, DD is essential. For instance, evaluating the impact of a specific public health intervention, like a new smoking regulation rolled out in only certain metropolitan areas.
And you'd use the nearby metro areas that didn't adopt the policy as your control group?
Exactly. In education, researchers use it to evaluate the impact of a new curriculum or funding formula implemented in one region versus a neighboring region. Similarly, it is crucial in healthcare, analyzing what happens when Medicaid eligibility rules change in one set of states but not others.
And crucially, the forecasts derived from these DD models inform the highest levels of policy planning. Governments use these causal estimates of beta 3 to conduct proper cost-benefit analysis. If beta 3 suggests a policy generates significant, measurable economic gain, that justifies the national rollout and the long-term investment.
Absolutely. The advantages that propel DD to the forefront of policy analysis are clear. Firstly, its necessity. It does not require randomization. For major public policy, DD is often the primary tool for establishing causation. Secondly, its simplicity of interpretation. Once the parallel trends assumption is credibly supported, the beta 3 coefficient is immediately interpretable as the causal effect of interest, net of common factors. It is highly transparent.
And that third advantage.
And thirdly, the fact that it effectively controls for all unobserved time-invariant heterogeneity through the structure of the fixed effects is a massive advantage over simpler regression techniques.
It's flexible and robust, handling real-world complexity better than almost any other causal tool. But we established that the simple two-group, two-period model rarely reflects the real complexity of policy rollout. We need to talk about those conceptual extensions.
We do. Policy is rarely a sudden switch for every unit at the same time. Policies are phased in or they are adopted by different unit states, cities, companies at different moments.
Right. So if State A adopts the policy in 2020 and State C adopts it in 2022, and we have 10 other states that never adopt it, the simple 2-by-2 subtraction falls apart. How is that complexity managed?
This requires moving beyond the basic model and incorporating advanced panel data methods.
What's the first step?
The first extension is simple, incorporating multiple time periods rather than just one before and one after. This allows analysts to track the trend over time before the policy and observe the dynamic effect after the policy.
And that lets you run those crucial placebo tests we talked about.
Precisely. But the most challenging and thus most interesting extension is handling staggered treatment adoption. This is when units receive the treatment at different times, sometimes called dynamic deed in tree. For instance, State A gets treated in 2020, State C gets treated in 2021, and State B remains untreated forever.
Okay, so who is the control group for State A in 2020? And who is the control group for State C in 2021? That gets confusing.
It does. In the period immediately after State A's treatment in 2020, its control group includes both states that are never treated, like State B, and states that are yet to be treated, like State C.
Okay.
Then, in 2021, when State C gets treated, its control group consists only of states that are never treated, like State B. Analysts use advanced regression techniques that combine DD principles with time-varying indicators to handle these shifting control groups. However, and this is where the cutting-edge econometric research has focused in the last 5 years, this staggered design introduces a new layer of complexity, bias from heterogeneity of treatment effects.
What does that mean in plain English?
It means that if the minimum wage hike has a massive positive effect in State A, but a small negative effect in State C, and you use State A, which is now already treated, as a comparison point for State C.
The model can produce biased results.
Yes. Modern econometricians have shown that under staggered D, you often end up comparing the newly treated units not just to the never treated units, but also to units that were treated earlier.
And why is comparing a newly treated state to an already treated state problematic?
Because if the treatment effect is heterogeneous, if the policy impact differs between states, the earlier treated state is no longer a pristine representation of the common trend.
Right, it's been contaminated by its own policy effects.
It now carries its own policy-driven changes, which complicates the calculation of the counterfactual. Researchers now rely on specialized estimators, like those developed by Goodman-Bacon or Callaway and Santana, which explicitly calculate the contribution of each pairwise comparison.
So they separate the treated versus never treated from the treated versus later treated comparisons.
Exactly, to rigorously identify and separate these different components of the effect.
That complexity is vital for improving forecasting in complex environments. Without mastering these advanced, multi-period, staggered approaches, any large-scale forecast of a nationwide phased-in reform would be statistically unreliable.
Furthermore, these complex real-world situations sometimes push researchers to look beyond data altogether, or use it in conjunction with other methods. For instance, when a truly credible control group for the parallel trends assumption is difficult to find, say, if a policy affects 48 states, leaving only 2 controls economists might turn to synthetic control methods.
Synthetic control, that sounds like a conceptual cousin of DEED.
It is.
No.
Instead of relying on a single pre-selected control group, the synthetic control method constructs a weighted average of several untreated comparison units to create a synthetic control unit.
So you're building a perfect control group from scratch.
In a sense, you're building one whose pre-treatment trends perfectly match the treated unit. It's essentially a rigorous, data-driven way of maximizing the chances of satisfying the parallel trends assumption, often succeeding, where a simple DD choice of one single control group might fail.
It is clear that DID is a foundational tool, but as we've seen with the challenges of staggered adoption, no statistical method is perfect. To provide a balanced deep dive, we must now focus on the critical limitations and the challenges that even the most skilled analysts face when using DID.
Of course. And the major weaknesses often circle back to that primary assumption. The first and most extreme challenge is the method's sensitivity to violations of the parallel trends assumption. We can't overemphasize this. If the pre-trends were already diverging, the DD result is biased. If you can't credibly defend that the groups were on parallel trajectories before the policy, the entire causal estimate of beta 3 collapses.
The whole thing falls apart.
The whole thing. Secondly, DIND has a structural blind spot regarding unobserved variables. While the fixed effects handle time invariant differences and the common macro shocks, it cannot control for a highly specific type of unobserved event.
And what's that?
Time-varying unobserved shocks that affect only the treated group.
This is a nuanced but crucial distinction. We know that time-fixed effects control for a national interest rate hike because that affects everyone. So what kind of shock doesn't get controlled?
Let's revisit our minimum wage example, State A and State B. A national interest rate hike is a common time-varying shock absorbed perfectly by the time-fixed effects and the beta 2 term. Now imagine State A raises the minimum wage, and 6 months later, a massive, unpredicted regional drought devastates State A's primary agricultural sector. This agricultural sector relies heavily on low-wage labor.
And that drought doesn't hit State B.
Exactly. That drought is a shock that happens over time, and it is unobserved by the DD model because it wasn't an input variable. Crucially, it affects only State A, not State B. This drought will depress employment figures in State A significantly.
And the model will blame the minimum wage.
The DD analysis will then mistakenly attribute the employment drop caused by the drought to the minimum wage increase, biasing the causal estimate of beta 3. Since the control group, State B, wasn't affected by the drought, its trend offers no way to account for this localized shock. The estimated policy effect will be wrong.
That is the essential gap. DD assumes that once you strip away the baseline differences and the national trends, anything left over must be the policy. But that's not true if there's a localized, time-specific event.
Precisely. This is why economists are so focused on the selection of the control group and the careful inclusion of state-specific covariates in the regression to try and capture major local shocks, like local tax changes or significant weather events.
But the risk always remains.
The risk of an unobserved localized shock remains a key weakness. Finally, we must address the risks of bias related to group interaction, specifically spillover effects. DD's validity rests on the assumption that the control group remains a true counterfactual, perfectly independent, save for the common economic weather.
But if the control group is indirectly affected by the treatment, they stop being a true counterfactual. How likely is that in a modern interconnected economy?
Extremely likely, which makes defining clean boundaries incredibly challenging. Consider our State A minimum wage hike. If State A borders State B, and State A's policy causes consumers living in State B to drive across the border to State A to buy cheaper goods.
Or if workers start commuting across the border for higher wages.
Or if labor moves slightly across the border, State B's economy is no longer truly untreated. If the wage hike causes localized inflation or changes in consumer spending that bleed into the control state, the control group's trend will now partially reflect the policy effect.
So the control group's trend is contaminated.
It is. When you perform the double difference, you are subtracting a trend that already contains part of the policy effect. The result: the final beta-3 coefficient will be biased towards zero, underestimating the true causal effect of the policy, because the control group absorbed some of the impact.
That is the ultimate cautionary tale for DID. In essence, the power of DID relies entirely on the quality and independence of the control group and the ability of the analyst to prove that the world they inhabit remains perfectly isolated from the treatment effect, save for those common background shocks. This has been an extensive and detailed breakdown of difference in differences analysis, moving from a simple intuitive subtraction to the rigorous application of panel data models and fixed effects. The final synthesis is clear. Difference in differences is critical because it provides a reliable, mathematically constructed counterfactual. By leveraging the experience of a comparable control group, DID allows us to isolate and define what would have happened to the treated group in the absence of the intervention.
That reliability is why D is a foundational analytical method, enabling us to separate the specific signal of a policy outcome from the overwhelming background noise of the national and global economy. It allows us to move beyond mere correlation and establish causation, leading to smarter policy evaluation, more responsible public spending decisions, and crucially, more accurate economic forecasting in a world defined by complexity and constant change.
And that leads us to our final thought for you to mull over after this deep dive. Given the critical importance of the parallel trends assumption and the increasing necessity of complex extensions like staggered treatment adoption for large-scale analysis in the real world, how challenging is it for economists to identify truly unaffected control groups in a globally interconnected economy, especially when policies like trade, climate regulations, or financial reforms inherently have widespread indirect ripple effects? And perhaps more importantly, how does the quality and availability of granular, hyper-local data determine whether a major policy change can be credibly evaluated and forecasted using these powerful quasi-experimental methods when the risks of localized, time-varying shocks and spillover effects are so high? It's a challenge that defines modern economic research.
Okay, let's unpack this. We are constantly trying to figure out what caused what.
Right. It's not just about what happened, but the why behind it?
Exactly. And in policy, in economics, that is the central question, isn't it? Did that new law actually reduce accidents? Did that tax cut really boost hiring?
In a perfect lab, sure. You could run a perfect experiment, an RCT, a randomized controlled trial. You hold everything still and just change one little thing.
But the real world it refuses to sit still for us. It's messy.
It's messy, it's dynamic, and there are a million things happening at once. The economy's always moving, trends are always shifting, and you just can't, randomly assign a new healthcare policy to half the country just so you can write a nice, clean academic paper.
You can't, and everything is moving all the time. So imagine a state puts in a huge subsidy for clean energy.
Okay.
And you see solar panel installations jump 20%. Fantastic, right? But what if, at the exact same time, the global price of solar cells just happened to drop by 30%?
The causality gets very muddy, very fast.
Instantly. So we need a tool, a way to filter out that noise, that global price drop, and isolate just the effect of the state subsidy.
And that is our mission for this deep dive, to really understand this powerful, essential, and I mean widely used statistical technique that's designed for exactly this kind of problem.
The difference in differences estimator, or DID.
That's the one. And to put it simply, DID is our best numerical measure of the causal effect of a policy or some other event, specifically for those times when a neat randomized experiment is just off the table.
So it's kind of the closest we can get to a real experiment out in the wild, a quasi-experiment.
That's a perfect way to put it. It lets us compare two realities that are running side by side. The goal here, and this is so crucial for anyone evaluating policy, is to calculate how much an outcome changed because of the intervention.
Not just because of other stuff happening at the same time.
Exactly. You want to isolate its specific impact from those general economic trends, like the global price drop, that would have affected everyone anyway. If we can do that, then our evaluations are actually based on evidence, not just, wishful thinking.
Okay, so if DID is a filter, a really sophisticated one, we need to understand what it's filtering out. Conceptually, what's it trying to remove to give us that clean signal?
That's the key. The entire logic is built to solve two massive problems, two biases that would completely ruin any simple comparison. If you don't solve for these, your estimate of the cause is it's wrong.
So what are these two big problems?
Okay. Problem one is what we call permanent differences. Let's imagine we're studying a new traffic enforcement policy in, say, City T, that's our treated city, and we're comparing it to City C, our control.
Makes sense.
Now, City T might just be an inherently safer city. Maybe it has better roads, fewer hills, I don't know, a tougher driver's ed program. These are things that are true regardless of this new policy.
So if you just look at the accident rates after the policy, City T is going to look better. But not because of the new enforcement. It's because of things that were true for years.
Precisely. You're not looking for which city is better. You're looking for which city changed more because of the intervention. So a simple comparison of levels post-policy is contaminated by those permanent structural differences.
And DID has a way to handle that.
It does. It looks at the change within City T over time. That's the first subtraction. It basically uses the city as its own baseline, which nets out those permanent built-in differences.
Okay, so that's problem one, permanent differences. What's the second source of bias?
This is problem two, common time trends. This is that big external factor, the sweeping shift that affects everyone at the same time.
Like our solar panel price drop example.
Exactly like that. Or, with our traffic example, maybe a big nationwide ad campaign about distracted driving launches right when City T starts its new local policy.
So accident rates start dropping everywhere. In City C, they control too.
Right. So if City T just measures its own accident rate before and after, they might see this big drop and, pop the champagne corks, thinking their policy was a huge success.
But that drop might have had nothing to do with their local policy. It could have been the national campaign.
Exactly. If you only look at the treated group, you can't untangle the local effect from the global trend. You have to filter that common trend out.
And that's where the control group comes in.
That's where it becomes essential. DCD measures the change in the control group, City C. Since City C didn't get the local policy, any change it experienced over that same time. Well, that change must be from those common trends, the national campaign, safer cars, whatever it is.
So, okay, let's walk through the steps then. We need a method that removes both things, the fixed baseline difference and that sweeping external trend.
Right, and that's why it's a double subtraction.
Step one, we look at the treated group, City T. We compare their accident rate before the policy to their rate after the policy.
That's the first difference. And remember, that number contains both the real policy effect and the effect of the common time trend. It's a mix.
Okay, so step two, we look at the control group, City C, over the exact same time period, and we measure their change before to after.
And that's the second difference. And because they didn't get the policy, we assume that change is only the result of the common time trends.
And then the final aha moment, the difference in differences. You subtract that second change, the common trend, from the first change, the total change in the treated group.
And what's left over, that's your estimated causal effect. It's really elegant. The control group acts as this dynamic correction. A simple before-after comparison in City T is naive because it ignores those big trends. The control group corrects for that, and that's what makes the result so much more credible.
So the change in the control group is it's our baseline for how the universe was changing during that time, and we're measuring how much the treated group deviated from that baseline.
That is a fantastic way to put it. Whatever is left over after you account for what would have happened anyway, that has to be the effect of the policy.
Now that we've got the intuition, let's look under the hood. Researchers don't just talk about double subtraction in their papers. They use a specific notation, a formula, to capture those four averages we just talked about.
Right. We have to formalize it. And you're right, it all boils down to four key numbers. We use the letter Y with a bar over it, T bar Y, to mean the average outcome. And we index it by group, T for treated and C for control, and by time, pre or post.
Okay, so lay them out for us, the four averages.
First, you need the average outcome for the treated group after the intervention. That's D bar YT post.
In our example, the average accident rate in City T after the new enforcements.
Exactly. Then, same group, but before the intervention. 2 YT pre-all.
And the difference between those two, that's our first subtraction, the total observed change in City T.
Correct. That's the policy effect plus all that other noise. Then you do the same thing for the control group. You need their average outcome after the intervention, $YC post.
And their average outcome before the intervention, $YC pre-all.
And the difference between those two is our estimate of the common trend. It's the change that we assume would have happened to City T anyway, even without the policy. It's our correction factor.
So the big formula just puts it all together.
It does. You take the total change from the treated group, and you subtract out the change from the control group. It looks like this. The DAD is equal to, in parentheses, $YC post night, post minus $YC pre, and then you subtract the second parenthesis, $YC post minus $YC pre.
I love how clean that is.
Yeah.
The nested parentheses really show the logic. You take the gross change in T and you literally strip away the gross change in C.
And what's left is what we're looking for, the estimated treatment effect. That single number is our best guess at the average causal impact of that intervention.
So let's say we do this for our traffic example, and the final DD value is, say, negative 0.5. What does that tell us?
Okay, a negative value there means the policy reduced the outcome. So it reduced accidents, which is good.
Right.
It means that the policy caused an additional half an accident reduction per 1,000 residents on top of whatever trend was already happening. Maybe accidents were already falling by 1 per 1,000 nationally, but in CDT they fell by 1.5. The DD is that extra minus 0.5.
And if we were looking at, I don't know, job creation after a tax break, a positive D of plus 200 would mean?
It would mean the tax break created 200 more jobs than would have been created anyway, just due to general economic growth during that period.
Now you have to add the big caveat here, right?
Always. This interpretation is only valid ceteris paribus, all other things being equal.
Which means we have to assume that nothing else uniquely weird happened to the treated group during that time that didn't also happen to the control group.
Exactly. The math is beautiful, but it's only as good as the assumptions holding it up.
Okay, so that simple four-number calculation is great for intuition, but in the real world, researchers use a more powerful tool, right? They use regression.
Yes, almost always. Especially when you're dealing with, lots of data points over many years. It lets you add in other control variables and just gives you more statistical confidence.
This is where it can get a little dense. How do you translate that clean, simple double subtraction into a regression equation?
It's actually a really clever translation. Instead of averages, we use what are called dummy variables. They're just switches, either a 0 or a 1. They signal whether a data point belongs to the treated group and whether it's from before or after the policy.
And the regression model estimates everything at once.
It does. The equation looks a little intimidating at first, but each part maps directly back to the problems we're trying to solve. It's usually written as y equals beta 0 plus beta 1 times a treated dummy plus beta 2 times a post dummy. And then the really important part, plus beta 3 times the interaction of treated and post, plus an error term.
Okay, let's break down those betas. What's beta 0, the intercept?
Beta 0 is your absolute baseline. It's the average outcome for the control group in the before period. It's where everything starts.
Okay, then beta 1 is attached to that treated dummy variable.
Right. And that coefficient, beta 1, is capturing the permanent difference. It measures that pre-existing gap between the two groups. If City T just always has a 5% higher income than City C, beta 1 absorbs that 5% difference right away.
So just by including that term, you've solved problem 1.
Yeah.
You've accounted for the fact they started in different places.
Exactly. Then you have beta 2, which is attached to the post dummy. That variable is 1 for any observation after the policy date.
So that sounds like it's capturing the common time trend.
It is. Beta 2 captures the overall shift that affects everybody after the policy date. If the whole national economy grew by 2%, beta 2 picks up that 2% for both City T and City C. It solves problem 2.
Okay, so we've handled the two big sources of bias. Now for the magic part, that interaction term. Beta 3 times treated times post.
This is the heart of it. That interaction term is only equal to 1 under one specific condition, when the observation is from the treated group and it's from the post-policy period.
It's a switch that only flips on for that one specific quadrant of our 4-box table.
Precisely. And by doing that, it isolates the extra little nudge, the specific effect that only happens to the treated group only after the policy. It's the deviation from the common trend that we can attribute to the intervention.
So beta 3 is the difference in differences estimator.
That's it. It's our causal estimate. And the beauty of the regression is you can do all this while also controlling for 10 other things you think might be important, like population size or unemployment rates.
Okay, this feels like a good time to make a crucial transition. We've talked about the math, the skeleton of the model, but now we have to talk about its spine. The one assumption that if it fails, the whole thing just collapses.
You can't overstate this. We are talking about the parallel trends assumption, or PTA.
And if this fails, the Debaty estimate is biased. It's basically worthless.
It is. The assumption states, very precisely, that the DD estimator is valid only if the treated and control groups would have followed parallel trends in the absence of treatment.
Okay, we have to pause there.
Yeah.
Because that's a statement about a future that never happened. In the absence of treatment, reality is something we can never, ever observe. So how can an entire method rest on something you can't prove?
That is the big philosophical challenge of it, and it's why researchers spend so much time on the one thing they can test. The trend in the period before the treatment.
It's pre-treatment period.
Right. The logic is, if the two groups were moving in lockstep, if their paths were parallel before the policy, then it's plausible, not guaranteed, but plausible, that they would have continued on those parallel paths if the policy had never happened.
So you look at historical data, you plot it on a graph, and you see if the lines for the two groups are moving together before the policy date.
You have to, because if they were already diverging before the treatment, then the difference you measure after is not the policy effect, it's just a continuation of that pre-existing divergence.
Can you give us a quick example of how that would contaminate the result?
Sure. Let's go back to jobs. Let's say our treated city, city T, was already growing jobs at 1% a year. And the control city, C, was only growing at 0.5% a year. They are not parallel. They're already pulling apart.
Okay.
Now the new policy kicks in. In the post period, City T's job growth goes up to 1.5%, and City C's stays flat at 0.5%.
So if you run the simple DD math, the change in T is plus 0.5%, the change in C is 0, so the DD is 0.5%. It looks like the policy created 0.5% of job growth.
But wait, T was already on a path to grow 0.5% faster than C, regardless of the policy. So the DDT calculation has incorrectly absorbed that pre-existing momentum and called it a policy effect. The true effect was actually 0. The city was just continuing its trend.
Wow. Okay. So if your trends aren't parallel to begin with, your control group is not a valid stand-in for what would have happened.
It's not. The assumption is what gives your forecast its credibility. It's what allows you to build the crucial thing we're after, the counterfactual.
The counterfactual, the alternate reality.
Exactly. The PTA is what lets us take the trend of the control group and sort of paste it onto the treated group to project where they would have gone. We're saying, look, the control group's world changed by this much, so we assume your world would have changed by that much too. Any deviation from that projected path, that is the policy effect.
So researchers absolutely have to show their work on this. Show the graph of the pre-trends. If those lines are moving together, the assumption looks plausible. If they're pulling apart, the result is immediately suspect.
Right. Now, in the real world, the data is rarely so simple. We often have panel data.
Meaning you're observing the same cities or states or firms over many, many years.
Exactly. And when we extend DID to that kind of data, we almost always combine it with another technique called fixed effects to make it even more reliable.
Okay, we are leveling up the model here. If the basic regression already controlled for permanent differences and common trends, what more do fixed effects bring to the table?
They let us control for those things with much, much more precision. We usually combine DID with two types of fixed effects, unit fixed effects and time fixed effects.
Let's start with unit fixed effects. What are those?
Okay, so unit fixed effects control for all the unobserved, time-invariant characteristics of each specific unit. Think of it as a unique fingerprint for every single city in your study.
So instead of just one general permanent difference between the treated and control groups,
you get a personalized benchmark for every single unit. So if New York City has a permanently higher cost of living than Denver, the unit fixed effect for New York absorbs that entire difference. It's no longer a source of bias. It strips away all those baseline differences completely.
That sounds incredibly powerful. It really isolates the change within each unit relative to its own unique starting point.
It is. Then we also add time-fixed effects.
Which sounds like an expansion of that post variable we had before.
It is. Instead of just one variable for after the policy, you include a separate dummy variable for every single year or every quarter in your study.
And why is that better?
Because it controls for specific economy-wide shocks that happen in a particular year. Imagine your study runs from 2005 to 2015. Well, 2008 was a very unique year, right?
The financial crisis.
Exactly. The time-fixed effect for 2008 absorbs the impact of that massive shock across all the cities in your study, treated and control alike. If 2012 had a big energy price spike, the 2012 fixed effect absorbs that. It cleans out the global weather for each specific time period.
So the combination of the two, unit fixed effects and time fixed effects, that really scrubs the data clean, leaving only the variation you want to study.
That's the goal. It rigorously strips away all that extraneous stuff, the unique features of the places and the unique features of the times, to make your final causal estimate as credible as it can be.
So assuming we've done all this correctly and our parallel trends assumption holds up, what can we say about the statistical quality of this DADI estimator? Is it a good tool?
It's a fantastic tool. Under those valid assumptions, we say that the DADI estimator is both unbiased and consistent.
Can you break those terms down for us? What does unbiased mean here?
Unbiased means that, on average, the estimator gets it right. If you could somehow repeat your study 1,000 times, the average of your 1,000 DD estimates would land right on the true causal effect. It doesn't systematically aim too high or too low.
Inconsistent.
Consistency is about sample size. It means that as you get more and more data, your estimate gets more and more precise. It closes in on that true value. So more data leads to a better answer.
That's the theory. But in practice, there are some major statistical traps, right? Particularly with calculating the uncertainty around our estimate, the standard errors.
Oh, absolutely. This is critical. You can get the DD number right. If you calculate your standard errors incorrectly, you can fool yourself into thinking you found a significant effect when it's really just noise.
And there are two big reasons for this, right?
Two main reasons, and they're related. The first is serial correlation.
Meaning the data points aren't independent of each other.
Exactly. When you're looking at the same city over time, this year's unemployment rate is obviously related to last year's. They aren't independent draws from a hat. If you ignore that, you're pretending you have more information than you really do.
And that makes your standard errors artificially small. You look more confident than you should be.
It's a classic way to get a false positive, a type I error. The second related problem is group-level treatment assignment. The policy isn't applied to 1 million individuals. It's applied to one unit, a state, a county.
So even if I have data on millions of people inside that state,
the treatment itself was only switched on once for that one state. If you only have, say, 5 treated states and 5 control states, your effective sample size for what caused the change is really just 10. Not 10 million.
And if you ignore that, you again dramatically underestimate your standard errors.
Right, so the standard practice is to cluster your standard errors at the level of the treatment, at the state level, for example. It's a statistical correction that accounts for both of these problems and gives you a much more honest measure of your uncertainty.
Okay, this brings us back to the big picture. Why do policymakers, why do economists rely on this tool so heavily?
Because it's a cornerstone of evidence-based policy. It moves us past just telling stories and into a world where we can get a real causal estimate.
What's that one critical question it answers for a lawmaker that a simple before and after chart just can't?
It answers the question, how much did our policy change things relative to what would have happened anyway?
That last part, relative to what would have happened anyway, that's everything.
It is, and you see it used everywhere. In labor economics, it's famous for studies on the minimum wage. You compare a state that raised it to a neighboring state that didn't to isolate the effect on employment from just, general regional economic trends.
How about in finance or tax policy?
Absolutely. When a country changes its trade policy or a state cuts corporate taxes, researchers will use D-a-day to forecast the impact on growth. They compare that state's GDP growth to a similar state that kept the old tax rate controlling for the national business cycle.
And it's used in social policy too, I imagine.
Yeah.
Health, education.
For sure. Did a new school curriculum actually boost test scores more than the general upward trend in scores that was happening everywhere? Did a public health campaign lower smoking rates beyond the decline that was already in progress? DD gives you a credible answer.
So at the end of the day, its real value isn't just the math. It's that it builds that counterfactual.
That's it. It creates a sophisticated prediction of the world without the policy, and that is incredibly powerful information when you're deciding what to do next.
But, like any powerful tool, it has its weak spots. It's not foolproof. We have to talk about the danger zone, the limitations that can really mess up the results.
Right, and we've already covered the biggest one, the failure of parallel trends. If that doesn't hold, the study is fundamentally flawed. Game over.
But even if the pre-trends look perfect, there are other, more subtle ways it can go wrong.
Yes, one big one is anticipation effects. This is when people know the policy is coming and they change their behavior before it officially starts.
Can you give an example of that?
Sure. Imagine a city announces today that in 6 months, they're going to implement a big new tax on sugary drinks.
Huh?
Well, what are people going to do? They might start stocking up now. Or stores might run huge sales to clear out inventory before the tax hits. So in the pre-treatment period, you see this artificially weird behavior. Sales might plummet right before the start date because everyone already bought their soda.
And that makes the before period look artificially low.
Right. So when the tax finally hits and sales are just normal low, the DD calculation will be totally skewed. It will underestimate the true negative effect of the tax because the baseline it's comparing to was already weirdly distorted by the anticipation.
What's another pitfall?
Spillovers. This is when the treatment in one group accidentally affects the control group.
The effect bleeds across the border.
Exactly. Say you're studying the effect of a new job training program in County A, and you're comparing it to the neighboring County B. Well, what if people from County B, the control group, hear about this great free program and just drive across the border to sign up?
The control group is now contaminated. They're getting some of the treatment.
Right. And that makes the control group look better than it should. Since DD is the difference between the two groups' changes, this will make the estimated effect of the program look smaller than it really is. It shrinks your result.
And there's one last one. The one that the model, by its very design, just can't see.
This is the toughest one. DD cannot capture a time-varying, unobserved shock that is unique to only one group.
Let's nail that down.
Wow.
The model handles things that are permanent and unique to a group, like its geography. And it handles things that are time-varying but common to everyone, like a recession.
Correct.
So what's an example of something that's both time-varying and unique to just the treated group?
Imagine you're studying the effect of a new fishing regulation in Lake A, our treated lake, and comparing it to Lake B. You see a huge drop in the fish catch in Lake A after the regulation, and your DD result is massive and negative. But what if, during that same post-period, a factory in the town next to Lake A had a massive, one-time accidental chemical spill that just happened to kill off half the fish?
That has nothing to do with the regulation, and it only happened to Lake A.
Exactly. It's unobserved by the researcher, it's time-varying, it only happened after, and it's unique. The DD estimator has no way of knowing about that spill. It will see the drop in the fish catch and wrongly attribute all of it to the new regulation. This is the ultimate danger zone.
So we've covered a huge amount of ground here. From the simple idea of a double subtraction all the way to the formal math and its biggest pitfalls, DD is clearly this powerful way to estimate causal effects by filtering out those permanent differences and common trends.
And its value is that it tackles that fundamental real-world problem when you just can't run an experiment. It's the best tool we have for quantitatively building the counterfactual, for creating that vision of the world as it would have been, which is essential for making smart policy choices.
It provides the quantitative correction, for sure. But as we just saw with those limitations, the most accurate answer isn't always just about the math.
No, not at all. Like any powerful tool, it demands very careful use, a lot of statistical vigilance, and just constant questioning of that core parallel trends assumption.
Which brings us to a final thought for you to chew on. Given that the DID model is built in a way that it mathematically cannot see a time-varying shock that's unique to the treated group, like that chemical spill, how much do researchers and policymakers need to rely on, well, old-fashioned detective work, on deep qualitative historical context to make sure they haven't missed some invisible shock that happened only to their treated group? Because even when the math looks perfect and the result is statistically significant, that result could be completely wrong if the real cause was something the model was blind to. That reliance on context, even in our age of big data, is something to really think about. Okay, let's unpack this. Today, we are taking a deep dive into something that, well, it's everywhere, but it's also constantly getting made fun of. Economics forecasting. I mean, you see it every single day in the financial news, right? One big bank says a massive correction is coming. The next one predicts this huge global boom. And yet, for all that noise, governments, massive corporations, funds with trillions of dollars, they all spend a fortune on these models. So if the predictions are, so often off the mark, why does everyone lean on them so heavily? Our mission today is to get past that simple question of, was it right or wrong? And really focus on the strategic utility. We've been digging into our source material, the strategic utility of economic forecasting, to understand how these numbers work as essential tools for decision makers, and not just, flawed attempts to see the future.
That framing is so important. We're not here to argue about whether the Q3 GDP forecast was off by 0.1%.
Right.
We're here to establish the foundational role, and it's this. Economic forecasts are, at their core, used to anticipate future economic conditions. They are not, and this is critical, they are not designed to eliminate risk. They're designed to help people reduce uncertainty when they're trying to plan for what's coming next.
So it's less of a crystal ball and more of a weather map for the economy. It shows you probabilities, not certainties.
That's a great way to put it. Imagine you're playing this incredibly complex, three-dimensional chess game, but you can only guess what your opponent's next 5 moves might be. A forecast doesn't tell you the exact moves.
It can't.
It can, but it tells you the probabilities of those moves. And that lets you focus your energy on defending against the most likely or the most damaging attacks.
That gets right to the heart of it, because I think if I'm a CEO paying millions for a forecast, secretly, I'm hoping for a sure thing. But the source material makes this distinction right at the top that really challenges that.
It does, and we have to keep coming back to this point. Forecasts do not provide certainty, they provide probabilistic guidance.
Probabilistic guidance.
That phrase shapes the entire conversation around risk management. If you take a forecast and treat it like a guarantee, you've already misused the tool. The value is in understanding the range of what's likely to happen and the risks tied to each of those outcomes.
So the strategic play isn't to follow a fixed map, but to adjust your course based on the shifting probabilities, knowing a storm could still pop up out of nowhere. You're looking for the strongest set of probabilities to anchor your big decisions, because the cost of being unprepared for something that was highly likely, that's often way worse than the cost of modeling for it in the first place.
Absolutely. It changes the goal from prediction to preparation.
So now that we've established the what, this probabilistic guidance, let's get to the who. Because here's where it gets really interesting. The sheer diversity of people and institutions relying on these numbers is just staggering. We really need to break down this global ecosystem of users and how they all take the same big economic picture and use it for their own very specific strategic needs.
Indeed. And we can really break it down into 5 main groups. And the key thing to remember is, even if they're all looking at the same, say, 1% projected jump in inflation, how they react will be completely different. It all depends on their job, their mandate.
Let's start at the top then, the biggest players.
The giants. We're talking about governments. Their focus is fundamentally public finance, making policy happen. The source highlights 3 big uses: fiscal planning, budget preparation, and then policy evaluation.
Fiscal planning is huge. When a country's Treasury Department maps out a 4-year plan, it's not just numbers on a spreadsheet. It's a promise about the nation's financial health. They have to forecast everything from how much people are going to spend, which drives tax revenue, to how many people might be out of work, which drives, spending on social programs.
And let's talk about what happens when they get it wrong, because the source really emphasizes how severe that can be. Let's say a government forecasts a healthy 3% GDP growth.
Okay, sounds good.
And they need that growth to fund a new healthcare program and, keep the budget balanced. So they plan accordingly, they issue bonds, they commit to all this new spending because they're expecting a flood of tax money to come in. But then, what if the economy only grows by 1%?
Ouch.
Those tax revenues are suddenly way, way lower, and now the government has a massive unplanned hole in its budget. But they've already promised the money for the new spending. So the fallout is immediate, it's political, they're forced into making emergency cuts, usually on things people care about, like infrastructure or education.
Really, they borrow more money, right?
Or they have to issue emergency debt, which can make them look riskier to global investors, and that can drive up the interest costs for the entire country for years to come.
So a single forecasting error can literally make it more expensive for the country to build a bridge a decade later. That's a massive consequence. And that feeds right into your second point. Budget preparation.
Exactly. Budget preparation is where that big macro plan becomes real. It's the line items. It's what decides if the Defense Department gets a 5% increase or a 2% cut. And those numbers, once they're set for the year, they're set in stone. So the forecast they're built on has to be as solid as possible. And the last piece is policy evaluation. Say a government creates a new tax credit to help small businesses. To know if it actually worked, they need a solid forecast of what the economy would have looked like without that tax credit.
Ah, the counterfactual, the what if.
It's the crucial baseline. They can then ask, did we get the result we expected, or did things turn out better or worse than the projection? Without that forecast baseline, trying to judge a policy's success is, frankly, just guesswork.
Okay, moving from governments to the people who steer the ship, so to speak. Central banks. Their whole world is stability and market control. The forecast is their #1 tool.
It really is. Their main job is setting monetary policy and specifically inflation targeting. This is how they keep the economy from getting too hot or too cold. But the key difference between them and the government is the time lag they have to think about.
What do you mean by time lag?
Well, when a central bank changes something like the main interest rate, it takes a long time for that change to ripple through the whole economy. We're talking like 18 to 24 months before you see the full effect on credit, investment, and prices.
So they can't react to what's happening today.
They can't. They have to set interest rates based on where they forecast inflation will be 2 years from now.
Wow. So if their forecast says inflation is going to be too high in 6 quarters, they have to act now. They have to raise rates today to slow things down, to try and hit a target that's still way off in the future.
That is the essence of their strategic function. The forecast tells them what to do. And if the market investors, businesses, if they stop believing in the central bank's forecast, you get volatility. People start betting on different outcomes. So the credibility of the forecast is directly tied to the bank's ability to keep markets calm.
Okay, next up, businesses, the actual engines of the economy. For them, this isn't about national stability. It's about beating the competition and making a profit.
For them, the source material really zeroes in on investment and capacity planning. These are huge, expensive decisions. Think about a big drug company.
Right.
They're not deciding if they should order more pens next month. They're deciding if they should spend billions of dollars over a decade to build a new research center and hire hundreds of scientists.
And that decision has to be based on a forecast that looks, what, 7 to 10 years out? A forecast about income trends, regulations, population changes?
All of it. If that long-term forecast points to a slowdown in people's disposable income, then spending all that money on R&D today becomes an enormous risk. The penalty for getting that wrong is just a catastrophic waste of capital.
It's a bet the company kind of decision.
In some cases, yes. And then there's the more day-to-day use, which is sales and demand forecasting. This is much more tactical. A big retailer, for example, uses forecasts to manage their inventory.
So if the forecast says it's going to be a mild winter,
They order fewer heavy coats. If it signals a big holiday shopping season, they stock up the warehouses and hire extra staff. The difference between a good and a bad sales forecast for them is the difference between writing off millions in unsold stuff or losing millions in sales because their shelves were empty. It's a direct hit to the bottom line.
Okay, user group #4. Financial institutions, banks, investment funds, the architects of risk.
That's right. For them, it's all about assessing and pricing risk. They use forecasts constantly for really sophisticated risk assessment. When a bank is deciding whether to loan money to a company, they build a model of how likely that company is to go bankrupt.
And that probability isn't fixed.
Not at all. It's completely tied to the health of the wider economy. So they have to project that company's financial health not just in the main baseline forecast, but in a bunch of worst-case scenarios. What happens if unemployment suddenly spikes to 8%?
And this isn't just for their own good, right? Regulators make them do this.
Exactly. This feeds directly into regulatory requirements. Banks have to run these mandatory stress tests using economic forecasts to prove they have enough capital to survive a major recession without collapsing. The forecast is literally part of their license to operate.
And what about pricing assets?
Yeah.
Stocks, bonds, things like that.
That's the other big piece. When you're trying to figure out what a company's stock is worth, you're basically guessing its future profits and then calculating what that stream of money is worth today.
A discounted cash flow.
Right. And those future profits are obviously tied to the macroeconomic forecast. So if the consensus long-term forecast for global growth gets revised downwards, even by a little bit,
The value of thousands of companies drops today.
instantly, even if they're doing great right now, the forecast of the future changes the value of the present.
Okay, so that brings us to the last and maybe most surprising user group. Households. You and me. People, I think this is all just for bankers and governments, but the source material's clear that we use them too, even if we don't realize it.
We do. We're talking about consumption and savings decisions. Now, you probably don't subscribe to the World Bank's quarterly report,
No, I can't say that I do.
but you are constantly absorbing the big economic stories from the media, and those stories are just reflections of these major forecasts.
So if the news is all about a strong job market and low interest rates,
You feel more confident, the perceived risk to your career goes down, you might feel more comfortable spending more, maybe buying a new car, or even taking on a massive 30-year mortgage to buy a house.
but if the headlines are all about high inflation and potential layoffs,
The opposite happens. A rational household pulls back. You start saving more, you put off buying that new appliance, you try to pay down your credit card debt.
and that creates a feedback loop, doesn't it? If millions of people get scared by a recession forecast and stop spending, their behavior can actually cause the very recession the forecast predicted.
It's a classic self-fulfilling prophecy. So the strategic utility at the household level is incredibly powerful. It connects your personal finances when you buy a home, how you save for retirement. It connects all of that directly to the same big models being used by the central banks. It's one seamless spectrum of decision-making.
That's a fantastic map of the ecosystem. It really shows that economic forecasting isn't one single thing. It's like 5 or 6 different tools, depending on whose hands it's in.
Yeah.
Okay, so we've laid out this huge scope of users, from a family deciding on a savings plan all the way up to the Federal Reserve setting interest rates. And it's clear that the kind of decision they're making depends on, how far out they're looking. Which brings us right to the idea of the time horizon. You just can't use a 3-month projection to decide on a 30-year project. So we need to break down these different forecast horizons and, more importantly, see how the usefulness of the forecast changes as we look further and further into the future.
Absolutely. When we talk about the forecast horizon, we're just talking about how far out the prediction goes. And the source material gives us a really clean breakdown. Short run, medium run, and long run. And each one reflects, more complexity and, frankly, less accuracy as you stretch it out. So
Yeah.
short run forecasts, these are typically looking out just a few weeks or months, maybe up to a year and a half.
Very immediate.
Very. The focus is on current operations, reacting tactically to what's happening right now. Their whole utility is about informing those small operational decisions.
So it's like an airline adjusting ticket prices for the weekend based on a 72-hour demand forecast. Or a factory tweaking its production schedule for next week because of a small supply chain hiccup.
Exactly. And these are highly reversible decisions. If the short-run forecast is a little off, the cost of fixing it is pretty small. Maybe you had a few too many staff on shift, or you have a little extra inventory to carry for a week. The whole point is just maximizing efficiency right now and managing your cash flow.
Okay, so what about the next step up?
That's the medium-run forecasts. Here we're looking at a time frame of, say, 1 to 3 years. This is the absolute bedrock of corporate planning. Its main job is supporting the big business planning and budgeting cycles.
So this is where the annual budget gets set. The forecast tells you what your revenue might look like, which then determines how much each department gets to spend, what the marketing budget is, how many people you can hire over the next year or two.
Precisely. And if that forecast suggests a bit of a downturn coming in year 2, a smart manager can decide today to slow down on expansion plans, to hold on to some cash, just in case those headwinds actually show up.
It also seems critical for project approvals. If you're looking at an investment that's supposed to pay off in 3 years, the medium-run forecast is what tells you whether it's a go or a no-go.
It's central to that decision, absolutely. And finally, we get to the long-run forecasts. These are the big ones. We're looking 5, 10, sometimes even 30 years into the future.
It feels like pure science fiction.
It can feel that way. Their focus is completely different. It's about trying to anticipate major structural changes in the economy and society. And their utility is in guiding these huge, often irreversible policy and investment decisions.
So this is a power company deciding whether to spend billions on a new nuclear plant that will operate for 50 years based on a forecast of climate policy and population growth. Once you build it, you can't unbuild it.
That's a perfect example. That's a sunk cost. Or governments using them to figure out how to fund pension systems 30 years from now. That depends entirely on long-run forecasts of things like birth rates, immigration, and how many people will be working. A forecast of a shrinking population demands a totally different tax policy than one predicting strong growth.
Which brings us to this, I guess you could call it a paradox, that the source material really hammers home the trade-off.
Okay.
It says that forecast accuracy typically declines as the horizon increases.
It's an inverse relationship, and it's not just a rule of thumb. It's almost a mathematical certainty in any complex system like an economy.
Why is that? Why does it get so much harder?
Well, two big reasons. The first is compounding error. A tiny, almost meaningless error in your starting data, something that might make your 6-month forecast off by 0.1%, can grow exponentially over 10 years, throwing your final number off by several percentage points.
Like snowballs.
It snowballs. And second, the number of new variables, things that you couldn't have even imagined, we call them emergent variables, that number just explodes over time. This guarantees that the assumptions your model started with will become less and less true.
So, okay, if we know long-run forecasts are the least reliable, what is their actual strategic purpose? You can't be using them as a precise prediction.
You're not. They serve two other critical purposes. First, they force you to think structurally. They make decision makers grapple with the long-term effects of big trends like demographics or technology, even if the specific numbers are fuzzy. And second, and this is probably the most important part, they enable scenario and stress testing analysis. You don't build your 30-year plan on the single baseline forecast. You use the forecast's framework to test how your plan would survive in a dozen different possible futures.
So the forecast gives you the architecture for a what-if game.
That's it. What if energy prices triple? What if a new technology disrupts our entire industry? The forecast provides the structure for asking those questions in a rigorous way.
So that's the real takeaway here. The value of a forecast changes with the horizon. Short term is about tactical adjustments. Medium term is for planning. But long term is much less about predicting a single number and much more about building a strategy that's resilient enough to survive a whole range of possible futures.
Exactly right. The forecast isn't the answer. It's the framework for asking better questions about risk. Which leads us, right into the kind of uncomfortable truth of all this. We've established that these forecasts are essential, but what's fascinating here is the source material's full-on acknowledgement that they are deeply fundamentally flawed instruments.
Right.
And a strategic user, a smart user, has to understand those flaws, the sources of error, to have any hope of using the guidance effectively.
It's like if you buy a really complicated, powerful car, you need to read the part of the manual that tells you what makes it break down. So our source material points to three main reasons forecasts are so uncertain, starting with a purely technical one: model error.
Model error just means that the mathematical framework, the model itself, is an imperfect or miscalibrated picture of reality.
It's a simplification.
It has to be. The real economy is infinitely complex. And our models, whether they're simple ones that just extend historical trends or these incredibly complex DSGE models that central banks use, they're all just simplified maps of the territory. And the problem is the territory can change. A model might be built on assumptions about how businesses and people behave, and those assumptions might have worked great for 20 years. But then a major structural shift happens, like, say, a new wave of deglobalization or a sudden change in how we all shop online, and the model's old rules just don't apply anymore.
So the relationship between things like inflation and unemployment, something like the Phillips curve, it might just weaken or break, and the model is still playing by the old rules, so it starts making systematic mistakes.
That's the constant battle. The world often changes faster than the models can be reliably updated and tested.
Okay, so that's model error. What's
Yeah.
the second source of uncertainty?
This one is a very practical data problem, especially for people who have to make decisions in real time. It's data revisions.
Meaning the data they're putting into the model is wrong to begin with.
Not exactly wrong, but preliminary. The initial economic data we get for, say, last month's business investment is often based on incomplete surveys. The more complete, accurate data might not come out for another few months,
So it gets revised.
sometimes significantly. And a policymaker is forced to act based on that first noisy signal. Imagine a central bank sees preliminary data in March that suggests inflation is taking off, so they react aggressively and raise interest rates.
Right.
But then in June, the data for February gets revised down, showing inflation wasn't as bad as they thought. It means they might have overreacted, slowing the economy down unnecessarily because they treated a noisy preliminary number as a hard fact.
So you're basically driving while looking in a rearview mirror that's a little bit blurry.
That's a perfect analogy. And finally, you have the one that breaks every model every time. Unexpected shocks.
The black swans.
The black swans. These are the massive, unforeseen events that models just cannot predict because they have no basis in historical patterns. A sudden geopolitical crisis that closes a major shipping lane, a natural disaster that wipes out an entire region's manufacturing, or, as we all experienced, a global pandemic that just stops the world in its tracks.
A model can predict a normal cyclical recession based on patterns it's seen before. It can't predict a war that causes energy prices to triple overnight.
It can't. That kind of external shock just blows up all the assumptions and forces everyone back to the drawing board.
So we have imperfect models, noisy data, and completely unpredictable shocks. It seems like the single number that comes out of a forecast is the least useful part of it. The real value has to be in how we understand and talk about all the uncertainty around that number.
That is the crucial pivot. To effectively use a flawed tool, you have to move beyond just the single point forecast. You have to understand the confidence intervals.
Explain that. What does a CFO or a government minister really need to get from a confidence interval?
Well, the point forecast, that single number, it encourages a very rigid, single-minded kind of planning.
This is the future. Plan for this.
Exactly. But the confidence interval shows you the range of possible futures, usually with a 90 or 95% probability. A smart user doesn't just look at the number, they ask, how wide is this interval?
What does that tell them?
It tells them how confident the model is. If the forecast for GDP growth is 2.5%, but the confidence interval is very narrow, say from 2.0% to 3.0%, that's a high confidence forecast. You can be pretty aggressive with your planning.
But if the point forecast is still 2.5%, but the confidence interval is huge, like from -1%, a recession, all the way up to +5%, a boom.
That massive range is a giant red flag. It's the model telling you that it has very little certainty about what's coming next, and the strategic response has to be completely different. A risk-averse CFO seeing that should immediately focus on building up cash reserves and hedging against that downside risk.
So the forecast didn't tell them what will happen, but it told them how dangerous the environment is, which is maybe more useful.
It's arguably much more useful, and this leads right into the second critical measure for using these tools well. You have to consider risks and alternative scenarios.
So go beyond the probabilities and actually tell a story about what could go wrong.
Yes. You model the baseline, sure. You model the upside and downside from the confidence interval. But then you also have to model the tail risks, those low probability but super high impact events. That would be a catastrophe if they happened.
Like what?
For a global bank, it might be modeling what happens if an entire region of countries defaults on their debt. For an energy company, it could be modeling a scenario where a sudden new regulation makes their biggest power plant obsolete overnight. The forecast framework gives them a way to stress test their company against these specific nightmares.
Yeah, this brings us right to that big warning from the source material, doesn't it? Over-reliance on point forecasts can lead to poor decisions.
It's the cardinal sin of using forecasts. When you treat that single number as the truth, you build a very fragile strategy. You build a plan for only one version of the future. And when reality inevitably turns out to be a little different.
You're caught completely flat-footed.
You're in panic mode. You're making expensive, reactive decisions instead of executing a flexible plan that was designed from the start to handle a range of outcomes.
That is the perfect segue, because we've talked about the quantitative side, the numbers, and their flaws. But now we get to what I think is the most critical insight of this whole deep dive. The forecast is a scientific tool and input, but it is not, and can never be, a replacement for actual human wisdom and judgment.
This is where the math meets management. And the mantra has to be, over and over again, forecasts inform decisions, but do not replace judgment. The model gives you an objective probability, but the final decision is always subjective. It has to incorporate things that a model can't possibly quantify. And our source material is great on this. It identifies 3 essential things that a decision maker has to add on top of the numbers. The first is institutional knowledge.
Right. This is the stuff that isn't in any public database. It's the specialized, on-the-ground knowledge that only exists inside a specific company or organization.
Perfect example. A big macro forecast might predict strong growth in the housing market because interest rates are low.
Okay, makes sense.
But the local city planning commission has institutional knowledge. They know that a bunch of local zoning laws and a lack of sewer capacity are going to physically prevent most of that predicted growth from ever happening in their area.
That's a micro-level reality that the big macro model would never see.
It's completely invisible to it. So institutional knowledge is like a filter. It refines the model's output by adding in these crucial real-world friction points. It connects the big data to the small, messy reality.
Okay, what's the second element?
Risk tolerance. This is all about the organization's or the individual's willingness to accept loss. This is where the subjective part of strategy really comes in.
So let's go back to that forecast with the really wide confidence interval, the one that went from recession to boom.
Yeah.
If two different companies get that exact same forecast,
Their reactions could be polar opposites. A high-growth tech startup that needs to attract investors might see that volatility as a reason to go all in, to bet on the boom scenario. Their survival depends on aggressive growth, so they accept the high risk of failure.
but a huge conservative pension fund.
A pension fund, with the duty to protect retirees' savings, will look at that exact same forecast and see it as a clear signal to get out of risky assets and move into safe government bonds. The forecast data is neutral, but its strategic use is completely defined by the mission and the resilience of the user. Risk tolerance sets the action threshold.
That's not what the forecast says. It's who's listening. Okay, and the third and final element.
We have to integrate policy constraints. These are the rules, regulations, or even ethical lines in the sand that limit your available options, no matter what the forecast says is the most profitable path.
This has to be huge for governments and big public companies.
It is. A forecast might show, with mathematical certainty, that moving a factory overseas would be the best possible decision for shareholder returns. It would maximize profits.
An optimal economic outcome.
On paper, yes. But then the policy constraints kick in. Maybe there are environmental rules or labor agreements that require keeping jobs in the country, or even national security rules about supply chains. Those constraints can completely override the purely economic calculation.
So what's the point of the forecast then, if you can't follow its advice?
It's still incredibly useful because it calculates the cost of following the constraint. It tells you exactly how much profit you're giving up to comply with the environmental regulation or to keep those domestic jobs. It quantifies the trade-off.
I see. So the forecast answers what's the cheapest way to do this. But the policy constraint forces the decision maker to choose the path that's, most compliant or politically survivable, even if it costs more.
Exactly. And if we pull all of this together, if we look at the big picture, the strategic utility of economic forecasting isn't really about seeing the future. It's about structuring uncertainty. It's about creating a framework that lets us manage risk, apply our own specific knowledge, and navigate these really complex constraints. The forecast brings rigor to the process. It forces us to put numbers on our expectations and model what happens if we're wrong. But its real power, its ultimate strategic value, only comes alive when a human being combines those hard numbers with the nuanced qualitative wisdom of real judgment. The forecast provides the data. The leader provides the wisdom.
That has been such a thorough and I think necessary journey. We've really moved past this idea of forecasting as just being, a guessing game. And we've revealed it for what it is, a sophisticated tool for managing strategic risk across, the entire global economy. So to just quickly recap the framework we've built here, we started with that core mission. Forecasts give us probabilistic guidance. Their job is to reduce uncertainty, not to eliminate it. Then we dove into that global ecosystem of users. We saw how governments use forecasts for fiscal planning, how central banks use them to target inflation years in the future, how businesses use them for huge investment decisions, financial institutions to stress test their own survival, and even how households use the general economic outlook to make personal decisions about saving and spending. We looked at the critical role of the time horizon and how the further out you look, the more the strategy has to shift away from prediction and towards scenario planning and stress testing, especially since we know accuracy goes down over time. And then finally, we looked at the sources of error model error, data revisions, and those unpredictable shocks. And we landed on the ultimate lesson. The forecast is only an input. It only gets its true strategic power when it's combined with those qualitative human factors. Institutional knowledge, your own risk tolerance, and the policy constraints you have to live with. Economic forecasts, at the end of the day, are an indispensable tool, but they only reduce uncertainty. They never, ever eliminate it.
And that leads us to one final, I think, provocative thought for you to take away, especially when we think about those really big, long-term strategic decisions, the kind that nations have to make. Since we know for a fact that accuracy falls the further out we look, and we know that any good decision has to combine the forecast with institutional knowledge, which is, inherently subjective and full of its own biases, it raises a really important question. When you're making a truly long-run strategic decision, like a 30-year infrastructure plan, How should a leader numerically weight the rigorous probabilistic guidance from the forecast against the essential but potentially biased institutional knowledge they also have to rely on? How do you build a system that stops your own internal biases from just steamrolling the cold, hard probabilities from the model while still allowing that crucial on-the-ground wisdom to correct the forecast's own blind spots? Finding that perfect balance, I think that's where the real art of strategic leadership begins. Welcome back to the Deep Dive, where we take the big numbers that rule the world, peel back the layers, and show you exactly what they're built of.
And today, we are really getting into the foundations.
We are. We're opening the hood on the economy's massive engine block. We are looking at the foundational metric that dictates global policy, drives market reactions, and ultimately defines national wealth and health, economic output.
This is the figure that headlines scream about every single quarter. If the number is up, we cheer. If it's down, the world holds its breath.
It really does.
But for most people, the understanding of this number, the total production of goods and services, it just stops right there at the headline.
And that's exactly what we're fixing. We are diving deep into gross domestic product, or GDP. Our mission today for you, the learner, is to move far beyond that simple figure. We're going to explore the three distinct and theoretically equivalent blueprints used to measure this colossal number.
And we'll show you how economists adjust it to make it meaningful over time, which is absolutely crucial.
Perhaps most importantly, we will dissect the critical gap between the economy's actual performance and its ultimate sustainable speed limit.
Understanding this architecture is really the secret to interpreting policy signals. You need to know not only the size of the pie, but the ingredients, the recipe, and the ultimate capacity of the oven.
Okay, let's unpack this. How this single critical figure is built, what policy risks it generates, and what vital information it simply refuses to tell us.
To start with the core concept, economic output measures the total market value of all final goods and services produced within a country's borders. And that's during a specific period, typically a quarter or a year.
And the truly elegant thing about this, I think, is that it rests on this idea of a circular flow. Every transaction is a loop.
Exactly.
If a good is produced, someone has to buy it, which is spending. And that money from the sale immediately becomes income for the people in the capital that made it.
Production generates spending, and
Yeah.
spending generates income. It's an unbroken circle of money flow.
A perfect loop.
And that continuous flow is the genesis of what we call the equivalence principle. Because production, expenditure, and income are just three different ways of looking at the same economic activity, GDP can be measured using three distinct approaches.
And they all have to give you the same result.
They must, in theory at least.
Yeah.
If $10 trillion worth of goods were produced, then $10 trillion must have been spent acquiring them, and $10 trillion must have been earned by those who produced them.
That's a fascinating constraint on the system. It suggests a perfect balance must exist. So if the three measures don't align in the real-world data that the government reports, it means the statisticians, well, they missed something in their count.
Precisely. That need for balance is why we have the three methods. So let's begin where the economic activity starts, with the production angle.
Okay, the production angle. This seems like the most straightforward way for, say, a business owner or a manufacturer to think about output.
It is. It focuses on the value added across all industries, from agriculture and manufacturing to services like finance and healthcare that occurs within the nation's borders.
And the key mechanism here, the thing that makes it work, is value added.
Yes. This is absolutely essential for avoiding the mistake of double counting. That is the nemesis of accurate GDP measurement.
Okay, so give us a robust example of that. What is the double counting trap?
Certainly. Let's imagine the production of a single car tire. A rubber plantation sells raw rubber to a chemical processor for, say, $100.
Okay.
That processor turns it into synthetic rubber material and sells it to a tire factory for $250. The tire factory then molds the tire, adds the tread, and sells it to the car manufacturer for $400.
And then finally, the car manufacturer puts that tire on a new vehicle, which is then sold to you, the consumer, for $30,000.
Right. Now, if we just added up the market sales price at every single stage, 100 plus 250 plus 400 plus 30,000, we would get an absurdly inflated number.
Because we've counted the rubber, what, 3 or 4 times by then?
Exactly. Value added solved this. The value added at the tire factory is the price they sold the tire for, $400, minus the cost of the intermediate material they purchased, the synthetic rubber, which was $250.
So their contribution to GDP is $150.
That's their piece of the pie. Similarly, the value added at the rubber processor is also $150. That's their sale price of $250 minus the $100 raw material cost.
So the production approach forces us to look past just the superficial sale price and measure the actual wealth creation at each distinct stage of the chain.
Yes. It recognizes that true output is the incremental economic transformation achieved by each industry. It's the ultimate check against simply inflating figures by counting the same materials over and over again.
And this allows an agency like the Bureau of Economic Analysis, the BEA, to look sector by sector: energy, real estate, tech services, and figure out the precise contribution of each one to the total economy without any overlap.
Exactly. Now, moving along that circular flow we talked about, we arrive at the expenditure angle.
The spending view.
This is often the most visible formula, the one people see in the news. It breaks down output based on who is buying the goods and services.
And this gives us that famous formula, C plus I plus G plus X minus M.
That's the one. C, I, G, and net exports.
So this is the blueprint we hear about in every quarterly GDP report. Let's dive into the detail of each component, starting with the biggest letter, C.
Consumption, C. This is all household spending. It's the absolute bedrock of the U.S. economy, typically accounting for about 2/3 of total output.
So 65, 70% sometimes.
Easily. And it covers everything the ordinary consumer buys. We're talking services like travel and education, non-durable goods like food and clothing, and then durable goods, which are items that last 3 years or more, like your appliances and cars.
The sources really emphasize that consumption is the largest, but also generally the most stable driver. It tends to fluctuate a lot less than investment. Why is that?
Well, because so much of consumption is driven by necessity and habit. People still need to eat, pay rent, go to the doctor, even during an economic slowdown.
Right, you can't just stop buying groceries.
You can't. Consumption definitely dips when consumer confidence plummets or unemployment spikes. But that base level of spending on essentials keeps this component relatively resilient. It's like a slow-moving engine.
And the one big exception here is when a household buys a newly constructed home. Even though a person is buying it, that spending is usually categorized under investment, under the letter I.
Precisely. And that brings us right to investment. This is spending by businesses, the capital formation they undertake, and it is the volatile, speculative, high-stakes part of the whole equation.
So this isn't buying stocks and bonds.
No, not at all. In GDP terms, investment means buying new equipment, constructing commercial and residential buildings, and, importantly, changes in business inventories.
This is where the risk is taken, right? If consumption is this stable river, investment is the whitewater rapids. Why is it so much more volatile?
Because investment is driven entirely by expectation. A business only buys a new fleet of trucks or builds a new factory if its management is optimistic about future demand.
If they think a recession is coming.
They can instantly halt multi-million-dollar projects. Just stop them dead. This sensitivity to the business cycle is what economists call the accelerator principle. A small change in consumer demand can trigger a disproportionately massive change in business investment.
So this makes the component that recession predictors watch the most closely.
Absolutely.
Yeah.
And speaking of volatility, that inventory change is a fascinating little part of investment. If a company produces 100 widgets and only sells 90,
the 10 widgets left over are counted as inventory investment. It's like the company bought them from itself.
It is. Inventory is a unique measure because it captures unplanned investment. And this is a huge signal. If businesses are building up inventory rapidly, it can mean two very different things.
Yeah.
If they built that inventory intentionally because they're anticipating strong demand, well, that's healthy. But if sales suddenly drop and the inventory buildup is unintentional, meaning goods are just piling up on shelves,
That's a huge red flag.
it's a critical leading indicator of a potential recession. Businesses will immediately cut production to clear that inventory, which leads to job losses and output contraction in the very next quarter.
That's a crucial nugget right there. A sudden, unplanned inventory pileup is the economy stuttering. Okay, moving on to government spending. G, this covers purchases made by the public sector, federal, state, and local.
G includes everything the government buys that constitutes a final output. So we're talking defense spending, buying vehicles for the Postal Service, building new highways, or paying the salaries of public employees like teachers and police officers.
But, as you pointed out the sources, what G excludes is often more important than what it includes. It excludes transfer payments. Let's clarify for the listener why those payments, things like unemployment benefits or Social Security checks, are invisible to the G component.
They're excluded because they are not purchases of currently produced goods or services. A transfer payment is simply redistributing existing income.
It's moving money from one pocket to another.
From the taxpayer to the recipient. The economic impact only registers when the recipient spends that money. So when a Social Security recipient buys groceries, that money is counted under consumption, under C.
So if we included the transfer payment in G and the grocery purchase in C, we'd be double counting the same economic event.
You'd be counting it twice. G has to be tied directly to the production of new output, not just the movement of funds.
That makes perfect sense. Okay, finally, we get to net exports, XM, which is exports X minus imports M.
Exports X are pretty straightforward. That's our domestic production being purchased by foreigners, so they clearly contribute to our domestic output and are added in.
But imports M are the subtraction, and this is where most of the confusion comes in. Why do we penalize GDP for buying imports?
Well, let's walk it through. We've established that GDP measures domestic production only.
Right, stuff made here.
So when I go out and buy a new phone that was manufactured in Asia, my spending on that phone is counted in consumption, in C. If we just stopped there, our GDP would be artificially inflated by the value of that foreign-produced phone.
I see. The C number went up, but the stuff produced here didn't.
Exactly. The subtraction of imports, M, is the accounting mechanism used to fix that problem. We subtract M to remove the portion of C, I, and G that was spent on output produced abroad. It purifies the number.
It isolates only the value of goods and services produced within our borders, ensuring that domestic focus of the GDP measure is maintained.
So the expenditure approach really is a comprehensive look at the demand side, but with very stringent accounting to keep the focus purely domestic.
Before we move on, let's look at that third, often forgotten method.
The income angle. This is what closes the circular loop. If the expenditure approach measures the spending.
The income approach measures the earnings generated from that production.
And the fundamental law here is, every single dollar spent must end up as income for someone else.
No accepted.
That flow of money is divided into 4 primary streams, reflecting the payments made to the factors of production. We have wages, which is compensation for labor. We have profits, the residual income for entrepreneurs and shareholders, and then rents and interest.
And wages are by far the dominant component here, right? It reflects the value of human labor in the modern economy.
Overwhelmingly so. Profits are the reward for risk-taking and innovation, the true measure of success for a business owner after all the other costs have been paid.
The crucial insight here is the seamless connection back to the expenditure approach.
Yes. If a household spends $500 on a new dishwasher, which is part of C, that $500 immediately fragments. A portion becomes wages for the factory workers, a portion becomes interest paid on the loan for the machinery, a portion goes to rents for the factory land, and whatever is left over is counted as profit for the business owners.
It's like an internal validation system for the whole model. But, if these 3 methods are supposed to be equivalent, why does the U.S. Bureau of Economic Analysis always report a statistical discrepancy in their official documents? If production equals spending equals income, shouldn't that discrepancy be 0?
That is an excellent, challenging question, and it speaks to the messy reality of data collection. In theory, they are perfectly equal. In practice, they never are.
So it's a data problem, not a theory problem.
It is. The statistical discrepancy arises because the data for the 3 methods are collected independently. They use different surveys, different sampling techniques, different source materials, trade statistics for exports, consumer surveys for C, tax filings for income.
And all those different sources have their own errors.
Exactly. Errors in collection, in timing, in coverage. They mean the final totals almost always diverge by a small but measurable amount.
So the discrepancy isn't a flaw in the economic theory, but a flaw in our ability to perfectly track every dollar in a massive $25 trillion economy in real time.
That's it, precisely. The BEA includes the statistical discrepancy line item simply to force the income side of the ledger to balance exactly with the expenditure side for the final reports. But the structural equivalence remains. It's why GDP is the central measure. It confirms that fundamental economic identity that production equals income equals expenditure.
It's a beautifully complex tracking system. Now that we've established the structural volume of output, we have to address how we make that volume meaningful, especially when you're comparing it over time.
Yes.
Here's where it gets really interesting, because we've been talking purely about dollar amounts, but what happens when the dollar itself loses value? We have to tackle the critical difference between a big number and a truly meaningful number.
This is the eternal problem of prices or inflation. If an economy produces, say, 100 units of energy, 50 cars, and 200 services in year one,
Okay.
and then it produces the exact same quantities in year two, but all the prices have risen by 10%, well, the total dollar value of output, the nominal output, would jump by 10%.
But the population doesn't have any more goods or services than it did before. They're not any better off.
Not one bit. This is why we have to define nominal output. It's output measured using the current market prices of the period being measured. It is the raw, unadjusted figure.
It is the headline number that often generates false cheer. Let's use a more complex example. Say our nominal GDP grew by 6% last year. That sounds fantastic on the surface.
That sounds great.
But if 4% of that growth was due to a genuine increase in production volume and the other 2% was purely due to inflation, just prices rising, the true increase in our standard of living is only 4%.
The remaining 2% is a statistical illusion. It's a mirage caused by price changes.
And that is the danger of relying on nominal figures. It makes long-term historical comparison completely meaningless.
Utterly. If you try to compare the nominal GDP of, say, 1950 to today, you are comparing apples to moon rocks.
Yeah.
The shift in the price level is so astronomical it renders the comparison irrelevant for assessing actual productive power.
Which is why we need real output. So real output is the total production figure that has been adjusted for inflation. This mathematical adjustment is essential for isolating true economic growth.
The crucial implication is that real GDP reflects the true changes in production volume. By stripping out the effect of rising prices, real GDP isolates genuine growth momentum.
It tells us definitively, are we producing more stuff or are we just paying more for the same stuff?
That is the fundamental question it answers. The process involves establishing a base year. So if 2012 is the base year, then every single good produced today, a car, a haircut, a software license, is valued using the price that a similar item commanded back in 2012.
So by keeping the prices fixed, any resulting change in GDP must be because of a change in quantity.
It has to be. And this brings us to the tool that bridges the gap between nominal and real, the GDP deflator. This is one of the most important concepts for our learner to grasp because it is the actual mechanism of adjustment.
Okay, let's unpack the deflator. It sounds like a complex statistical tool.
Conceptually, it's actually quite simple. The GDP deflator is just a broad measure of the overall level of prices for all new domestically produced goods and services.
So it's different from the CPI, the Consumer Price Index.
Very different. The CPI tracks a fixed basket of consumer goods, things you and I buy. The deflator tracks the prices of everything included in GDP consumption, investment, government purchases, everything.
So it's a measure of inflation for the entire productive economy, not just the stuff consumers buy at the grocery store.
Precisely. And the calculation is fundamentally a ratio. You take nominal GDP and you divide it by real GDP, then multiply by 100. This ratio gives us the percentage change in prices relative to that base year.
So if the deflator is, say, 120.
It means that the overall price level today is 20% higher than it was in the base year.
And crucially, this deflator is how economists perform the transformation. If the BEA reports the total market value of all goods and services this year, the nominal GDP, they then divide that nominal figure by the deflator to get the real GDP figure.
That's the mechanic. If your nominal output for the year is $25 trillion, and the deflator indicates that prices have risen 25% since the base year, you divide 25 trillion by 1.25.
And the resulting number, 20 trillion, tells you the true volume of production adjusted back to those base year prices.
Exactly. The necessity of real output cannot be overstated. Without it, you can't do meaningful long-term analysis, nor can policymakers forecast with any accuracy. If you're a central bank trying to predict the future strength of the economy, you have to know if the current expansion is driven by genuine volume increases, which might need a policy response, or just by price bubbles.
Real GDP provides that clarity.
It does.
Now that we know how to measure the volume accurately using real GDP, we can move from the static snapshot to the dynamic movement. Economies don't grow in a straight, predictable line. They follow a rhythm of ups and downs.
Expansions and contractions. That's right. Output naturally fluctuates around a long-term growth trend. This underlying trend, which might be 2 or 3% growth per year, is dictated by slow-moving structural factors.
Things like population size, education levels.
Infrastructure quality, and especially technological advancements. Those are the big ones.
But the actual output is always swinging around that trend line. And these swings are the infamous business cycles, the defining feature of modern capitalism.
And we use the real output data to define the phases of this cycle. So expansions are periods where the economy is growing robustly, typically above that long-term trend rate. They're characterized by falling unemployment and rising corporate profits.
And recessions are the periods of contraction officially defined in many places as 2 consecutive quarters of negative real GDP growth.
Right. The output data is absolutely critical for detecting these economic turning points. When real GDP growth slows down significantly, but hasn't yet gone negative, it signals that the peak of the expansion is near.
And the warning signs? They often appear first in that investment component we talked about as businesses start to pull back.
Exactly. Conversely, during a recession, we're looking for the rate of decline to slow down and flatten out. That inflection point, what we call the trough, suggests that contraction is nearing its end and a recovery is about to begin. These output figures are the essential diagnostic tools.
But just knowing the current output isn't enough. To interpret whether an economy is healthy or sick, you need a benchmark. You need to know what the economist should be producing.
This is where we introduce the crucial yet unobservable concept of potential output. It is the economy's theoretical speed limit.
Defined as the maximum level of output that can be achieved when all available economic resources, labor, capital, technology, are fully utilized in a sustainable way. That word sustainable is doing a lot of heavy lifting there.
It truly is. Potential output represents the economy operating at maximum efficiency, where there's no cyclical unemployment. So everyone who wants a job at the market wage has one, and factories are running without causing prices to accelerate or straining supply chains.
It's the maximum output you can sustain without generating persistent inflationary pressure.
That's the key.
It's like the maximum sustainable horsepower of an engine. You can redline the engine for a short burst, pushing actual output above potential, but you risk overheating and breaking the machine. That overheating, that's inflation.
Exactly. Potential output is directly linked to the productive capacity of the nation. So if a country improves its labor force skills through education, builds better infrastructure, or adopts a huge new technology like AI is projected to be, its potential output permanently rises. The economy can now produce more sustainably.
And the reverse is also true. A natural disaster that wipes out capital or a rapidly aging labor force could actually cause potential output to decline.
It could. But it's a concept that involves complex judgments. For instance, what constitutes full utilization of labor? Is it 3% unemployment? 4%? Economists are constantly debating the natural rate of unemployment, the rate that exists even when the economy is perfectly healthy.
And that debate really highlights why estimating potential output is one of the hardest jobs in economics. It's unobservable. You can't just look up potential GDP in a data table.
You can't. It'd have to be estimated using sophisticated modeling techniques, like statistical filters that try to separate the long-term trend, the potential, from the short-term fluctuations, the actual.
So the policymaker is basically chasing a ghost. They're making decisions based on their best guess of what the maximum speed is, even though that speed limit is constantly changing, and it's based on debatable assumptions about labor and technology.
And that inherent uncertainty is the wellspring of all policy risk, which brings us directly to the consequence of getting that measurement wrong. The output gap.
The output gap. This is the difference, the crucial diagnostic delta between actual output, real GDP we measure, and the estimated potential output. This gap is the most important policy signal an economy generates. It tells us whether we need stimulation or contraction.
Let's break down the two outcomes that come from this gap. The first one, case one, positive gap. This is what we call an overheating economy. It happens when actual output is greater than potential output.
So we're producing beyond our sustainable limits. What happens immediately?
Resources become scarce. Demand for everything from copper wiring to specialized software developers exceeds the sustainable supply. And when demand outstrips supply, competition drives prices up.
Inflation.
This pressure manifests as accelerating inflation across the economy. The moment actual GDP pushes past potential, the central bank sees a red flashing light. It signals they must intervene to cool things down.
The engine is redlining. A positive output gap is a sure sign that wages will start rising faster than productivity as employers compete fiercely for the small pool of remaining available workers, which just fuels a wage price spiral.
And then there's the other side. Case 2, a negative gap. We call this slack. This occurs when actual output is less than potential output.
This is the signal of economic inefficiency. We have a pool of unused resources, we have empty factory space, underutilized machinery, and most visibly, unemployed workers. The economy is operating well below its true capacity.
A negative gap signals disinflationary pressure because demand is low relative to the economy's capacity to supply goods. Businesses have very little pricing power, and they often face declining profits.
And this is the scenario that compels government stimulus or central bank rate cuts. It is the urgent message that policymakers have to step in, boost demand, and get those idle resources back to work.
So the output gap is truly the instantaneous diagnosis. It tells us if the central problem is scarcity driven by too much demand, the positive gap, or waste driven by not enough demand, the negative gap.
And the subsequent trillion-dollar policy decisions hinge entirely on how accurately that gap is calculated.
Given the gravity of the output gap as a policy signal, the ability to accurately measure and forecast output is probably the single most direct influencer of modern economic governance.
Absolutely. The output forecast, where we project real GDP and the output gap will be in the near term, that is the foundation upon which every major policy lever, both fiscal and monetary, is calibrated.
Think about fiscal policy, government spending, and taxation. If the economic forecasts, based on current GDP trends, predict a persistent, widening negative output gap, the government has a clear mandate for countercyclical action.
And that mandate is usually stimulus spending. This is where decisions are made to launch massive infrastructure packages, to increase unemployment benefits, or implement tax holidays, all aimed at injecting aggregate demand, C and G, into the economy to pull actual output back up toward potential.
And the scale of that intervention, whether it's a $500 billion package or a $2 trillion one, is directly tied to the estimated size of that projected negative gap. A large negative gap means a large required stimulus.
So if the underlying GDP data is flawed, or the potential output estimate is wrong, the stimulus will be the wrong size. It'll be inappropriate.
Completely. Then you shift to monetary policy, the domain of the central bank. Their dual mandate to maintain maximum sustainable employment and stable prices is guided entirely by their output forecast.
So that mandate is basically about keeping the output gap as close to zero as possible.
That's a great way to put it. So if the forecast shows the economy is running into a positive gap, it's overheating, creating inflation, the central bank's primary weapon is raising interest rates.
Right. Raising rates directly targets the C&I components of that expenditure formula. Higher borrowing costs discourage businesses from undertaking investment and discourage consumers from taking out loans for durable goods or homes.
And by doing that, they're cooling overall demand and trying to gently bring actual output back down to that sustainable potential level, hopefully without causing a recession.
A soft landing.
That's the goal. Conversely, if the forecast suggests a deepening negative gap, the central bank cuts rates to encourage borrowing and stimulate spending. The central bank's entire forward guidance, its commitment to future policy, is pegged to their internal estimation of the current and future output gap.
So without GDP data, the central bank is effectively paralyzed.
Flying blind.
Given that the stakes are measured in trillions of dollars and the risk of joblessness for millions, this heavy reliance on output forecasting, especially on that unobservable potential output, carries immense systemic risk.
Since it's a complex model, errors in estimation are, well, they're inevitable.
They are, and those inevitable errors lead to potentially catastrophic policy mistakes. Let's detail the first major danger, which is played out historically multiple times. Danger 1. Misjudging high growth as low capacity.
This happens if policymakers underestimate the economy's true potential output. They might look at a period of, say, moderate actual growth and mistakenly believe the economy is already hitting its speed limit. So if they believe the speed limit is 4,000 RPMs when it is actually 6,000, they will prematurely raise interest rates or propose austerity measures. They'll slam the brakes on an economy that still had significant room to grow without inflation.
And the ultimate consequence of this premature tightening is a prolonged period of economic slack, or even a shallow recession that was unnecessarily triggered by a policy error.
They artificially constrain the economy below its true potential, stifling genuine job creation and productive expansion.
The opposite danger is maybe even more corrosive. Danger 2. Misjudging low capacity as high growth potential. This happens when policymakers overestimate potential output.
So they think the economy is capable of, say, 6% sustainable growth when it can only really handle 4. So they interpret the
Right.
current 4% actual GDP growth as a sign that they still have a massive negative gap to fill. They think more stimulation is needed.
And this leads to aggressive overstimulation.
Yes. They keep interest rates too low for too long, pump massive amounts of fiscal spending into the system, and continue these aggressive policies long after the economy has hit its true potential. They are just feeding demand into an already stretched system.
And the result is runaway inflation, severe overheating. This forces a drastic, sharp policy reversal later on, typically involving rapid, aggressive interest rate hikes that are highly likely to trigger a severe recession.
And all because the estimate of the engine's capacity was fatally flawed from the beginning. The difficulty of accurately estimating this moving target, potential output, is precisely why the economic debate so often rages over whether policymakers are being too aggressive or too timid. They're making monumental decisions based on a theoretical benchmark.
Which brings us to a more fundamental issue. For the learner focused on thorough, nuanced knowledge, it is absolutely vital to know the blind spots of this metric. GDP is a powerful measure of aggregate output, but it is not a measure of societal well-being or sustainability or social progress. It misses massive pieces of human and economic reality.
This is so important. Let's dedicate some time to these crucial exclusions, starting with the vast hidden world of the informal economy.
Okay.
GDP fundamentally excludes economic activity that is not formally recorded, taxed, or tracked by official surveys. This includes illicit activities, yes, but far more importantly, it includes the massive amount of essential work performed in the household that is not monetized.
Let's talk about caregiving. If you hire a professional nanny for $50,000 a year, that income is counted in C, consumption.
Right.
But if you quit your job to care for your child yourself, the economy has now lost $50,000 of measured output, even though the service of childcare is still being provided. The value is still there, but it's invisible to GDP.
The true value of self-repair, cooking meals at home, or volunteer work is immense, yet completely ignored. This exclusion significantly undervalues the true total production in the economy, especially those essential services provided within the home.
And the second, and I think most structurally damning omission, is environmental costs. GDP is functionally blind to natural resource depletion and pollution.
It's worse than blindness. It's perversely positive in its accounting. GDP treats the depletion of natural capital like emptying an oil field or clear-cutting a forest as pure, immediate income. It adds to current output with no corresponding subtraction for the lost natural asset.
There's that famous dark anecdote here that perfectly illustrates the irony. If an oil tanker runs aground and causes a massive spill,
The immediate cleanup expenses, the wages for the cleanup crews, the government purchases of absorbent materials, the legal fees, all of that contributes positively to GDP. It increases C&G.
so GDP sees the pollution and its resulting remediation as an economic boom, not a disaster.
Destruction and cleanup both boost the number. It's a measure focused entirely on current economic flow and totally ignores the stock of natural resources being drained to sustain that flow. This is a critical philosophical limitation if we're aiming for long-term national wealth.
And finally, a key social limitation: income distribution. GDP is an aggregate total, and aggregates hide everything about inequality.
That is the ultimate critique of GDP as a measure of progress. A country could see its real GDP grow steadily year after year, which generates great headlines. But if all of that growth is captured by, say, the wealthiest 0.1%, and the real wages for the median worker stagnate or even decline,
Well, the majority of the population's standard of living is actually worsening, even as GDP goes up.
GDP tells you the exact size of the economic pie, but it tells you absolutely nothing about the size of the slices or whether those slices are distributed fairly. It treats a dollar earned by the poorest worker and a dollar earned in capital gains by a billionaire as mathematically identical.
Which ignores the profound social and political consequences of that unequal distribution.
Exactly. This limitation has led to a major search for alternative metrics that can supplement GDP, things like median household income or the Gini coefficient, which directly measure inequality. Relying solely on the aggregate figure gives a dangerously incomplete picture of national welfare.
Before we wrap up, we have to address a practical reality that plagues all economists: the constant shifting of the data itself. Output data are notoriously subject to significant revisions.
Yes, months or even years after the initial release. This is a major structural problem. We often hear about the advance estimate of GDP growth. That's the first number released, followed by the second estimate, and finally the third estimate. But the revisions don't even stop there.
Why do they shift so much?
The initial figures are compiled very quickly using incomplete preliminary survey data. They have to estimate components like inventory changes and specific service sector consumption because the underlying tax and trade information hasn't been fully reported yet.
And as better, more complete data comes in over the subsequent quarters, the BEA refines the estimates.
And the implication of this statistical lag is profound. Policy decisions are always made on the first and often flawed draft of history.
So the Federal Reserve might raise interest rates based on an initial GDP estimate that suggested rapid inflationary growth.
Only for a revision a year later to show that the growth was actually quite mild and non-inflationary.
And if that revision shows the central bank was operating on flawed assumptions, it means the recession or stagnation that the economy experienced was, in part, a consequence of reacting to bad data.
Policymakers are essentially navigating a massive, complex ship with a weather forecast that is constantly being corrected after the fact. The later the data, the more accurate the history, but the less useful it is for making decisions right now.
We have completed a massive deep dive here, moving from that simple headline figure to the complex three-dimensional architecture that defines economic output. So what does this all mean for the informed learner?
It means that total production is the core metric of economic life, and it's measured simultaneously through three lenses that must, in theory, align. What was produced, the value added, what was spent, C plus I plus G plus net exports, and what income was generated, wages, profits, rents, interest.
Crucially, we distinguish between nominal, the current dollar figure, and real, the inflation-adjusted volume change. We use the GDP deflator to strip out price changes and understand true growth momentum over time.
And finally, we establish that policymakers are fighting this constant battle to gauge the output gap, that critical difference between the economy's actual production and its potential sustainable capacity, which signals whether inflation or economic slack is the immediate threat.
But our deepest dive concluded by highlighting the fundamental limits. GDP measures production, but it ignores the vast, essential contributions of the informal economy, the cost to the environment, and perhaps most vitally, how that output is distributed among the population.
Which leaves us with a necessary final provocative thought for you to consider, which builds on these limitations. If the goal of economic policy is to improve human well-being and GDP is our primary scorekeeper, how can policymakers truly judge success if they rely on a single metric that rewards environmental destruction, ignores unpaid labor, and hides vast social inequality?
The search for measures of progress beyond mere output growth continues, and it forces us to ask, is maximizing output always the same as maximizing progress? Or is a stable, equitably distributed, and environmentally sound 2% growth preferable to a volatile, unequal 5% growth?
Something fundamental to mull over as you navigate the next quarter's economic headlines.
That's all the time we have for this deep dive into the architecture of economic output. We'll see you next time. Welcome back to the deep dive, where we take these, huge stacks of complex information and really try to distill them into the essential knowledge you need.
And hopefully give you a few of those aha moments along the way.
Exactly. So today, we are tackling a topic that, I'll be honest, it often lives in the footnotes of financial news, but it dictates where billions, maybe even trillions of dollars end up flowing. We're talking about the long-term capital gains tax policy, or LTCG.
It sounds like a piece of, dry legislative bureaucracy.
It really does.
But this specific tax rate is genuinely one of the most powerful economic levers a government can pull. It fundamentally affects how wealth is created, how investments are allocated.
And how robust the national budget is.
Absolutely. It's huge.
Yeah, so we aren't just talking about a number on a tax form here. We are talking about a deliberate incentive structure, one that's designed to shape the entire economy. So our mission today is really focused on the machinery behind that rate. We want to show you the crucial but also incredibly risky role of economic forecasting in deciding what that rate should be.
And we've gone through a pretty comprehensive stack of material for this one. Everything from the legal definitions to the deepest economic implications.
And the policy challenges, which are massive.
They're huge. And this is a critical dive because that rate, it's not an accident. It's a calculated and often very fragile bet on the future of the economy.
So our ultimate mission here is simple. We want you, the listener, to walk away understanding not just what the LTCG rate is,
Oh, why?
Right. Why every policymaker and, frankly, every serious investor obsesses over the economic forecast when they're trying to predict or just react to its movements.
And that obsession, it really stems from this core tension that the policy is trying to solve. Governments are always trying to balance two conflicting goals.
Okay.
On one hand, they want to encourage long-term economic growth, they want productivity, they want innovation, so they give investors this big tax break.
But on the other hand,
On the other, they desperately need stable, predictable tax revenue right now to pay for everything.
so the LTCG rate is the tightrope they have to walk between those two things.
Exactly. It's the balancing act.
Okay, so let's unpack this and start with the absolute foundation. We hear the term capital gains all the time, but that long-term part, that's the secret sauce here.
It really is.
So what exactly are long-term capital gains, and why does that holding period matter so much?
Okay, so fundamentally, a capital gain is just the profit you make when you sell an asset for more than you bought it for.
Right.
Simple enough.
Right. Buy low, sell high.
Exactly. But to qualify as long-term, that profit has to come from selling an asset that you held for a specific extended period of time.
And in the U.S., our sources say that period is.
Typically defined as more than 1 year and 1 day.
That threshold, 1 year, it feels so specific, but it's critical, isn't it? It acts as a kind of policy gatekeeper.
It's a huge gatekeeper. It's
Yeah.
what separates, the short-term speculators, the day traders.
A market churners.
Right. Their gains get taxed at the much higher ordinary income rates. This policy separates them from the investors who are, at least in theory, putting capital to work for the long haul.
So the government is basically drawing a line in the sand.
A necessary one, yeah. It's a behavioral signal. It's designed to reward patience. If you want companies to innovate, to hire people, to build real things, you need investors willing to commit capital for more than, 11 months.
And the tax break is the reward for not cashing out too quickly.
It's the economic carrot.
I do wonder, though, why the 1 year mark? It feels, I don't know, almost arbitrary. Why not 6 months or 2 years?
You're hitting on a key policy debate right there. I mean, in a mathematical sense, it is arbitrary.
Okay.
But it's a political and psychological necessity. If the goal is structural investment, you have to define what structural means. And 1 year is generally accepted as the minimum period to tell the difference between real investment and just, speculation.
And I imagine changing that would cause chaos.
Oh, massive implications. If you moved it to 2 years, for example, you'd probably see a big impact on market liquidity. You'd probably increase something called the lock-in effect, which we'll definitely get to later.
Understood. So it's an arbitrary line, but it's a stable one that everyone understands.
Exactly.
Okay, now let's talk about scope. How wide is the net that this tax rate actually casts?
The scope it's vast.
Yeah.
It touches nearly every single way that people and corporations build wealth. When you dig into the source material, 3 main categories really stand out as the bedrock of what's covered.
Let's detail those, because I think this is where you start to realize just how much of the economy is touched by this one single policy.
For sure. The first big one is real estate.
Okay.
This includes your house, residential property you might sell after living in it for a while. But it also includes massive commercial properties, office buildings, apartment complexes, huge tracts of land and investor holes hoping it'll appreciate.
And the second category is probably what most people think of immediately when they hear capital gains.
That's right, stocks and bonds. This is the core of most retirement accounts, most investment portfolios.
Mutual funds, ETFs, individual shares.
All of it. If you own them and you sell them for a profit after that 1 year mark, that gain falls under this LTCG system.
And then there's the third category, business equity, which I think often gets overlooked but can represent some of the biggest transactions in the whole economy.
Absolutely. This one is so important. We're not just talking about selling, 100 shares of Apple.
Right.
We're talking about an entrepreneur who sells the company they built from scratch after a decade. We're talking about venture capitalists finally exiting a long-held investment in a successful startup.
Or partners selling their stake in a big private firm.
It covers the entire engine of innovation and really large-scale wealth creation.
So if I hold any of these assets for more than a year and they go up in value, I get the reward. The incentive mechanism kicks in. These gains are taxed at a rate that's usually much lower than my ordinary income, my salary, my bonus, that kind of thing.
That's the whole point of the incentive. I mean, for a lot of high-earning professionals, their ordinary income tax rate could be, say, 37%.
Easily.
But their long-term capital gains rate might top out around 20%. That difference, that gap, is a powerful magnet. It pulls capital toward long-term commitment. It's a deliberate choice to reward, well, delaying consumption.
The decision to keep capital invested.
And to commit funds to those big, long-horizon projects that actually drive structural growth.
So the goal is pretty clear: encourage investment, but the actual rate that gets applied is incredibly complex. It's not just one number. What determines the final LTCG rate?
It's a really dynamic process, not some static formula. First, you have the obvious thing, the legislative framework, the laws Congress passes.
Right.
But the actual effective rate is really shaped by three bigger factors. The first is just broader fiscal objectives. Is the government trying to pay down the national debt right now?
Or are they trying to fuel growth through tax cuts?
Precisely. And the second factor is where the immediate economic conditions come in. A government in the middle of a recession might be desperate to stimulate the economy.
Which would suggest a lower capital gains rate.
Exactly. Conversely, if there's a huge boom, asset prices are spiking, revenues flooding in, they might feel it's time to raise the rate a bit.
Both to capture more of that revenue and maybe to cool off what they see as an overheated market.
The rate has to be calibrated to the economic cycle.
And we can't forget about variability. It's not a flat number for everybody, is it? Our sources confirm the rate often changes a lot based on your own financial situation.
That's a key distributional aspect. For you, the listener, it's really important to know that this policy is actually highly progressive in its structure.
How so?
In a lot of tax systems, lower and middle-income individuals, people whose capital gains fall below a certain threshold, can pay a 0% federal rate on their long-term gains.
Zero. That's a huge benefit if you're just starting to build some wealth.
It's phenomenal. But for the highest earners, the rate escalates. It often hits a top statutory rate, say 20%, plus you might have additional net investment income tax on top of that.
Pushing the total federal rate up to, what, almost 24%?
Close to it, yeah. This income-based variability is a core design feature. It's meant to manage the political and, the fairness implications of the tax.
And beyond income, does the type of asset matter, even within that long-term category?
Sometimes, yes. Policy often carves out special exceptions for assets the government really wants to encourage. A great example is qualified small business stock, or QSBS.
Oh.
That often gets extremely preferential treatment. Sometimes it's even totally exempt from federal capital gains taxes.
Yeah.
The explicit goal is to funnel capital into small, growing companies that drive innovation and create jobs.
So what really stands out here is that the LTCG rate is not a simple calculation. It's this sophisticated policy tool, this mechanism of extreme financial tailoring.
That's a great way to put it.
It's designed to manage behavior across different income levels, different asset classes, all while trying to hit these big national fiscal goals.
Exactly. And because those goals, fiscal stability and economic growth, are constantly moving targets, setting this rate requires incredible foresight.
Right. This rate isn't chosen based on last year's data.
Not at all. It's based on a prediction of what the economy will look like 5, maybe even 10 years from now. And that transition leads us perfectly to the macro lever function of this rate. If the policy is designed to influence long-term economic behavior, policymakers can't just, they can't guess what that influence will be.
They need models. They need to predict the outcome.
Right. So setting the rate requires sophisticated economic forecasting.
Okay, so forecasts are the predictive models that estimate future economic growth, investment activity, and critically for balancing the book's future tax revenues.
They're trying to model how the entire economic ecosystem is going to respond to this one single policy change.
It sounds almost impossible.
It's incredibly difficult. The core utility of the forecast is evaluation. To figure out, before you implement it, how a change in the capital gains rate will affect investment incentives, asset prices, and the pace of capital formation across the country.
Okay, so let's detail the intended positive effects of using a lower rate. This is the heart of that economic stimulus argument we hear so often during tax debates. When you lower the long-term capital gains rate, what is the policy actually trying to achieve?
The first goal is to stimulate investment. By reducing the tax barrier on profits, capital just becomes more mobile. It becomes more willing to take risks.
So if investors know they get to keep a bigger slice of the pie,
They're more likely to fund a new venture or buy a productive asset. It just injects fresh liquidity into the system.
and this feeds directly into the second point, which is increasing capital accumulation.
Exactly. When investors are incentivized to invest rather than, say, consume or just hoard cash, the capital base of the country actually grows.
Factories, more research labs, more infrastructure.
More startups. This accumulation builds a larger, more resilient foundation for the entire economy.
I really like the analogy that the source material suggests for this. Think of it like tuning an engine for maximum efficiency. The tax on capital gains is basically friction that's slowing that capital engine down. Lowering the rate is like reducing the friction.
That's the supply side theory in action. Businesses use that influx of capital to innovate, to buy better technology, to hire skilled workers, to expand. A more efficient allocation of capital leads directly to higher long-term potential GDP.
And a more productive economy overall.
That's the theory.
So the argument is that a lower tax rate, while it might cut revenue today, creates a bigger, more productive economy tomorrow. And that bigger economy will ultimately generate more revenue down the line.
That is the crucial theoretical defense of low LTCG rates.
Right.
But, and this is a big but, here's where we hit the trade-offs.
Right.
What happens when the rate is considered too high? This is the flip side, where higher rates can start to actively inhibit the economy.
Yeah. And the most famous negative consequence of that is the lock-in effect.
The lock-in effect is the policy nightmare. It's this reduction in asset turnover. People hold on to assets simply to avoid the immediate, steep tax bite.
Can you give us an example of that?
Sure. Imagine an investor who bought stock in a great tech company 10 years ago. It's now worth 50 times what they paid. A huge gain.
Okay.
They realize the company's probably matured, and there's a new, smaller, faster-growing startup that represents a much better use of their capital now.
But if they sell that winning stock to buy the new, better one, they have to pay, say, 30% or more in capital gains tax on that massive profit, which immediately shrinks the amount of capital they have to reinvest.
That's the calculation. So rather than paying that huge tax bill, the investor just chooses to keep their capital locked up in the old stagnant asset, even though it's no longer the optimal choice.
So the government gets no tax revenue from that transaction.
And the economy misses out on that capital moving to its highest value use.
So this waiting isn't just costly to the investor, it's costly to the whole economy because it leads to delaying critical investment decisions.
Capital gets stuck.
It creates a drag on growth. When rates are too high, the tax tail starts wagging the economic dog. The policy that was meant to govern the market ends up distorting it, freezing assets in place, and reducing overall market liquidity.
Which brings us right back to that core tension, the policymaker's dilemma that the forecast has to solve.
Right.
You have this massive trade-off between the promise of long-term growth from lower rates and the need for reliable, stable tax revenue from higher rates.
And the forecast is the quantitative tool they use to predict this incredibly complex dance between behavior and revenue.
It has to answer that central question.
Yeah.
If we lower the rate by 5 percentage points, how much new investment and how much extra selling will that generate?
And will the resulting economic activity eventually be large enough to offset the immediate hit to revenue? That is the defining analytical task. They have to model the growth impulse against the immediate fiscal hit. They need some kind of assurance that the long-term benefit of simulating capital formation isn't so expensive in the short term that it, destabilizes the entire national budget.
It's an exercise in high-stakes financial diplomacy. And every single percentage point change represents a calculated risk based on a prediction of future human and market behavior.
So we've established that setting this LTCG rate is a real high-wire act balancing growth and revenue. Now we get to the fascinating part. How do governments actually use these predictions to craft legislation?
Right.
Because it's not just about predicting the future. It's about using that prediction to craft a law that maximizes what you want to happen and minimizes the unintended consequences.
That's the essence of policy design. The primary role of anticipation and forecasting is to let policymakers see the potential macroeconomic effects before any reforms are even introduced.
They're trying to prevent costly surprises down the road.
Especially given how volatile the market is.
So let's start with the most basic use. Projecting revenue effects. This is kind of the bread and butter of fiscal policy, right?
It's fundamental for national budgets.
Yeah.
If Congress is considering a policy, they need official scoring from bodies like the CBO, the Congressional Budget Office, or the JCT.
Joint Committee on Taxation.
Right. They need estimates of exactly how much revenue a change will gain or lose over the next decade. Changing a tax rate that affects a revenue stream as volatile as capital gains requires really precise projections for deficit planning, for spending decisions, for debt management, everything.
And this brings up an incredibly important distinction that you need to understand. Static versus dynamic scoring.
Yes.
When they project revenue, how do they approach that behavioral question?
This is a classic political and economic divide. Static scoring is the simpler, more conservative method. It basically assumes that changing the tax rate will not change investor behavior or overall economic growth.
So if the government cuts the capital gains rate from, say, 20% to 15%, a static score would just multiply the existing level of sales by the new 15% rate and say, well, we're going to lose revenue.
Correct. It completely ignores the behavioral incentive. Dynamic scoring, on the other hand, attempts to factor that response in. It says, okay, if we cut the rate to 15%, people will sell more assets, the economy might grow faster, which leads to higher tax revenues elsewhere.
So the true net cost to the Treasury might actually be lower than what the static estimate says.
That's the idea.
Dynamic scoring seems much more realistic because it's actually modeling how humans respond. But I imagine it's also much, much riskier.
It is. Because if your behavioral prediction is wrong, your revenue forecast is wrong, and the budget is blown.
The decision to use it is a policy choice in itself.
It is. It reflects a belief in the power of these incentives, and that leads us to the heart of a behavioral modeling, which is the elasticity of realizations.
Okay, there's another one of those terms. Let's unpack that. Elasticity of realizations.
It sounds super complicated, but it's really just a measure of how sensitive investors are to changes in the tax rate. Think of the tax rate as the price of selling an asset.
Right.
If that price goes down, the rate is cut, how much does the volume of selling increase?
Let's use an example to show what low versus high elasticity would look like.
Perfect. Imagine two investors. They both have $1 million unrealized gain. The current tax rate is 20%. The government proposes cutting it to 15%.
Okay.
Investor A is, let's say, financially conservative. They already plan to sell in 2 years no matter what. The 5% cut is nice, but it doesn't change their plan. Their realization is inelastic. They're not motivated to change.
And Investor B?
Investor B has been holding on to that asset specifically because they thought 20% was too high. That's the lock-in effect we talked about. The moment the rate drops to 15%, they sell immediately. Their realization is highly elastic. They're extremely sensitive to that tax price.
So the government forecasters are trying to average out the behavior of millions of Investor A's and Investor B's across the whole market.
Yes. They use historical data to estimate this elasticity coefficient. And that one number dictates whether a rate cut will actually stimulate enough selling to generate more revenue. It's fiercely debated in policy circles because the entire forecast basically hinges on it.
But that only captures the response after the policy is passed. There's another layer here, the anticipation effect.
And this is arguably the most volatile and dangerous part of forecasting capital gains. The anticipation effect models how investors respond to expected rate changes.
Because behavior doesn't wait for the law to pass.
Not at all. It responds to the legislative calendar and just the political chatter.
Let's use a concrete timeline to show how this would play out.
Okay. Imagine it's the middle of 2024.
Yeah.
A new administration announces they plan to raise the top LTCG rate from 20 to 28%, effective January 1st, 2026. What happens in the 18 months leading up to that?
Well, any investor who is thinking about selling in 2026 or 2027 suddenly has a massive incentive to sell now, to accelerate their sales into 2024 and 2025 to lock in that lower 20% rate.
Exactly. So forecasters have to model a huge temporary spike in realized capital gains revenue for late 2025. This is often called a pull-forward effect.
And the opposite would happen if a tax cut was coming. People would delay their sales,
creating an artificial lull. And the result is that the revenue numbers get completely distorted in the short term. The government gets this massive temporary windfall right before a hike.
and then faces a corresponding revenue drought right after the new rate takes effect because all the willing sellers have already made their move.
Policymakers have to factor that distortion into their projections. Otherwise, they risk mistaking a temporary blip for some kind of permanent, sustainable revenue growth.
Which means they have to rely on scenario analysis. They have to wargame the policy.
That's a great way to put it. It involves running multiple scenarios. They model extreme rate reduction scenarios, predicting not just the growth, but the maximum potential revenue losses.
And they have to model rate increase scenarios, predicting the gains, but also calculating how bad that lock-in effect might get.
Right. At what point does the rate get so high that people just stop selling altogether, and you actually lose revenue compared to the lower rate?
And the whole point of all this forecasting is to avoid those unintended pro-cyclical effects we mentioned earlier.
A pro-cyclical policy is poison to economic stability. It's a policy that makes the existing economic cycle worse.
It amplifies the booms and the busts.
Right. You want policy to be countercyclical, to dampen the peaks and troughs. If you misjudge the lock-in effect during a boom and raise rates too high, you might slam the brakes on the economy too hard.
Or, even worse, if the economy is already heading into a recession and your forecast overestimates how much revenue you'll get, you enact a policy that brings in less money than you thought.
Which forces painful budget cuts right when the economy desperately needs support. It's a vicious feedback loop. Economic pain plus fiscal instability. So that scenario analysis is a critical risk mitigation tool.
And before we move on, we have to touch on the distributional and wealth effects again. Because the forecasts aren't just about money coming in, they're about who is affected.
This is where the social implications get analyzed. Forecasts are essential for understanding how these changes affect wealth and income distribution.
Because capital gains are so heavily concentrated among the highest earners?
Extremely concentrated, often the top 1% or even the top 0.1% of taxpayers.
Hmm.
So any change to the LTCG rate disproportionately impacts income inequality statistics.
So the analysis has to model which income groups will see the benefit of a cut or who will bear the burden of a hike.
Exactly. I mean, capital gains are a primary driver of accumulated wealth, of intergenerational wealth transfer. By modeling these effects, policymakers at least try to understand the consequences, even if they can't perfectly align the tax changes with broader goals of equity and fairness. Now that we understand the policy levers, we really need to dive deeper into the inherent volatility of this revenue stream, because it is the single biggest reason why LTCG forecasting is such a tightrope walk.
And the core concept here, which is so crucial for you to grasp when you think about government budgeting, is that capital gains realizations are highly procyclical.
Highly procyclical. It means they're extremely sensitive to the economic cycle, and they move in the same direction, only faster and more violently.
Okay, so when the economy is booming, what happens?
Asset prices are surging, investor confidence is high, corporate profits are great. This creates massive unrealized gains that people are happy to finally realize.
And the result is a huge spike in capital gains tax revenue. It can create an illusion of fiscal health during a boom.
It absolutely can. But then when a recession hits, the entire situation reverses, and it reverses violently. Asset prices collapse. Investor fear spikes.
And people are holding assets at a loss. No one wants to sell into a depressed market.
Right. Or they start realizing losses to offset previous gains. And the revenue from capital gains just falls off a cliff. We saw this in 2008. That revenue stream virtually evaporated overnight.
That extreme volatility must be a massive headache for fiscal stability planning.
It's a nightmare. Governments can't rely on this revenue stream to fund core, predictable expenses like healthcare or defense. They need forecasts to help them estimate not just the expected average amount of sales.
It's a volatility, the risk.
The volatility inherent in the tax revenue. They need to know the potential size of the swing. For example, during the dot-com boom, capital gains revenue spiked to, I think, nearly 14% of federal corporate income tax receipts.
Wow.
But just 2 years later, after the bubble burst, that figure was cut in half. That requires incredibly careful budgeting.
You'd need specialized reserves or something.
Exactly. You have to rely on other, more stable tax streams to cover your predictable bills. The forecasts have to account for that downside risk that could leave a massive hole in your budget.
Let's talk about the time horizon for policy design. When policymakers are trying to encourage long-term productivity, they can't be reacting to every quarterly swing in the stock market.
No, they have to rely on the long-run economic outlook.
That seems essential for stability.
It is. Long-term forecasts focus on the fundamental slow-moving drivers. Structural growth trends, demographic shifts, long-term development of capital markets. They're looking at the tide, not the waves.
And they have to consciously decide to filter out all the short-term uncertainty that dominates the financial news cycle.
Right. That short-term noise comes from market volatility, temporary political fights, things that might just affect the next 6 months. If policy is based on that noise, it risks being constantly changed.
Which creates incredible instability and defeats the whole purpose of encouraging long-term holdings in the first place.
The sources are really clear on this. Capital gains policy has to rely on a stable, long-run view of the economy to give investors certainty.
Okay, now let's shift the lens completely and look at this from the investor's perspective. We've established they respond to these forecasts. How do businesses and individuals actively use these projections in their own planning?
They use the government's public forecasts, they use their own consultants' forecasts, they listen to the political rhetoric, and they use it all to optimize their outcomes. It creates that complex feedback loop we talked about.
So they're timing asset sales to minimize their tax burden?
Constantly. This is that anticipation effect in action. If an investor is considering a major sale, they're watching the legislative calendar like a hawk,
They'll rush sales in December if a tax hike is scheduled for January 1st.
or delay them until the new year if a cut is pending. They also adjust their portfolio allocation based on the outlook. If they think the LTCG rate is going to stay low, they might favor riskier, high-growth, long-term assets.
Because they know the eventual gain will be lightly taxed, making the risk more worthwhile.
Right. But if the rate is high or volatile, they might pivot to safer, less appreciation-dependent assets like bonds or dividend stocks. They're constantly evaluating their after-tax returns.
And this all feeds directly into their decision between short-term versus long-term holding strategies.
Absolutely. If the difference between the short-term ordinary income rate, let's say 37%, and the long-term rate at 20% is that vast,
That's a 17 percentage point spread.
that is a huge incentive to hold the asset for at least 1 year and 1 day. It creates a kind of forced patience. The investor uses the government's forecasts to make rational, self-interested decisions. And those millions of decisions then fundamentally shape the reality the government is trying to forecast in the first place.
Which brings us to the final and really necessary point of this discussion, the forecasting challenges themselves. Why is projecting capital gains revenue so notoriously difficult compared to, say, income tax revenue from wages?
Well, first and foremost, capital gains revenue depends inherently on factors that just defy precise prediction: asset prices and general market expectations. Asset prices are driven by complex, sometimes emotional and irrational forces, what Keynes called animal spirits. Predicting where the NASDAQ will be in 5 years is impossible. And yet, forecasting LTCG revenue requires a reliable prediction of where asset prices are going.
And second, it's exceptionally difficult to forecast because of financial market volatility and these things called structural breaks in the economy.
A structural break is an unforeseen, paradigm-shifting event: a geopolitical crisis, a global pandemic, the invention of the internet.
Something that fundamentally alters the way markets operate, rendering all the previous historical models partially or wholly obsolete.
Exactly. These events can't be modeled smoothly. They create these discontinuous jumps in the data. And since capital gains are so sensitive to market shocks, a structural break can instantly destroy a multi-year revenue forecast.
And the consequence of all these difficulties is critical. Forecast errors can be severe. We're not talking about missing the target by 1 or 2%.
No, we're talking about catastrophic misses. If the government overestimates capital gains revenue during a policy change, they face huge, immediate revenue shortfalls. That destabilizes the budget and forces emergency cuts or borrowing.
And if they underestimate it,
They risk policy miscalibration. They get the rate wrong. They could be leaving vast amounts of economic growth and potential tax revenue on the table unnecessarily. It is ultimately the highest stakes game of economic prediction there is.
they have to predict market prices, investor psychology, global events, the political climate, all while using the resulting policy to try and guide the economy towards stable, long-term growth. It's a staggering challenge.
That brings us to the end of our deep dive into fiscal forecasts and the long-term capital gains policy. So let's just quickly summarize the critical takeaways for you, the learner.
Okay. We established that long-term capital gains are defined by that critical, sometimes arbitrary, one-year holding period.
Right. And it covers the accumulated wealth in real estate, stocks, and business equity, and offers that lower rate as an incentive for long-term commitment. We then analyze that massive economic tension at the heart of the policy, the trade-off between stimulating long-term growth by reducing a lock-in effect.
And the need to ensure stable government revenue in the short term.
We also detailed how forecasting is used in policy design, distinguishing between static and dynamic scoring, and explaining how models have to predict this really complex investor behavior.
Specifically quantifying the elasticity of realizations and timing that destructive anticipation effect. And finally, we highlighted the profound instability of this revenue stream. Because gains are so highly procyclical, capital gains policy has to ignore that short-term market noise
And rely on a long-run structural economic outlook, despite the severe and inherent challenges of forecasting market behavior and structural change.
Forecasting LTCG is truly one of the riskiest forms of government projection.
It really is. It demands this delicate balance between predicting complex human and market behavior and maintaining critical fiscal health. It's a policy that is constantly trying to stabilize a system that is naturally volatile.
But let's leave you with one final provocative thought to mull over. one that builds entirely on everything we've just discussed about behavioral response and anticipation effects.
We've seen that investors will rush to sell or delay selling based entirely on the anticipation of a future tax change.
Right. Market participants will move billions of dollars just because they expect a policy change is coming.
So, if that's true, does the very act of forecasting revenue and publicly discussing these potential changes fundamentally destabilize and distort the market outcomes the policy is meant to control in the first place?
Does the prediction itself create the instability?
Is the economic forecaster, by necessity, a market disruptor?
That is the question you get to ponder as you look at the complexities of wealth accumulation and government budgeting. Thank you for joining us for the deep dive.
We'll see you next time.
We live in a world that is, well, it's absolutely obsessed with predicting the future. And in policy and finance, we pay professionals a lot of money to do it.
A whole lot.
And just think about the sheer scale of the decisions that hinge on these predictions. Governments are deciding where to spend billions based on projected tax revenues.
Central banks are adjusting interest rates that affect, every single mortgage and business loan in the entire country.
And CEOs are trying to determine whether to break ground on a new billion-dollar factory.
Right. And all of them, every single one, is basing these huge, monumental choices on economic forecasts.
That's really the core tension here, isn't it?
It is. When the Federal Reserve is debating whether inflation is transitory or if it's persistent, or when a major retailer is planning inventory for the holiday season.
Yeah.
They aren't just looking at what happened last year. They're looking at someone's predicted value for GDP growth or the consumer price index 6 months, maybe a year down the line.
So we rely on them, almost implicitly. But here's the central question we really want to get into today. How do we, as, informed decision makers, know if these economic predictions are actually useful?
And that really is the mission for this deep dive. This analysis is built for you, the listener, to go beyond just hearing a forecast number like, oh, GDP will be 2.5%, and to really understand the principles, the technical toolkit, and the critical standards that economists use to judge if that number is worth betting on.
Worth betting serious capital or policy credibility on.
Exactly. It's all about a kind of quality assurance process that happens behind the prediction.
Okay, so to set a baseline, let's start with the simplest definition, right from our source material on forecasting standards.
Let's do it.
Forecast accuracy is defined as how close the predicted value is to the actual observed outcome. So fundamentally, high accuracy just means small forecast errors.
Well, that simplicity sort of hides the colossal stakes, doesn't it?
It really does.
Why does accuracy matter so much beyond getting a good grade in an academic paper? Our sources really emphasize that poor accuracy isn't just a technical fail. It translates directly into extremely costly policy or business mistakes.
Can you give an example of that?
Sure. If you systematically overestimate economic growth, you risk implementing an over-leveraged budget. Or you expand a business right before a major downturn. The financial and societal consequences of relying on flawed predictions, they can be immense.
Absolutely. I mean, if a government agency overpredicts long-term interest rates because of a flawed inflation forecast, they might structure their debt completely inefficiently.
Right. Or a major corporation overpredicts consumer demand, and they invest millions, maybe billions, in inventory or new production capacity that just sits idle. It becomes a massive write-off.
So poor accuracy directly influences policy credibility, which is essential for stable markets, and it just cripples any kind of robust risk management.
Which means the goal here isn't some impossible standard of perfect precision. The goal is reliable guidance. It's about having a clear understanding of the range of potential outcomes.
So today we are going to unpack the specific quantitative measures people use and why just using one is never enough, the unavoidable limitations built into every economic system, and some of those hidden traps.
Oh, like data revisions? That's a mind bender.
Yeah.
It can make a good forecast look terrible and a bad one look good.
Okay, so let's unpack that. If errors are so incredibly costly and if we're all aiming for just reliable guidance, why do we accept that errors are even part of this game? Why can't we just engineer them out of the system?
That's the perfect question to start with, because it sets a necessary realistic expectation. Our sources stress that forecast errors are, simply put, unavoidable in economics. Completely. We're not dealing with a closed mechanical system that's governed by fixed physical laws, like predicting an eclipse. We're dealing with human behavior, global interconnectedness, and systems that are constantly interacting and evolving. The economy is a dynamic, living thing.
So, okay, We have to acknowledge that errors are inevitable. But if we can't eliminate them, then we absolutely need to understand where they come from. So we can diagnose them and, maybe fix the parts we can fix.
Right. What are the primary sources of forecast error?
Exactly.
So we can deconstruct these unavoidable errors into four main sources. And, recognizing which one is dominant in any given period is essential because the solution for each type is totally different.
Okay, what's the first one?
The first source is random shocks. These are the totally unpredictable, external, high-impact events that no model, no matter how sophisticated, could possibly have anticipated.
So things like a global pandemic.
A pandemic is the perfect example. Or a major war that starts without warning. Or even a sudden, catastrophic natural disaster like the 2011 earthquake in Japan that just shut down crucial global supply chains overnight.
Right.
These are pure external forces hitting the economic system from the outside, and they fundamentally alter its trajectory without any warning at all.
So that type of error it's almost an act of God. The model wasn't wrong necessarily. The entire world just changed under its feet.
Precisely. Now, the second source is model misspecification. And this is an internal flaw. This is entirely within the forecaster's control.
Okay.
It means the underlying mathematical structure that's used to represent the economy is either flawed, incomplete, or it's based on economic relationships that just don't exist anymore.
So like assuming a relationship that's broken down.
Exactly.
Yeah.
Maybe the model assumes a really fixed, stable relationship between high unemployment and low inflation, what we historically call the Phillips curve. But that relationship has weakened or maybe vanished because of things like globalized labor markets.
So if the fundamental map of the economy the model is using is wrong, if it misrepresents cause and effect, then the directions it gives you are going to be wrong.
Of course. And this is theoretically something economists can control by refining their models. But as you can imagine, that's often a political or intellectual challenge, not just a mathematical one.
Right. It requires economists to admit that their foundational assumptions might be, obsolete.
And that requires a huge amount of intellectual honesty, a willingness to scrap years of established modeling practice. The third source is often overlooked, but it's critically important. Data measurement error.
So the inputs themselves are flawed.
The input data itself contains inaccuracies. Economic stats like GDP or housing starts or unemployment rates, they are very frequently preliminary estimates. They're collected quickly, and they are subject to later revision.
So even if my model is perfect, if I'm feeding it unreliable data, if I'm measuring with a broken ruler, the forecast coming out is just going to inherit that inaccuracy.
It's the classic garbage in, garbage out problem.
Right.
And finally, the fourth source, which I think is the greatest long-term challenge, is structural economic changes.
This is when the rules of the game themselves change.
Exactly. The economy fundamentally shifts its internal wiring in a way that the existing model hasn't captured. The best modern example is the rapid adoption of artificial intelligence.
How so?
Well, traditional models might assume that productivity gains lead proportionally to wage inflation. But what if AI allows for massive productivity increases without requiring a similar growth in high-skilled labor wages?
Then that foundational relationship just breaks.
It breaks. The stable coefficients that the model relies on become obsolete because the market structure itself has fundamentally shifted.
Okay, so just to summarize, we have the unforeseen events, which are random shocks.
Yep.
The map being wrong, which is model misspecification.
Right.
The input data being faulty, so measurement error. And the entire economic landscape fundamentally changing, which is structural change.
And as we said, the calculation for the error itself is super straightforward. Forecast error equals the actual value minus the forecasted value. If actual annual growth was 3.0% and you predicted 2.5%, your error is positive 0.5%. Simple as that.
So if errors are inevitable, then diagnosing which type of error we're dealing with becomes vital, because the fix is different for each one.
That's it.
You have to hold the forecaster accountable for the errors they can prevent, like a biased model, while being a bit more forgiving of the external shocks they couldn't possibly have seen coming.
And that brings us right back to the crucial usefulness test. Even though we know errors are unavoidable, it's the size and, critically, the consistency of those errors that determine the practical usefulness of the forecast for a decision maker.
I see. A model with huge random errors is basically useless, but a model with small, highly consistent errors, well, that might be salvageable, but only if we can clearly identify and measure that consistency. So to move from these vague ideas of good or bad forecasting, we need to stop talking in general terms and start measuring performance. Precisely.
We do. To judge these errors, we need a sophisticated toolkit of metrics. And this is where it gets really interesting, because using only one measure is like, well, it's like trying to diagnose a complex illness with just a thermometer.
Right. You get one piece of information, but you miss the whole picture.
Exactly. Different metrics highlight different flaws and, importantly, different kinds of risk.
So let's walk through the main quantitative tools. What are the non-negotiables for a serious evaluation? Where does the diagnostic process begin?
You always start by looking for bias, because systematic bias signals a structural failure in the model. And we diagnose this using the mean error, or ME.
Mean error. Okay, what does that specifically isolate?
The mean error simply takes the arithmetic average of all the individual forecast errors over a specific testing period. Its result is a diagnostic tool designed exclusively to detect systematic directional bias.
So if it's consistently positive or consistently negative?
That's your red flag. If over, say, 20 forecasts, the positive errors, the underpredictions, consistently outweigh the negative errors, your ME will be consistently positive. Maybe it's plus 0.3%. That tells you your model is structurally leaning. It is systematically missing the target in one specific direction.
Which suggests the model is either constantly applying the wrong foundational assumption, or maybe there's even a kind of conservative or optimistic slant built into the human judgment overriding the model. The ME tells you the center of the model's target is misaligned.
Precisely. So if you're a policymaker, an unbiased ME1 that's close to zero is step one. It means your model is right on average. But, and this is a huge but, the ME doesn't tell us anything about the magnitude of the individual errors.
Right. I think you mentioned this earlier. If you underpredict by 5% one quarter and overpredict by 5% the next, your mean error is 0.
Exactly. It suggests a perfectly unbiased model. But you were spectacularly wrong both times. You just got lucky that the massive mistakes canceled each other out.
Which means we need a different metric that focuses purely on the size of the error and ignores whether it was positive or negative.
And that is where we bring in the mean absolute error, or MAE.
How does MAE filter out that directionality?
Well, MAE measures the average magnitude of the errors by treating all errors, whether they were positive or negative, as if they were positive. You take the absolute value of every single error, you sum them all up, and then you divide by the total number of forecasts.
Okay, so that's very straightforward. It's useful for communication. If my MAE is 0.5 percentage points, I can tell my stakeholders, on average, our forecasts were half a percentage point away from the actual outcome.
It's very easy to interpret. It gives a clear picture of typical performance, which is why it's so popular. But now we have to introduce the concept of risk management. Because not all errors are created equal, are they?
No. A forecast that's wrong by 1% might be okay. But a forecast that's wrong by 5% could trigger a financial crisis or a massive operational collapse.
Right. And to evaluate that kind of risk, we need a different mathematical approach. The mean squared error, MSE, and its widely used cousin, the root mean squared error, RMSE.
Okay, this squaring of errors is the part that can be a bit counterintuitive for someone who isn't deep in statistics. Why do we add this mathematical complexity?
The MSE introduces a vital principle in risk assessment. It disproportionately penalizes large errors. Think about it. If your model misses the target by a tiny bit, say 0.1, squaring that error results in 0.01. And if it misses by 10 times that amount, 1.0, squaring it results in 1.0.
So that larger miss is penalized 100 times more heavily than the smaller miss.
Exactly. So if I'm a financial regulator or a risk manager at a big investment bank, I care deeply about avoiding that one single massive outlier, that catastrophic miss. MSE is the metric I would prioritize because it forces the model designer to focus on eliminating those high leverage failures.
So it's a trade-off. It effectively tells the model builder, we will accept a few small random errors, provided you get rid of the really massive ones. The model gets optimized not for average closeness, but for avoiding disaster.
That's the perfect way to put it.
But let's go back to the unit problem. If I'm forecasting inflation in percentages and my MSE comes out as, say, 0.49, what does 0.49 squared percentage points actually mean to a CEO? It's mathematically powerful, but it's conceptually abstract.
That is precisely the Achilles heel of the MSE. And it's exactly why the RMSE is the metric you see cited most frequently. The root mean squared error just takes the square root of the final MSE value.
And by taking the square root,
it does two essential things at once. First, it brings the measurement back to the original units, percentages, dollars, whatever you were forecasting. If the MSE was 0.49, the RMSE is 0.7. Now you can tell the CEO, Our average error weighted heavily against outliers is 0.7 percentage points. Much clearer.
Okay, that's interpretable. And the second thing?
Second, because it's derived from the MSE, it still retains that heavy penalty on large errors. So our MSE brilliantly combines the mathematical rigor of risk assessment with the interpretability of the MAE.
That's a crucial distinction. This whole toolkit, ME for bias, MAE for average magnitude, and RMSE for risk-weighted interpretability, it ensures we're judging the model from multiple angles. Which leads us to that crucial conceptual point about what good even means. We have to talk about bias versus precision.
Yes, this relationship is absolutely fundamental. They sound similar, but they describe two very distinct critical characteristics of performance that, don't always align.
So let's define them.
Okay, a forecast is considered unbiased if, over a long period, the individual errors average out to zero. It might be too optimistic one quarter, too pessimistic the next, but the mean error is basically negligible. There's no systematic directional lean.
And a forecast is precise if the individual errors are consistently small. The predicted numbers cluster tightly around the actual outcome every single time. Low variability.
And the paradox comes in because it is surprisingly common to achieve one of these without the other. And a truly useful model has to aim for both. Let's use that dart player analogy again, but let's push it into the policy realm.
Okay, let's start with the player who is unbiased but imprecise.
Right. This player is fundamentally chaotic. Their darts hit the board all over the place, rarely near the center. But the mathematical average of all their throws lands right on the bullseye. They are right on average, but no single prediction is actually useful.
So this represents a model with high variability but low systemic error.
Exactly. And if I'm a policymaker trying to use this model for short-term intervention, this forecast is useless. I have no confidence in the single number they give me, even though I know they'll be right in the long run.
Okay, now contrast that with the player who is precise but biased.
This player's throws all cluster together very tightly, maybe within a 1 centimeter radius. It shows great technical skill, low variability. But that tight cluster lands consistently 2 inches to the upper left of the bullseye.
So they're consistently making small errors, but they are consistently wrong in the same direction. High precision, but high systemic bias.
Right. For a central bank, this would be like constantly under-predicting inflation, but always by a small, consistent amount.
So here's the substantive challenge for you, the listener. Which one of those is worse? If you're the policymaker, is the precise but biased model actually worse than the unbiased but imprecise one?
That is a brilliant question.
With the unbiased but imprecise model, I can't trust the number at all. It's a total gamble. With the precise but biased model, I know exactly where it's going to be wrong every time. I could, theoretically, just adjust my aim.
You could. If you know the model always predicts 0.5% lower than reality, you just add 0.5% to every forecast it gives you.
So the precise but biased model, as long as that bias is stable and we've identified it,
which the mean error helps us do.
It's actually highly valuable because you can adjust for that systemic error. The unbiased but imprecise model, with its high variability, it's just pure noise.
That's it. It really emphasizes that good forecasting aims for both low bias and high precision. But if you have to choose, high precision, coupled with a correctable bias, is often much better than high variability, even if that high variability model is technically unbiased.
Wow, that is a deep insight. And it really underscores why just checking the ME once is not enough. You have to combine the ME to find the center of that dart cluster with the MAE or RMSE to check the tightness of the cluster to truly get the model's practical utility.
Any evaluation process that ignores either precision or bias is just. It's failing to provide the full picture that you need for high-stakes decision-making.
It sounds like achieving both unbiasedness and precision requires immense sophistication, a ton of data, and continuous tuning. But how do we know if all that effort is even justified? Why bother building a multi-million-dollar econometric model if we can't prove it's better then? Well, just guessing.
That is the core philosophical and, frankly, practical challenge of the discipline. It's often called the benchmark test. And the principle is simple. Forecast accuracy is never evaluated in a vacuum. It must be relative to a standard that is simple, cheap, and easy to calculate.
And if your fancy, complex model can't measurably outperform the simplest possible prediction,
then it is just expensive noise, and it should be thrown out.
So what are these simple benchmarks?
We mandate the use of two fundamental, basically zero-effort benchmarks that any serious economic model has to outperform. just to justify its own complexity.
Okay, let's detail the first one. This is the ultimate low bar.
The first is the naive or no change forecast. This is simplicity itself. You just predict that the outcome tomorrow will be exactly the same as the outcome today. If the unemployment rate was 4.0% last month, the naive forecast says it will be 4.0% this month.
And that actually works sometimes.
In many short-term financial markets, this random walk approach, assuming tomorrow's price is today's price plus a bit of noise, is surprisingly hard to beat. If your sophisticated model can't get a lower RMSE than this simple rule, it's useless.
Okay, what's the second benchmark? It's slightly more informed, but still requires almost no effort.
That's the historical average. Here, you just predict the long-term average value for that variable. If the average inflation rate over the last 30 years has been 2.5%, you predict 2.5% for the next year. This works exceptionally well for economic variables that tend to revert to a mean over time.
This sounds brutally simple, but I seem to recall that in the history of this field, there have been periods where highly complex state-of-the-art models were routinely beaten by these simple averages.
Absolutely. The need to establish these benchmarks came directly out of those humbling historical failures. Complex models often fail because they try too hard to find patterns in what is essentially noise. They overfit or they react too sharply to small, transient changes that quickly just revert back to the average.
So the simple benchmarks serve as a vital check on hubris.
They do. The sophisticated models, the ones with hundreds of variables and complex simulations, must show a statistically measurable improvement in accuracy, a significantly lower MAE or RMSE compared to these zero-effort benchmarks.
And that raises a crucial question for you, the listener, especially if you're commissioning these forecasts. Is the complexity and the massive cost of a sophisticated model worth the marginal gain in accuracy?
Right. If the complex model only lowers the RMSE from 0.8 down to, say, 0.7, that tiny improvement might not justify the immense resource expenditure. You have to weigh the marginal utility against the marginal cost.
And beyond that, how do we make sure the model isn't just a very good historian? How do we prevent it from simply memorizing the answers to the test rather than learning the principles?
That issue is called overfitting, and it's a danger in any statistical modeling, not just economics. It's like a student who is taught only the specific questions on the final exam, they'll get a perfect score.
But if you give them a new test on the same subject, they fail because they never learned the underlying concepts.
And that is exactly why out-of-sample evaluation is considered absolute best practice. This technique is designed specifically to prevent that overfitting problem.
And overfitting is insidious, right? Because it makes the model look fantastic on the historical data.
It looks perfect. It can perfectly explain the past. But when you present it with genuinely new information, the future, it just collapses. It can't generalize its findings.
So how does out-of-sample testing solve this? What are the actual mechanics of the test?
Well, the process is meticulous. When the economist is developing and calibrating the model, they deliberately hold back a significant portion of the most recent data, say the last 2 or 3 years. The model never sees this data during its learning phase.
So it's trained on an older data set.
Right. And once the model is finalized, its accuracy is assessed only by testing its predictions against this withheld, unseen data.
That perfectly mimics real forecasting conditions, because in reality, you never have future data when you're making a prediction today.
Exactly. It forces the model to prove its ability to generalize relationships, not just repeat historical coincidences. It's the gold standard because it ensures the measured accuracy is based on the model's ability to forecast true novelty.
And what's the warning sign?
If the out-of-sample RMSE is significantly higher than the in-sample RMSE, you know the model has been overfit. You have to go back, simplify it, and retrain it.
So if we follow all these rigorous methods, beating the benchmarks, avoiding overfitting, is there a guaranteed time limit on reliability? Can I trust a 3-month forecast for inflation as much as a 10-year forecast for GDP growth?
Fundamentally, no, you can't. You're dealing with what's called the horizon effect, and it's just an unavoidable reality in dynamic systems. Accuracy fundamentally and predictably declines as the forecast horizon increases.
So the longer the prediction window, the wider the range of possibilities becomes.
Much wider. Think about the difference between predicting your own weight next week versus predicting global population growth 50 years from now. The shorter the horizon, the fewer opportunities there are for those random shocks or structural changes we talked about to accumulate and completely derail the prediction.
Okay, so short-term forecasts, say 1 or 2 quarters out, are generally more accurate because the current economic structure, the policy regime, the existing momentum, it all still dominates the outcome. There's a high degree of inertia.
Exactly. But as you move to long-term forecasts, several years or even decades out, the predictions become exponentially more uncertain. And at that horizon, the forecast result is less dependent on the immediate data and much more heavily influenced by the structural assumptions that are built into the model.
For example, a long-term forecast relies almost entirely on assumptions about things that are inherently hard to predict, like what will the rate of immigration be? How quickly will new environmental regulations be implemented? Will productivity growth stay strong?
Yes, all of those. If the model assumes a stable demographic trend for the next 25 years, and then a major global migration shift occurs because of conflict or climate change, that long-term forecast, which was based on the old assumption, instantly becomes useless.
Because the structural assumptions dominate the outcome, and those assumptions are inherently fragile.
Right. And this gives the listener a direct application. You must always align the forecast horizon when the prediction is for with your decision needs when you need to act. Don't use a highly uncertain 20-year projection to make a short-term trading decision.
And don't use a high-confidence 3-month inventory forecast to plan long-term infrastructure investment. The uncertainty has to match the duration of the risk you're taking on.
Which brings us to one of the most intellectually confusing and practically devastating problems of this whole field. This is where it gets truly mind-bending. Sometimes the forecast looks dead wrong because the actual number was, say, X. But then 6 months later, the government statistical agency revises its figures and says, actually, our initial estimate was wrong. The real number was Y.
So the target itself changed after the forecaster took their shot.
The target moved. This is the critical problem of data revisions, and it complicates the accuracy landscape massively.
Tell us exactly why this happens and what the impact is.
Economic data, especially high-frequency data like quarterly GDP or inflation, are often preliminary when they're first released. They rely on partial, incoming survey responses. So government agencies like the Bureau of Economic Analysis in the U.S. collect more comprehensive information over time, tax data, customs records, updated census results, and they subsequently revise those initial estimates, sometimes substantially.
Can you walk us through a scenario?
Sure. A forecaster makes a prediction for Q1 GDP based on all the data they have in March. They predict Q1 will be 3.0%. The initial flash estimate for Q1, released in April, comes in at 2.5%.
And the media jumps all over the forecaster, saying they missed by 0.5 percentage point.
Exactly. But then a year later, the final, comprehensively revised Q1 number comes in at 3.1%.
Wow. So suddenly the original forecast of 3.0% was almost perfect.
Almost perfect. The forecast only appeared inaccurate because the comparison point, the actual value, later changed due to revisions. If you evaluate accuracy using the final revised data, you're essentially punishing the forecaster for not being able to predict the future revisions of government statisticians.
Which is a completely unfair and impossible requirement.
It's a huge methodological challenge. How do we properly evaluate accuracy in this environment where the historical truth is constantly being rewritten?
Do we just ignore the final best data available?
No. But you must adopt the standard of using real-time or vintage data for evaluation. You have to use the data that was actually available to the forecaster at the moment the forecast was made.
So you compare their March forecast for Q1 to the Q1 data as it was initially released in April.
And their Q2 forecast to the Q2 data as it was released in July, and so on. This requires meticulously tracking data vintages, which is a very time-consuming process.
Are there resources for that?
Yes. Agencies like the Philadelphia Fed maintain databases specifically for this purpose. Furthermore, evaluators need to be aware of revision bias. Do initial estimates consistently tend to be higher or lower than the later final figures?
Is there a known consistent bias in, say, initial GDP reports?
Yes. Historically, for certain data releases, yes. Understanding that initial releases might, for example, systematically overestimate growth by an average of 0.1% because of the speed required for reporting, that becomes crucial context. It means the target isn't just fluctuating, it might be predictably skewed from the start.
So a sophisticated model really needs to forecast the true economic value, not the statistical agency's first flawed estimate of that value.
A very difficult task.
So even if we minimize the forecast error through brilliant modeling and careful use of real-time data, the number the forecaster gives me is still just a single point. If they predict 3.0% GDP, should I really be planning for exactly 3.0%?
That single number, the point forecast, is what the media and the public crave because it's simple and it's decisive. But it completely masks the true complexity of robust forecasting, which is built entirely on probability. We have to differentiate between the point forecast and prediction intervals.
Okay.
A single point forecast gives you the most statistically likely outcome, the median or the mean of the model's projected distribution. But a robust accuracy assessment has to include prediction intervals and the full probability distribution,
And a prediction interval tells the decision maker the range of likely outcomes.
often with a stated level of confidence, like 70% or 90%.
So instead of a central bank only saying, we predict 3.0% growth, they should be saying, we predict 3.0% growth, but with a 90% confidence interval that the outcome will fall somewhere between 2.2% and 3.8%.
And that range, that interval, is where the critical practical insight really lies. It emphasizes that understanding uncertainty is often far more important to a decision maker than simply minimizing the error on that single point.
Right. A policymaker setting debt levels or a business planning for a capital raise doesn't need the exact point. They need to understand the risk.
They do.
If my business is planning a major investment, knowing the point forecast is a healthy 3.0% doesn't tell me what I really need to know about the tail risk. Knowing there's a 5% chance the outcome will be negative, leading to a recession, that's the information I use to structure my emergency reserves.
The point forecast completely fails to capture that low probability, high impact risk.
So that's the ultimate takeaway for anyone using forecasts.
I think so. Decision makers need to know the probability density of those extreme outcomes. A model that's slightly less precise on its point estimate, but gives you robust, well-defined prediction intervals, is often exponentially more valuable than a model that just focuses on getting the lowest RMSE on its single prediction.
The accuracy measure has to capture the quality of the entire probability distribution, not just the quality of its center point.
Absolutely.
We've identified the errors, the essential metrics, the comparison benchmarks, the data traps. Now, if the limits are fundamental and errors are inevitable, what are the actionable strategies the experts use to try and get better? How do you push against that ceiling of forecast accuracy?
There are 4 primary documented strategies for enhancing accuracy, and many of them involve accepting the inherent weakness of any single method and instead opting for a kind of systemic diversity.
Okay, what's the first one?
The first, and arguably the most statistically effective strategy, is combining forecasts. This is the practical application of the wisdom of crowds principle. You use the outputs from multiple, often structurally different, models. Instead of picking one best model, you average the predictions of 3 or 4 different ones.
But why does averaging independent models usually outperform even the best individual model? That seems a little counterintuitive.
Well, the statistical magic is that different models inevitably have different idiosyncratic errors and biases. Model A might be great at forecasting consumption, but poor at forecasting investment, and Model B might have the opposite flaw.
I see.
When you average their outputs, the unique, non-systemic errors of each individual model tend to cancel each other out, pushing the average closer to the true value than any single forecast could achieve reliably.
So the diversity of the modeling approach acts as a statistical hedge against the unique failings of any single map of the economy.
Precisely. The second strategy is simply, but it's foundational. Regular updates. Models need to be consistently refreshed with the newest data available. In a rapidly changing environment, using data that is only 3 months old is already a huge disadvantage.
So if a model isn't refreshed frequently, it quickly starts modeling a version of the economy that just doesn't exist anymore.
It becomes a historical artifact. The third strategy addresses those structural challenges we talked about earlier, and that is monitoring structural changes. This is where the economist acts less like a pure engineer and more like a social scientist. They have to be vigilant, constantly observing fundamental shifts, like the sudden rise of remote work or a persistent change in consumer saving habits, and then adjusting the model's core relationships accordingly.
Which prevents the model from continuing to rely on relationships that have been fundamentally broken by innovation or social change.
Yes. And finally, a strategy that takes us back to the foundations of economic thought. Ensuring the model has a strong intellectual footing. This is using theory guidance.
What does that mean in practice?
It means the model shouldn't just be a complex statistical black box that finds high correlations between random variables.
Right.
That can lead to what we call statistical ghosts or spurious correlations.
Right.
It has to be guided by established economic theory during its initial design. This ensures that the relationships the model identifies are economically plausible and structurally stable, not just statistical accidents that happen to hold true for a specific historical period.
So theory gives the model a conceptual skeleton, and it prevents it from wildly overreacting to noise.
That's a great way to put it.
But despite all of these rigorous efforts, combining models, constant updating, structural monitoring, we keep coming back to the fact that errors are unavoidable. What are the hard fundamental limits? What is the absolute ceiling on how accurate economic forecasts can possibly be?
It is so essential for both forecasters and the people using the forecast to be realistic about this. We have to acknowledge these fundamental limits. Economists are not astronomers predicting the trajectory of a known comet. They are trying to predict the outcome of billions of individual human decisions interacting within a constantly changing global system.
So what's the first limit?
The first limit is systemic complexity and non-stationarity. Economic systems are simply too vast, too interconnected, and their underlying behavioral rules are too constantly evolving, or non-stationary, to be modeled perfectly. Human behavior is nonlinear, and it's subject to psychological factors, sentiment, expectation bubbles, things that resist being fully captured by even the most sophisticated math.
And isn't the system also self-referential? Our predictions themselves can change the behavior of the people we're trying to predict.
Oh, absolutely.
If the Fed predicts low inflation, that prediction might cause consumers to behave differently, which ultimately changes the outcome.
It's a huge problem. The economy is reactive to its own predictions, which introduces a layer of fundamental uncertainty that engineering or the physical sciences just don't have to face. And the second most decisive limit is the existence of unanticipated shocks.
The black swans.
The black swans. Unforeseen massive events, a sudden sovereign debt crisis, a war that cuts off critical energy supplies, a rapid technological breakthrough that destroys entire sectors. These act as unpredictable external forces that fundamentally derail any existing model structure. By their very nature, these shocks cannot be predicted by models based on historical relationships because there is no prior data to train on.
So these two factors, inherent complexity and unpredictable shocks, they mean there are fundamental limits to how accurate forecasts can be, regardless of how much computing power or how many combined models we throw at the problem.
We just have to accept that aiming for perfect foresight is a futile endeavor.
We've covered the metrics, the necessity of benchmarking, the data traps that can confuse the results, and the fundamental, irreducible limits to accuracy. We started by saying that poor accuracy leads to costly mistakes, which is why transparency in forecasting is so essential for decision makers.
And if we connect all this knowledge to the bigger picture, understanding these rigorous measures allows you, the listener, to critically assess any economic prediction you encounter. You now know not only what the predicted number is, but whether the model that generated it is unbiased, precise, and crucially, how its accuracy was actually measured.
Right. Was it tested out of sample? Was it benchmarked against a naive forecast? Did they account for the vintage of the data they were using?
All those critical questions.
This deep dive really shows that accuracy in economic forecasting isn't just about being right. It's fundamentally about understanding the probability of being wrong, reducing the errors you can control, and transparently communicating the irreducible uncertainty to the people who need to act on the information.
The focus should always be on rigorous methodology and transparently providing the decision maker with the full probability distribution so they can manage their own risk tolerance.
And if we accept that unanticipated shocks fundamentally limit the maximum possible accuracy, and if we know that understanding prediction intervals is more useful to a policymaker than the single-point forecast, this raises a really important question for all of us. When is providing a specific point forecast, say GDP will be 2.8%, actually a disservice to the public and to business compared to providing a detailed probability distribution? What does the deep-seated desire, driven by media and political demand, for a single, easy-to-digest number cost us in terms of preparedness for the inevitable uncertainty of the future? You know, when you look at the global economy, it feels like this permanent exercise in managing massive, just unimaginable uncertainty. We see central banks, raising and lowering rates. Governments are committing trillions to these huge spending plans. And then you have corporations betting billions on what's next.
And they're all doing it based on a future that, deep down, they know they can't predict with any real certainty.
Exactly. It feels less like careful navigation and more like a high-stakes poker game where the rules just keep changing on you.
Oh, absolutely. And I think the institutions playing that game, they learned a long, long time ago that betting the farm on one single prediction is just a recipe for disaster.
You're right.
So today we're doing a deep dive into the architecture that lets them manage that uncertainty. It's called Economic Scenario Analysis.
Economic Scenario Analysis.
Yeah. It's this really sophisticated structured forecasting tool that's designed precisely to navigate that kind of risk. It's all about ensuring you're resilient no matter what the future actually looks like.
And that is our mission today, listener. You sent over a fascinating stack of sources on this whole methodology, how it's built, who's using it, and maybe most importantly, where its blind spots are. So we're here to give you the shortcut. We're going to unpack exactly how this structured thinking works, what its building blocks are, and why it's considered so much better than just, hoping your single best guess comes true.
And we can actually state the core takeaway right at the top, I think. It frames the whole discussion.
Okay, let's do it.
Scenario analysis. It's not really focused on prediction. It's focused on evaluation.
Evaluation.
Right. It's a tool for evaluating alternative future economic outcomes. You do that by looking at multiple plausible scenarios instead of just relying on that one single kind of fragile prediction.
So the goal isn't precision.
The goal isn't precise prediction. The goal is robust planning.
Robust planning. That distinction feels like everything, especially when you're talking about high-stakes finance or policy, where one wrong bet could, collapse a bank or tank a whole national budget.
Precisely. If you just internalize that one goal robustness, then you understand why this whole framework even exists.
Yeah.
We're looking for plans that still work even when the world, doesn't cooperate.
Okay, let's unpack this architecture then. Let's start with the foundational mechanics of it all.
Sounds good.
So let's get into the nuts and bolts. We use this word scenario, but what is that, mechanically speaking? For an economist or a financial planner, what's the actual architecture of that story?
That's a great place to start. Mechanically, a scenario is so much more than a spreadsheet. It's really a detailed, self-contained narrative about the future economy.
A narrative. A story.
Exactly, a story, usually over a timeline of, say, 1 to 5 years. And it reflects a complete set of assumptions about all the key economic drivers.
So you have to think of the economy like a big machine with all these interconnected levers.
That's a perfect analogy. You've got monetary policy, fiscal spending, consumer behavior, global trade, dozens of levers. A single scenario is basically one specific, consistent setting for all of those levers at once.
So it's one plausible story of how inflation behaves, what interest rates do, how the labor market reacts, all happening at the same time.
All happening at the same time in response to some kind of initial shock. It's not just a collection of numbers. The critical part, like you said, is that it has to be a cohesive, believable story that holds up to what we know about economic cause and effect.
And the main purpose of running all these different cohesive stories, why go to all that trouble?
The primary purpose is really singular and focused. It's to manage deep uncertainty and systemic risk in these high-stakes decisions.
Okay.
By mapping out not just the path you expect, but also these other plausible adverse paths, you force yourself to understand the whole spectrum of threats and opportunities. It makes decision makers prepare for outcomes they might have otherwise just dismissed as, it's too unlikely to worry about.
So the output isn't really a forecast. It's more like a map of how resilient your institution is.
That's it, a map of institutional resilience.
And your sources highlighted 3 major categories of disruption that this kind of analysis is specifically designed to assess. We should probably detail those because they show the sheer scope of what these big institutions are worried about.
Yeah, these 3 categories cover almost everything that can just completely derail your plans. The first one is economic shocks.
Economic shocks.
Right. These are sudden, severe, and usually external changes that just throw your main forecast way off track. We're not talking about little bumps in the road. We mean large, immediate events.
Okay, can you give me a concrete example, something recent that would require an immediate scenario test?
Sure. Think back to the sudden spike in inflation we saw globally after the pandemic, or that initial, really unexpected energy price spike after the conflict in Ukraine started.
Right, those were huge.
They were. There were supply-side shocks mixed with demand changes. So an analyst running a scenario on that might model a sudden, say, 30% increase in the price of global commodities, oil, steel, food, and then just track that effect through the whole system.
So what does it do to production costs, to consumer spending, to profits for businesses?
Exactly. The scenario analysis is testing how resilient a company or even a government's budget is to that one specific jolt.
Okay, and then you have the moves we make on purpose, the policy changes. This is where a central bank or a government decides to step in, and that can have really unpredictable side effects.
That's the second category.
Yeah.
It deals with the impact of government or regulatory actions. And while these are technically controlled by policymakers, the economic outcome of those actions is hugely uncertain.
Right.
For instance, what if a government suddenly implements a massive, unexpected tax reform, let's say a huge tax on carbon emissions that just fundamentally restructures the entire energy sector? Scenario analysis lets them test the consequences of pulling those powerful levers before they actually do it.
Or, maybe even more common, the dramatic actions of a central bank.
Correct. The core of this category is all about interest rate scenarios. What if a central bank, seeing some scary inflation data, just executes a rapid, severe rate hiking cycle?
Something like 500 basis points in 18 months instead of the 200 the market was expecting.
Exactly. The scenario models how that sharp increase in borrowing costs just ripples through the housing market, corporate debt, capital investment, everywhere. Decision makers use it to see if the policy fixes one problem, like inflation, but ends up causing two worse ones, like a recession and a credit crunch.
And that third category, that deals with the fragility of the financial system itself, right? Market disruptions.
Yes, these can be systemic failures or just periods of intense disruptive volatility that start inside the financial markets.
So something like a sovereign debt crisis.
A sovereign debt crisis is a perfect example. A large industrialized nation defaults, and it sends absolute chaos through the global bond market. Or for a bank, a scenario might be a sudden deep drop in the stock market combined with a massive run on regional banks, completely freezing up liquidity.
So a bank running a scenario like that might be testing its capital against, say, a 50% drop in bond values and a 30% drop in the housing market happening at the same time.
Precisely. They are testing their institutional resilience against those specific multifaceted threats. They want to make sure, for example, that they have enough capital to weather those extreme drops in asset prices and people pulling their deposits, all without needing a government bailout.
So it all comes back to what you said at the start. It's robust planning, not just hoping a crisis won't happen.
It's always about robust planning.
Okay, so this foundational idea of scenarios brings us to this really crucial distinction. The difference between what analysts do every day, making a forecast, and what scenario analysis actually adds to the picture. Let's talk about the traditional point forecast first.
The point forecast it's the bedrock of mainstream economic prediction. It's what most of us think of when we hear the word forecast.
The single number.
The single, solitary, most likely outcome. It's the analyst's best single guess, based on all the current data and models of where a variable will be at a certain point in time. We predict U.S. GDP will grow by 2.1% next year, or the S&P 500 will close at 5,500 by year end.
It gives you a lot of clarity, but what's the inherent fragility of relying only on that single precise point?
The fragility is profound, really. The world rarely, if ever, delivers the single most likely outcome.
Right.
It delivers one of 1,000 less likely outcomes that, collectively make up the other 99% of probability. Economic models, as smart as they are just imperfect maps of a super complex world.
So if you base your entire multi-year investment plan or your whole national budget on that one single number,
and reality deviates even a little bit, say GDP hits 1.9% instead of 2.1%, your entire plan is instantly compromised. Or worse, it's just completely irrelevant.
That's the classic risk, isn't it? Optimizing for one outcome versus preparing for many. You optimize for 2.1% growth, but you fail spectacularly if you get 1.9%.
Exactly. It's the difference between trying to hit a tiny bullseye and just preparing for everything else on the target.
Yeah.
If you only rely on that single point, you are by definition structurally unprepared for any deviation.
So this is where scenario analysis comes in to explicitly address that fragility by shifting the focus.
It does. It contrasts with the single point forecast by focusing on providing a range of possible outcomes. So instead of betting everything on that 2.1% GDP growth, scenario analysis systematically maps out what happens if GDP hits 4% the upside, or if it shrinks by 1% the downside.
Or if it stays stable but inflation just explodes.
Right, a targeted scenario. The core function is asking these deep what-if questions. You're exploring the boundaries of what's possible rather than just trying to perfectly identify the center.
It's an explicit recognition that the error bars on any economic forecast are just enormous.
They're huge.
Yeah.
And so you have to stress test your plans against those error bars.
But help me get the relationship clear here, because it sounds a little contradictory. If the forecast is that fragile, why don't scenarios just replace traditional forecasting altogether?
That's a really common misconception, and one we need to clear up based on what these institutions actually do. Scenarios complement point forecasts. They don't replace them. They work together. Think of them as two parts of a single risk structure. The point forecast, that establishes your expected path. It's the destination you're aiming for, built on consensus assumptions and current trends.
And the scenarios define the boundaries of how you might deviate from that path.
Precisely.
I see. So the point forecast is the map to your target, the one path you hope to take. But the scenarios are the detailed diagrams showing what happens if you hit a landmine on the way or maybe find a shortcut.
That's a perfect way to put it. You need the map, because you still need a target to aim for, but you need the danger assessment even more because you spend most of your time navigating potential problems.
Right.
Scenario analysis lets you assess not just how likely you are to hit your target, but more importantly, how bad it will be if you miss it in any plausible direction. It moves your planning from just, linear expectation to multidimensional preparedness.
Okay, that focus on preparedness must force people to limit their scope. I mean, if you could build an infinite number of scenarios, you'd just get stuck, right? You'd never get any work done.
Analysis paralysis, it's a real threat.
So moving into our next section here, let's look at the structure they impose on this. What are the best practices for limiting the number of scenarios to something manageable?
Yeah, that's a key piece of best practice, and it's rooted in just operational reality. You have to limit the number of scenarios to a manageable set. Usually something like 3 to 5 core scenarios.
And you have to make sure those few stories cover the whole spectrum of possibilities.
Exactly. And that typically includes a central path and then the 2 major bookends of what could happen.
And the essential starting point for that set is the anchor, right? The path of least resistance, the baseline scenario.
Correct. The baseline scenario is the foundation. It's the anchor for everything else. It is built entirely on the most likely economic outlook, which comes from that consensus point forecast we were just talking about.
So it takes all the currently announced policies, like if the central bank has signaled a certain rate path, and it just assumes normal economic operation.
Yes. It explicitly avoids any major unexpected shocks. The baseline is the world as we currently anticipate it. It sets the context for measuring the impact of all the alternative stories.
Which makes sense. It's the scenario that you compare everything else against.
Exactly. If the impact of your pessimistic scenario isn't that much worse than the baseline, well, then your organization is pretty resilient. But if your upside scenario doesn't give you much better results than the baseline, your growth strategy might be too timid.
Okay, now for the extremes. The crucial bookends that define the boundaries of what could happen and are so essential for real risk management.
Right. The essential counterpoints are the optimistic, or upside scenario, and the pessimistic, or downside scenario.
Let's start with the upside.
The upside is defined by a highly favorable economic outcome. This could involve unexpected leaps in productivity from a new technology, or a sudden boom in global trade, or maybe fiscal stimulus that proves way more effective than anyone forecasted. It's the everything breaks right scenario.
Sustained high growth, but without runaway inflation. The dream scenario.
The dream scenario. But then you have the pessimistic scenario, and that's the true stress test, the one that central banks are really worried about.
Absolutely. The downside scenario is the most critical one for survival. It's defined by recession, significant financial stress, and adverse shocks. And because this scenario is used to test resilience, it has to be pretty severe.
Right. It might include simultaneous geopolitical crises, a severe and sustained energy shortage, or the failure of a major financial institution that causes credit markets to just seize up.
So asset prices plummet at the same time.
Everything goes wrong at once.
How does an analyst make sure their downside scenario is severe enough to be useful, but still, plausible? That seems like a tough balancing act.
It is a challenge. Often, regulatory bodies actually mandate the severity. For example, the Federal Reserve stress tests might require banks to model the effects of unemployment rising to 10% and commercial real estate prices falling by 40%. The event itself might have a low probability, but its mechanics have to be economically plausible. The variables need to move together logically to tell a coherent story of severe economic stress. You have to model the worst plausible outcome to make sure you don't run out of capital when it really matters.
And beyond the standard 3 baseline, upside, downside, you mentioned there are also these highly targeted scenarios. They're designed to isolate and test specific factors that might not be systemic, but could still be lethal to a specific organization.
Yes, those are the policy or shock scenarios. They're built specifically to isolate and test your resilience to one concentrated threat. You use these when you're mostly concerned about a single massive input change.
What's a good example?
You might have a scenario that's focused purely on interest rate changes. You could model a sudden massive rise of, say, 500 basis points over 6 months.
Far beyond any reasonable expectation.
Far beyond. But you do it just to see what that extreme policy shock does to your balance sheet. This would be absolutely crucial for a mortgage lender or any institution holding a lot of long-term bonds.
Or they could model drastic fiscal moves, I imagine.
Exactly. Tax reforms. Major, unexpected changes to fiscal policy, like getting rid of specific corporate deductions or introducing a nationwide wealth tax. The point is to measure the isolated, nonlinear effect of that single, massive policy change without all the clutter of other shocks happening at the same time.
And finally, the external events that are always kind of looming over every economy.
The external shocks. These scenarios model events that start completely outside the domestic economy. Things like geopolitical crises, a major new pandemic, or resource shortages, like a sudden global food price spike because of crop failures or climate events.
Right.
A government needs to know what a 50% spike in global energy costs, driven purely by a foreign conflict, does to its domestic inflation and its budget deficit. These targeted scenarios are vital because they force you to understand your single-factor vulnerabilities before you start mixing all the variables together.
So the scenarios are the story, but the variables are the words you use to write that story. And this is where the complexity just explodes, right? Because analysts aren't just adjusting one number. They're moving a whole bunch of levers at the same time and making sure they all line up.
That's right.
So which are the essential interconnected variables that analysts have to adjust together to build one of these consistent scenarios?
The sources identify 6 essential levers that, collectively define the state of the economy. And they have to be adjusted simultaneously because they're all causally linked.
Okay, what are they?
They are GDP growth, inflation, interest rates, employment, exchange rates, and asset prices. To build a downside scenario, for instance, you have to vary your assumptions about all 6 of these, and you have to make sure the variation tells a cohesive story.
Let's spend some time on that interdependence because this really feels like the art of scenario construction. Why can't you just adjust, say, GDP growth and leave everything else the same?
Because that would be an economically nonsensical scenario. It's
Yeah.
just not how reality works. The economy operates in cascades.
So let's use an example. Let's start with GDP growth, the measure of output. If we're building a downside scenario where GDP growth turns sharply negative, what are the mandatory chain reactions for the other variables?
Okay, great. So if GDP contracts sharply, a recession, you must immediately adjust employment. Unemployment will spike, and wage growth will slow down or stop completely as companies lay people off and freeze hiring.
And that lack of demand.
That lack of demand means you also have to adjust inflation. Unless there's a huge simultaneous supply shock, inflation should fall sharply or maybe even turn deflationary just because consumers have stopped spending money.
Okay, so our recessionary scenario now has low GDP, high unemployment, and low inflation. What does the central bank do in this story?
The central bank has to react. So in response to low inflation and a recession, interest rates must be modeled as falling sharply, maybe even down to 0, as the bank tries to stimulate the economy.
And what does that do to financial markets?
Well, low interest rates combined with all that negative economic sentiment means that even though borrowing is cheap, corporate profits are collapsing. So asset prices, stocks, corporate bonds, they have to be modeled as being depressed because of poor earnings and high systemic risk, even with low interest rates.
And finally, exchange rates. How does that kind of scenario affect the currency?
The exchange rate response is complex. It really depends on the global context of the scenario. If the recession is purely a domestic problem, your currency, say, the dollar might weaken as capital flows out, looking for growth somewhere else.
But what if it's a global crisis?
If the scenario involves a global crisis where the dollar is seen as the ultimate safe haven, then the currency might paradoxically strengthen even as the domestic economy is suffering. The analyst has to justify that specific flight-to-safety dynamic within their narrative.
So the key is that they all have to move, and they have to move in directions that support the overall story you're trying to tell.
That's the core of it. What's fascinating is that the analyst isn't just plugging in numbers. They have to adjust these 6 variables together to tell a cohesive, logically consistent story.
That sounds incredibly complex. How do they coordinate all of that without some kind of, I don't know, all-knowing supercomputer?
They rely heavily on sophisticated econometric models. These aren't just simple spreadsheets. They're programmed with historical correlations and economic theory, like the relationship between unemployment and inflation, or interest rates and asset values.
But the model is only a tool, right?
It's only a tool. The analyst's job is to apply their judgment and make sure the scenario stays internally consistent. It's easy to change one variable, but the real importance, the art, is making sure the new assumptions for all 6 variables fit together under the logic of the shock you've introduced.
Give me a good example of an internally inconsistent scenario that they would have to avoid.
A classic example of an inconsistency would be a pessimistic scenario that models a sharp rise in unemployment and simultaneously models asset prices, like the stock market, soaring.
Right, that makes no sense.
It makes no sense. High unemployment means low consumer demand and terrible corporate profits. The only way asset prices could soar in that environment is if some other massive contradictory force like, unlimited free money from the central bank was also at play. And if that force isn't explicitly part of your narrative, the scenario is just useless for risk management.
So you can't contradict basic economic theory without a really clear, specific explanation for why.
Exactly. You have to explain the shock that justifies breaking the rules.
So once those core variables are set, let's dig into the actual design process. How do analysts take their baseline forecast and spin it into these consistent alternative realities, especially making sure all those variables behave logically together?
Well, it all starts with the baseline path. The initial forecasts, which are data-driven, provide the expected trajectory for all 6 of those economic variables over the, projection horizon, usually 2 to 5 years.
So that's the starting point, the world as it's currently anticipated.
Right, and then the alternatives are built by deviating from that path.
How do they do that?
Alternative scenarios are created by adjusting the forecast assumptions and introducing specific shocks or deviations that push the variables off the baseline. For example, if we wanted to construct a stagflationary downside scenario,
Okay, stagflation?
it would introduce a severe shock, maybe a combined supply shock, like a massive geopolitical disruption cutting off resource imports, and a labor shock, like persistent high-wage demands.
So in that scenario, you'd push GDP growth down, but because the inflation is supply-driven, you keep inflation high.
Precisely. GDP growth goes to near zero or negative, but inflation stays stubbornly high. Now, this forces the central bank to keep interest rates high, unlike in a pure recessionary scenario, to fight that persistent inflation.
And then the cascade hits.
Then the cascade hits. High interest rates plus poor growth means asset prices have to suffer a steep, prolonged correction. That story, as painful as it is internally consistent under the theory of a stagflationary shock.
And this is where economic theory comes in, acting as the internal police force to make sure the scenario doesn't become nonsense.
The material really stresses this. Economic theory is leveraged heavily to ensure scenario consistency. Consistency is the absolute gold standard.
So if you model a policy of, say, quantitative tightening.
Right, removing money supply. Basic theory says that liquidity has to decrease, interest rates on long-term bonds have to rise, and risk appetite has to fall. You just cannot have a scenario with massive quantitative tightening that also shows soaring housing prices and low corporate debt spreads. It just doesn't work.
Can you give me a clear example of that kind of mandatory consistency, but specifically in the financial markets?
Sure. Think about the relationship between interest rates and bond valuations. Within a scenario, if the analyst posits a major, unexpected interest rate hike, a policy shock economic logic dictates that the value of existing lower-yielding bonds has to fall dramatically.
So high rates must lead to depressed asset prices.
Especially for long-duration assets, yes. Within that scenario's framework, if your scenario showed high rates and a stable bond market, any regulator would just immediately reject the model as inconsistent and therefore useless for managing risk.
And that just drives home the crucial best practice here. You have to ensure internal consistency and base your assumptions on economic logic and data. A compelling story isn't enough. It has to be an economically plausible story.
Even if it's testing the limits of those relationships.
Exactly.
And that plausibility is what gives decision makers the confidence to actually act on the results. Inconsistent scenarios are just. They're a wasted exercise. Consistent scenarios are like a simulated reality, and that's what provides the decision robustness they're looking for.
Now, you mentioned this earlier, but this might sound familiar to some of our listeners who've worked in finance or planning. They might be thinking, well, I already run sensitivity analysis on our projections.
Right.
We need to spend a minute explaining the critical, fundamental difference between these two analytical tools.
Yes, this is a fundamental point of distinction. It separates basic forecasting from really sophisticated risk management. Sensitivity analysis is defined by its simplicity. You change one variable at a time while holding all the others constant.
So a planner might ask, what happens to our profit margin if raw material costs go up by 10%? assuming everything else stays exactly the same.
Exactly. Assuming interest rates, exchange rates, consumer confidence, all of it remains perfectly equal.
That sounds simple and useful for understanding your direct exposure to something. So why isn't that enough for strategic economic planning?
Because that assumption, holding all other factors perfectly equal, is economically impossible during a real crisis.
Right.
Real-world shocks are never isolated like that.
Right. They have knock-on effects.
Always. When the cost of raw materials surges because of a geopolitical conflict, it immediately impacts half a dozen other factors. It impacts inflation, which forces central banks to adjust interest rates, which affects the currency, which then changes import costs, which feeds back into consumer spending.
It's a chain reaction.
It's a huge chain reaction. Sensitivity analysis is great for, say, academic study or micro-level budgeting, but it's really poor for capturing systemic complexity.
And this is where scenario analysis proves its sophistication, by moving beyond that isolated test.
Scenario analysis is defined by its complexity. It changes multiple variables simultaneously and explicitly captures the interactions and feedback loops among them. It tells the story of the entire economic system reacting to a shock, not just the initial direct impact of the shock itself.
Let's use that raw material shock example to walk through the difference.
Okay, in a sensitivity analysis, you get one number. If raw materials go up 10%, our costs rise by X and our profit falls by Y. That's the end of the analysis.
But in a scenario analysis, you get the whole cascade effect.
You get the systemic story. The scenario analyst says, okay, raw materials rise 10%. This drives up core inflation by 1.5%. The central bank reacts by raising interest rates by 200 basis points, which crushes the housing market and pushes asset prices down. Simultaneously, the higher cost of goods crushes consumer confidence, slowing GDP growth to zero, which then forces a hiring slowdown and a spike in unemployment.
So you're measuring the total interactive harm of the shock plus all the necessary reactions to it.
Exactly. It requires a much more robust, dynamic model to track those interconnected effects over time, not just static inputs.
So if we have to conclude then, which tool is superior for high-level risk management, especially for central banks and large financial firms?
Scenario analysis, without a doubt. It provides a far more realistic picture of systemic economic risk because real-world shocks impact the economy across multiple dimensions at once. You're never just testing a variable, you're testing the capacity of your institution to handle systemic, multi-front stress.
And this isn't just theory, right? This architecture is the core risk management tool across the entire global economy. Let's detail the broad adoption and the extremely high stakes of its usage, starting with the biggest players.
The adoption is basically mandatory and ubiquitous among these high-stakes decision makers. Starting with central banks like the U.S. Federal Reserve, the ECB, the Bank of England, they use scenario analysis extensively for rigorous, mandatory stress testing of their financial systems.
This is the famous DFS and CSIR testing in the U.S., isn't it?
Precisely. They model these highly specific, severe, coordinated shocks. For example, modeling a deep recession combined with a simultaneous sharp reversal in the housing market and a massive spike in corporate defaults.
And the objective is to test the resilience of the biggest banks.
Right. The scenario determines if banks have enough capital reserves to keep lending and stay solvent, even if the economy hits the worst plausible outcome. The results of those tests directly dictate how much capital the banks are legally required to hold.
So it's a key mechanism for preventing another 2008-style systemic meltdown.
A critical one. It's designed to make sure the system can bend without breaking.
Okay, now for governments. We often see budgets presented with a single forecast, but behind the scenes they must be running these scenarios on their national debt.
Oh, absolutely. Governments use scenario analysis for fiscal sustainability analysis. They use these alternative futures to test the long-term viability of their budget and debt planning. This is especially important in countries with high debt-to-GDP ratios.
And the question they're asking is, what happens to that debt ratio if GDP stalls for 3 years, tax receipts plummet, and unemployment payments and debt service costs surge because interest rates are high?
That's the exact question. And the scenario output helps them decide if they need to institute austerity measures now, or if their current debt levels are safe across a range of outcomes. It informs long-term structural policy. If a downside scenario shows the country crossing an unsustainable debt threshold, well, the government has a mandate to make policy adjustments today.
And what about the engine of the global economy, the big financial institutions themselves, beyond what the central bank's stress tests require?
For individual banks, insurance companies, massive investment firms, scenario analysis is core to their ongoing internal risk management and ensuring capital adequacy. They use proprietary, often even more detailed scenarios than the ones mandated by regulators.
To calculate potential losses in catastrophic events.
Everything from a pandemic shock to a sudden geopolitical trade war. This analysis directly informs how they manage their internal reserves, how they price derivatives, their overall risk appetite, everything.
So if an insurance company realizes their downside scenario shows a potential catastrophic loss of, say, $50 billion, they have to go hedge that risk or adjust their portfolio accordingly.
That's the mechanism of action. The scenario analysis is what triggers the proactive risk mitigation.
Finally, let's look at the actual production companies, the large businesses that build things and hire people. How do they use this sophisticated architecture?
They employ it for crucial strategic decisions, particularly investment and capacity planning. Imagine a massive semiconductor manufacturer. They might be thinking about building a new multi-billion-dollar fabrication plant, a fab, that takes 5 years to build.
And it requires sustained high demand to be profitable.
Exactly. So they have to run multiple scenarios.
How would a scenario directly affect that decision to build the fab?
Well, they'd model an optimistic scenario surging demand, high prices, where the fab yields a 25% return. Great. But then they also have to model a downside scenario, geopolitical tensions, cutting off key markets, a severe recession, where the return falls to -5%.
A catastrophic loss.
A catastrophic loss. Yeah. So if the investment only pays off handsomely in the upside case, but generates these terrible losses in a plausible downside case, management might decide the risk is just too high. They'll delay or scrap the investment even if the baseline forecast looks positive.
So scenario analysis moves capital allocation from what do we think will happen to can we survive if we are terribly wrong?
That is the perfect summary of the transition that scenario analysis facilitates. It is a tool for survival and systemic stability.
We've built the architecture, we've looked at the mechanics, we've seen who uses it for these massive decisions. Now let's wrap up by assessing its true value and navigating the crucial pitfalls. What are the key benefits that make this indispensable to modern planning?
The benefits are systemic and profound. First and foremost, scenario analysis explicitly incorporates uncertainty.
It's an admission that you don't know the future.
It is a formal, structured admission that the future is unknowable. And by moving away from that single-point delusion, institutions stop chasing perfect accuracy, and they start preparing for a wide range of reality.
Which, as we've been saying, leads directly to the next key benefit, improving decision robustness.
Yes, it fundamentally improves decision robustness. It makes plans resilient across various outcomes. A plan is truly robust if it yields acceptable returns in the baseline, maybe exceptional returns in the upside, but crucially, it doesn't result in systemic failure in the pessimistic scenario.
Right. If your strategy needs the optimistic scenario just to break even, it's a reckless strategy.
It's not a robust one, exactly. It also acts as an early warning system. It helps you identify vulnerability.
It catches your blind spots.
It does. By subjecting your organization, your portfolio, or your national budget to these structured stress tests, you find the weak spots before they become catastrophic failures. Does your portfolio rely too much on commercial real estate loans that collapse in the downside? Does your budget fall into a debt spiral if rates climb just 2% faster than you thought? Scenario analysis forces those vulnerabilities into the light so you can mitigate them proactively.
And there's a cultural shift, too, within an organization.
It encourages forward-looking thinking. Instead of just obsessing over the current quarter's data or just extrapolating from the recent past, it forces leaders to think systematically about long-term drivers, extreme tail risks, and structural relationships. It promotes a proactive, scenario-based strategy rather than a reactive one.
But as powerful as this is, it is not a silver bullet. We have to talk about the critical constraints so that you understand its inherent limitations. We've seen in major crises that even the most sophisticated models can fail.
The first, and arguably most important limitation, is the dependence on inputs and model structure.
Garbage in, garbage out.
It is the classic GI-GO principle, applied with extreme prejudice. The results are only as good as the chosen assumptions, and the design of the underlying model used to translate those assumptions into outcomes.
Which means the analysts have immense power just by choosing which assumptions to test and which ones to ignore. If they pick a downside scenario that isn't severe enough, the institution gets a false sense of security.
They do. Let's take a specific example. In the lead up to the 2008 financial crisis, many financial models failed because the core assumption was that nationwide housing prices couldn't fall all at the same time.
Right. They thought it was regional.
They might have run a scenario where housing prices fell in California or Florida, but not one where they fell everywhere at once. Because that crucial correlation break wasn't put into the model, the scenarios drastically underestimated the systemic risk. If your model misrepresents a key relationship, your results will be fundamentally flawed.
That's a huge danger. But there's another crucial point that often confuses people, which is that scenarios are not probabilities.
This is a critical distinction to grasp. It means the model does not tell you the chance of a recession. It only tells you the potential outcome, the severity, if a recession occurs.
So the downside might show a 40% loss in your portfolio, but the model doesn't say there's a 5% chance of that happening.
Exactly. It doesn't assign a probability.
So how do decision makers decide what to prepare for if there's no probability attached?
They have to use qualitative judgment or other statistical tools to assess probability. But the point of scenario analysis is to focus the mind entirely on the consequence, irrespective of the perceived likelihood.
Right.
If the potential damage in the downside scenario is existential-like, the total collapse of your institution, you must mitigate it, even if you think there's only a 1% chance. You focus on the damage and the robustness of your response.
And finally, the limitation that always comes to light in a real crisis. The problem of the unknown unknowns. The black swan events.
This is the fundamental constraint of any model that's based on economic theory and historical data. Scenarios cannot capture all possible future outcomes. They are generally constrained by what we think is possible. They can't account for events that fundamentally break the known connections between variables, true, unprecedented shocks for which there's no historical parallel.
Like the sudden global shutdown from a pandemic, which just completely inverted labor market dynamics in ways economists hadn't mapped in decades.
Exactly. The scenarios built before that event, while they might have stress-tested geopolitical risks or interest rate movements, they just couldn't have prepared anyone for that specific non-economic shock cascade.
So if the inputs can be flawed, the analysis isn't probabilistic, and the world is always creating these unknown unknowns, how do practitioners make sure this powerful tool stays effective and relevant? What are the best practices for maintaining it?
The practice has to be highly dynamic. The sources stress that scenarios must be regularly updated as conditions change. They can't be static documents.
So if geopolitical tensions suddenly spike, or a huge new fiscal policy is announced,
The baseline scenario, and therefore the upside and downside narratives, have to be adjusted to reflect that new reality almost immediately. A scenario built in the stable, pre-2020 low-inflation world would be dangerously irrelevant today.
it's an ongoing living process, not a one-time report.
And furthermore, its role in forecast evaluation is essential. The outcomes of the scenarios help you assess the robustness of the primary forecast itself. It's a crucial feedback loop.
How does that work?
If your baseline point forecast looks fantastic, predicting smooth sailing, but the smallest negative deviation in the downside scenario causes catastrophic failure, well then your baseline forecast is, by definition, too risky to pursue without massive structural hedging.
So the scenarios are the ultimate reality check for how fragile your main forecast is.
They are. They highlight your exposure to extreme outcomes, which is vital knowledge when, as the sources note, inherent forecast accuracy is so limited. Since we know we can't predict the precise future, we use scenarios to understand the full consequences of being wrong. And that lets institutions manage their exposure rather than just betting on an outcome.
So we've taken the full deep dive into the architecture of economic scenario analysis. We've gone from the single, fragile guess of the point forecast to this robust, multi-story approach that really defines modern, high-stakes risk management.
In central banks, governments, and global corporations.
And the core insight remains so clear.
It does. Economic scenario analysis is the structured process of telling multiple, consistent what-if stories about the economy. It ensures resilience and stability by moving the focus from the impossible task of being right to the mandatory goal of being prepared.
It's the tool that allows central banks to test their banking systems against disaster and businesses to justify or halt massive projects. It's planning for reality, not for fantasy, by mapping out the landscape of potential dangers.
But this reliance on consistency, on known rules, leads us to our final provocative thought for you to mull over.
Okay.
We've emphasized again and again that the effectiveness of this analysis depends entirely on internal consistency rooted in known economic theory. The idea that high rates must lead to low asset prices, that high unemployment depresses inflation.
Given that framework, what does that imply for preparing for truly unprecedented shocks? We're talking about events that fundamentally break the known connections between key variables. Shocks where, for a moment, economic laws seem to suspend, or historical correlations completely invert.
If the model of consistency is the very foundation of the analysis, how do we build scenarios for the truly unprecedented? How do we stress test our system against the shock that requires us to throw out the very economic theories we use to build the scenario in the first place?
That is the frontier challenge for the economists and risk managers of tomorrow. Something to think about as you navigate your own decisions this week. Thank you for joining us for the deep dive.
We'll see you next time.
Have you ever looked at the news, seen a massive headline about national GDP growth, or maybe a sudden spike in the inflation rate, and thought to yourself, okay, that sounds huge and important, but how does that actually connect to me?
Right.
How does it connect to the choice I made to skip that expensive coffee this morning, or the decision my neighbor's small business made last week to maybe hold off on hiring someone new?
It's one of the oldest disconnects in economics, really. For the average person, it's just so easy to feel like the economy is something that happens to us, that it's driven by these distant, abstract forces like, the Federal Reserve or massive global trade flows.
Yeah, these huge things you can't control.
But as you rightly point out, the reality is that those massive economic outcomes, the GDP number, the unemployment rate, they're nothing more than the statistical aggregation of millions, literally millions of tiny, specific, individual decisions.
The ones made by every household and every firm every single day. And our mission today is to bridge that perceived gap. We want to turn that disconnect into a source of, predictive power. We are diving deep into the art and science of integrated forecasting.
And this is so critical.
It's all about how experts move past looking at the forest or the trees and instead learn how to combine the huge, sweeping, aggregated macro data with the incredibly granular, specific micro data.
And the goal?
To create forecasts that are not just more accurate, but vastly more useful for making high-stakes, real-world decisions.
This entire deep dive, it's built on sources that explore the rationale and the methodology for combining these two seemingly disparate worlds of information. You have the high-altitude view, and then you have the boots-on-the-ground reality.
Okay, let's unpack this immediately. Let's start with the core premise, the rationale. The need for this combination is beautifully simple when you think about it.
It really is.
Economic outcomes are simultaneously shaped by these big aggregate forces. Think about global pandemics, huge government spending programs, or central bank interest rate hikes.
The big currents.
And at the same time, by individual level behavior. So how a specific household decides to save, or how a single small firm decides to price its goods in the face of, local competition.
You truly cannot understand one without the other. If you only look at the whole, you fundamentally miss the movement, the driving motives of the individual parts.
But the reverse is also true, right?
Absolutely. Conversely, if you only look at the parts, you miss the big, overwhelming currents, the rising tides that are pushing them all along.
So using both.
Using both data types fundamentally improves your forecast accuracy. It captures both inertia and innovation. It enhances our economic interpretation of complex events. And, it dramatically increases the policy relevance of what you find.
I think the best way for you to visualize this is through that forest analogy we mentioned. The macro picture is like viewing the entire forest from, say, 30,000 feet. You can see the overall health, you can see the average density of the canopy, the direction the entire system is moving because of prevailing winds or a multi-year drought.
You see the big shapes.
Exactly. But you have no way of knowing if a specific area or a specific type of tree is thriving or if it's diseased.
And that's precisely where the micro data comes in. That's when you zoom right down to ground level.
Or use a drone.
Right, or use a drone. And you're examining the health of individual trees. You're measuring the specific soil quality in one valley versus another, and you're observing how one type of localized pest, that small, specific mechanism, is affecting the growth rate of specific saplings versus the old growth.
And the real power of integration, I think, comes when those two perspectives contradict each other.
Oh, absolutely. That's the key.
If the forest average looks good, the macro signal is positive, but you start seeing at the micro level that, say, 80% of the individual young trees are subtly failing because of some new localized fungus.
then that macro average is actively misleading you.
Your forecast for next year's forest health will be dramatically, and I mean dangerously, off. That combination, that synergy, is the ultimate goal of this deep dive. We want to show you how that crucial improvement in prediction is actually achieved. Okay, let's dedicate this first part to laying the necessary foundation. We really need to clearly define our terms and, maybe more importantly, explore the inherent strengths and the critical limitations of each data type before we even talk about blending them.
It's the only way. It sets up the entire discussion of complementarity.
So let's begin with macroeconomic data, the big picture.
The big picture. This is data representing aggregate economic conditions across the entire system. It's the stuff that, dominates financial headlines. It's the high-level indicators that central banks and national treasuries rely on to steer the ship.
And these are the usual suspects, the ones that often drive national policy. They fall into what, 4 primary categories?
Generally, yes.
So first we have GDP and output growth.
The headliner.
Right. This measures the total value of goods and services produced. It's essentially the ultimate barometer of national performance. When we talk about the economy getting bigger or shrinking, we are 9 times out of 10 talking about GDP.
Then second, you have the critical indicators of price stability, inflation and price indices.
Like the CPI.
Exactly. The Consumer Price Index, which tracks a basket of goods you might buy, and also the Producer Price Index, which tracks what producers are paying for their inputs. This tells us about purchasing power, systemic pricing pressure,
and whether the economy is running too hot or too cold.
Precisely.
Okay, third, we have to look at the health of the workforce. So unemployment and labor force indicators.
And this is more than just the headline unemployment rate, which, by the way, is often a lagging indicator.
A very important point.
It also includes things like the labor force participation rate, non-farm payroll numbers, and aggregate wage growth. It's measuring the overall health of the job market across all sectors.
And finally, what's happening underneath it all? The financial plumbing.
Interest rates and monetary aggregates. This is capturing the cost of capital, the benchmark rate set by central banks, as well as measures of overall liquidity and the money supply in the banking system.
Which dictates all the financial conditions for borrowing and lending.
Right.
So the strengths of this kind of data, they're undeniable, they're necessary. Macro data gives you that broad national or even regional coverage. It gives you an immediate, if general picture of national health.
And it has direct, immediate relevance for the biggest policy decisions, like setting that central bank rate or understanding the broad sweep of the business cycle, that recurring pattern of boom and bust.
But, and this is the big but, the limitations of relying solely on macro data are so crucial. They explain the entire reason we're doing this deep dive.
And the first, and maybe the most misleading problem, is that aggregation masks difference. When you average everything together into a single number, let's say 2% GDP growth for the country,
right,
that average number often hides wildly disparate performances internally. It's a statistical fiction, in a way.
That's where all the nuance is completely lost. Imagine during a period of, say, moderate economic growth, the national figures look fine. They look okay.
Stable.
But if you zoom in, you might find that the financial services sector is absolutely booming, driving all the growth, while the entire manufacturing base is collapsing, losing jobs and capacity.
The average looks stable, but the fundamental internal structure of the economy is shifting dramatically and possibly dangerously.
We saw this so vividly after the 2008 crisis, didn't we? Where aggregate consumption measures recovered.
They did, on paper.
Yeah.
But the composition of that recovery was incredibly uneven. It favored certain geographic regions, certain income brackets, and it led to this significant underlying social strain that the macro numbers just didn't capture at all.
So the average outcome feels stable.
But the distributional reality for millions of people is severe decline.
And then there's this persistent headache for anyone doing real-time forecasting, the problem of revisions and lags.
Oh, this is a huge one. Macro data is inherently slow.
Why is that?
Because it has to collect information from thousands, sometimes millions of entities. So the initial release of GDP or inflation data is often just preliminary. It's based on incomplete samples.
And then it gets changed later.
It can be revised substantially weeks or even months later as more complete data trickles in. So the forecaster is often making crucial decisions, and the central bank is often adjusting policy based on data that is not only historical,
All right, it's from the last quarter.
but it's also often statistically inaccurate in its first release. You are making present-day policy decisions based on an economic past that might not have even existed once the revision comes through.
That lag and that instability in the historical record, it just creates significant uncertainty.
Yeah.
So if the macro data is the broad, often dusty, and always slightly delayed national map, let's pivot our focus. Let's get into microeconomic data.
The individual mechanism.
Right, the boots-on-the-ground detail that provides that necessary contrast.
Microdata describes individual units, and this is really where we find the granular truth. We're talking about specific households, single firms, defined regional markets, or even individual transactions captured in real time.
So let's look at some specific examples that go way beyond the aggregate, instead of, say, national industrial production.
We look at firm-level sales, inventory, and specific investment figures. We can observe, for instance, exactly how much a specific automaker plans to spend on transitioning its supply chain.
Or, precisely how many widgets the local industrial fabricator sold last month, rather than just looking at the sector average, which might be misleading.
We also gain incredible depth into household income and consumption patterns. And this data is often broken down by highly specific demographic or geographic segments.
So you can see if high-income households are increasing their spending on luxury services.
Or if middle-income households are dipping into the savings they built up during the pandemic, or worse, resorting to credit card debt just to maintain a stable level of consumption. The why becomes clear.
And crucially, this level of detail applies to prices too. We can look at industry-level prices and specific input costs.
Right. Not just the overall CPI basket, but the price of specific raw materials.
Like lumber for home builders.
Exactly. Lumber for residential construction, or specific types of semiconductors for electronics manufacturing, or even electricity costs for energy-intensive industries. This detail helps us understand margin pressure and cost propagation.
It gives us a much clearer view than just the final price we all pay at the checkout.
The strengths of microdata are its rich detail and its speed. It offers immediate insights and provides these early signals of structural economic change.
So if consumer behavior is fundamentally shifting, like that sudden and rapid pivot from buying physical media to purchasing digital subscriptions, you see that granular shift at the micro level first.
Months, sometimes even quarters, before that movement is large enough to measurably affect the national GDP figures. Microdata is where genuine innovation and disruption first appear on the radar.
Okay, but here is where the conversation gets really interesting, because microdata comes with its own significant and equally dangerous set of drawbacks. This is the trade-off.
A huge trade-off.
While it's rich in detail, it almost always has limited coverage. It's often specific to one area, one type of consumer survey, or one industry panel that voluntarily reports its data.
You might have amazing real-time credit card swipe data for major urban centers, for example.
But almost zero visibility into rural consumer behavior or the cash economy, which can be a huge part of the picture.
And this limitation, it leads directly to the problem of sampling bias.
Okay, what does that mean in practice?
Well, if your microdata relies on surveying a specific panel of businesses or households, you have to ask, are those units truly representative of the entire national population?
Probably not.
If your sample is inadvertently skewed toward, say, smaller, high-growth tech firms, your conclusions about overall business optimism or investment will be fundamentally flawed for the rest of the economy.
And maybe the single biggest challenge for anyone building a model, higher noise.
Macro data, by its very definition, is the average of millions of transactions, which makes it inherently smoothed out and stable. Microdata, however, reflects every single individual fluctuation.
So if one huge firm has a fantastic quarter because of a one-off government contract,
that data point is massive and it's real, but it's an anomaly. It's not a predictive trend.
Exactly. This instability, this noise, makes it incredibly difficult to derive stable, predictive forecasts from microdata alone. You risk overwhelming your model with idiosyncratic, one-time events.
So to wrap up this first part, we have two worlds. One is broad and stable, but it's slow, it lacks crucial detail, and it's subject to revision. That's macro.
And the other is incredibly detailed and fast, but it's noisy, it's incomplete, and it's highly susceptible to bias. That's micro.
The mission of integrative forecasting, therefore, is to merge their strengths while trying to mitigate their collective weaknesses. That sets us up perfectly for part two. Let's move on and explore the synergy, the complementary relationship, and why this combination is so much more powerful than just the sum of its parts. This is the heart of it all.
This really is the core of integrated forecasting.
The central insight, which is established by our sources and, frankly, confirmed by practice, is this. The relationship between the two datasets is complementary, but it's also asymmetrical.
Explain that.
Macro data indicates what is happening at the economy-wide level, while micro data explains why it is happening. It reveals the underlying mechanisms and the behavioral motives.
Okay, let's dive deeper into that consumer example. Let's say the latest macro GDP release shows that aggregate consumer spending has slowed down significantly this quarter.
Okay, so that's the what.
That's the what. If you relied only on that number, the consensus forecast might just be general pessimism has set in. People are worried.
A simple, but possibly wrong conclusion. But then you zoom into the micro data, maybe using high-frequency transaction data combined with household income panels.
And what do you find?
You find that consumption among the top 10% of income earners actually increased marginally, driven by investment in specialized services. Meanwhile, the bottom 50% pulled back sharply.
But not due to pessimism.
Not due to pessimism, but because their marginal savings were depleted, and they were facing rising, non-discretionary costs for things like energy and food.
The why is now entirely clear. It's not a generalized lack of confidence. It's a specific, targeted, and highly distributional crunch driven by sectoral price movements.
And if you were a furniture retailer, your strategy changes dramatically depending on which of those two stories you believe. The synergy fundamentally shifts the required policy response or the business strategy. You move from a blunt instrument to a scalpel.
And this synergy delivers concrete, measurable benefits for forecasters. The first massive benefit has to be early turning point detection.
Yes, micro-level shifts often start occurring months before they are large enough to actually register in the national aggregate statistics.
Give me an example of that.
Okay, if specific firms in capital-intensive sectors start canceling smaller capital orders, that's a rapid microsignal, that often tells us that they're anticipating a slowdown in future demand.
And this is happening before the big numbers move.
Months before the official GDP numbers would confirm a recessionary trend.
That forward look is just invaluable. It's the difference between predicting the recession and just reacting to it after it's already here.
And furthermore, the integration leads to improved structural interpretation. By seeing how the individual parts interact and how various sectors perform against the aggregate trend, we get a much clearer understanding of the underlying economic structure.
Which sectors are resilient, which are fragile.
And precisely how a shock, like a supply chain disruption, actually propagates through the system. Does the shock hit the consumer directly, or does it get absorbed by corporate margins first? The microdata reveals that transmission line.
And critically, integration helps reduce model misspecification.
This is a technical one, but it's so important.
Break it down for us.
Purely macroeconometric models that try to predict the future based only on historical macro relationships often assume that past correlations will hold true.
But they might not.
They often don't. If the underlying microbehavior has changed dramatically, for example, if technology has made consumers suddenly much more sensitive to temporary price changes than they were 10 years ago, a macro-only model will fail spectacularly.
So integrating that observable microbehavior makes the models more robust.
Fundamentally more robust and less likely to be structurally wrong about the future.
Let's make this even more tangible. Let's look at some specific integrated applications where this data synergy provides immediate superior results.
Great idea. Let's start with output and demand. The macro indicator here is obviously the quarterly GDP trend. But to truly forecast demand and output, you have to combine that high-level GDP number with specific, granular, firm-level production and inventory data.
What's fascinating here is the feedback loop, right? The granularity informs the aggregate.
That's it. We track something like the Institute for Supply Management, the ISM Index, which is a macro survey, but we gain far more predictive power by integrating the specific, detailed inventory data from major retailers and wholesalers.
So if specific manufacturing plants are reporting higher than expected finished goods inventory, that's a micro detail. What does that tell you?
It tells you that the next quarter's GDP output forecast should likely be revised downwards, even if current sentiment indices are positive.
Why?
Because high inventory today means future production will likely slow down tomorrow to absorb the surplus. It's a leading indicator of a slowdown.
Okay, next, let's consider the massive field of inflation forecasting. Everyone tracks the aggregate price indices like the CPI.
That's a what?
That's the what. But to forecast where inflation is truly going and whether it needs a central bank to intervene, you desperately need to understand the micro component.
Which is price-setting behavior.
This is where we separate the temporary from the structural. We use microdata to understand why a specific firm is raising its prices.
Is it because their specific labor costs have gone up 15%? That's a structural cost-push microshock.
Or is it because everyone just received stimulus checks and demand is temporarily overwhelming supply?
A transient demand-pull macro shock. A forecast that can distinguish between those two causes is vastly superior.
So if it's structural?
If aggregate inflation is being driven primarily by micro-level structural factors like rising sticky wages or higher geopolitical input costs, then the inflation is likely persistent and requires aggressive policy.
But if it's just a temporary demand spike?
It might dissipate on its own. The integrated view allows the model to decompose the aggregate inflation figure into its driving parts, which is essential for accurate policy recommendations.
Then there is the labor market. We naturally focus on the overall national unemployment rate, but the real intelligence, the quality of the forecast, comes from connecting that with detailed firm hiring, layoff, and specific wage data.
You have to know where the jobs are being created. Is it high-skill engineering or low-wage service sectors? And how fast are wages moving in those specific targeted sectors, broken down by demographics?
This distributional insight is so critical for assessing the actual strength and, frankly, the equity of an economic recovery.
A seemingly stable macro unemployment rate can, for example, mask a situation where high-wage sectors are laying off workers,
Which is a negative microsignal indicating future weakness.
while low-wage sectors are aggressively hiring. That's a positive but lower quality microsignal that actually drags on productivity. The integrated view tells the full story of labor quality, earning potential, and long-term economic scarring.
I feel like I have to interject some genuine skepticism here. If the microdata shows that every sector is hiring, but they're only hiring in part-time roles paying minimum wage, doesn't that fundamentally invalidate a macro reading that says the labor market is tight just because the unemployment rate is low?
It absolutely does, and this is exactly why integrated models are so powerful. They force the forecaster to confront that qualitative difference.
So how does that change the conclusion?
A traditional macro model might conclude that low unemployment means inflation will rise due to competition for workers. The integrated model, however, sees the micro-wage distribution, sees that wages are only rising for the top 5% of earners, and it adjusts the inflation forecast downwards.
Why?
Because the broad spending power necessary to drive that inflation just isn't materializing for the rest of the workforce.
Okay, finally, let's look at investment forecasting. The macro signal here is interest rates, the overall cost of capital.
But the micro side involves analyzing firm balance sheets and detailed expectation surveys. Just because money is cheap, low macro interest rates, doesn't automatically mean firms will borrow and invest.
Right.
Indeed, a firm may have access to historically cheap capital, but if the micro data shows that the CEO confidence level is in the basement, or if their current debt load, which is visible on their balance sheet, is already high, they will just sit on their hands.
So investment is a combination.
It's the macro ability to borrow, coupled with the micro willingness and capacity to borrow, factoring in all those firm-specific risk profiles.
That's an excellent survey of the applications. And it brings us logically to part 3. We're moving from the why and the what to the crucial how. How do experts actually do this?
We're getting into the econometric approaches that experts use to mathematically combine these large, disparate data sets into a single, cohesive forecasting framework.
And what's most important to stress here is that this is not just, data science for its own sake.
Not at all. Economic theory must always be the guiding light. We can't just throw massive amounts of data into a supercomputer and hope to the best. Theory has to inform the structure, guiding variable selection and aggregation rules.
To prevent what's called data mining.
Exactly, to prevent simple data mining that might lead to statistically significant but economically nonsensical correlations.
Okay, let's look at the 3 primary structural approaches, starting with the classic and maybe the most conceptually straightforward one. Approach 1, top-down forecasting.
In the top-down method, forecasters start high and broad. They generate the macro aggregate forecasts first.
So for instance, a government agency or a major financial institution might predict that overall national GDP growth for the next fiscal year will be, say, 2.5%.
And they base that on global trends and interest rate expectations.
The execution then involves this critical step, disaggregation. The model takes that national prediction and it allocates those growth figures down to specific sectors, industries, or even large individual firms.
So if GDP is 2.5%, the model might allocate 0.5% growth to the construction sector, 1.0% to the technology sector, and so on, using historical ratios or other industry-specific weights.
The strength of top-down seems to be its forced coherence.
It is. All the individual pieces, when you mathematically add them up, must perfectly equal that initial macro forecast. But the challenge is that the process of disaggregation is often fraught with difficulty.
How so?
Well, how do you mathematically allocate 2.5% GDP growth across potentially thousands of specific sectors without introducing significant arbitrary factors or relying on historical weights that may no longer apply in a changing economy?
And I see the fundamental weakness, too. The initial macro forecast is the single point of failure.
That's the Achilles heel. If the forecaster missed a global shift, and the initial GDP prediction should have been 1.5% instead of 2.5%, every single granular forecast underneath it, the predictions for construction, tech, retail, is structurally and coherently wrong. That one error propagates downward through the entire model.
Which logically leads us to the counterbalance, approach 2, bottom-up forecasting.
The opposite journey. And it was often developed precisely to address that responsiveness weakness of the top-down methods.
So here, forecasters start at the granular level. They make the micro forecasts first.
Right. They might predict the specific sales, revenue, capital expenditures, and inventory movements for a large sample of hundreds or maybe thousands of representative firms or households.
The execution then involves aggregation. These detailed micro forecasts are mathematically scaled and summed up to estimate the macro-level outcome.
So if the aggregated sales of the firms in their sample represent a stable 10% of the national economy, they can then extrapolate and predict overall national sales and, eventually, GDP.
The benefit here is clear. It's speed and responsiveness. It's highly sensitive to real-time changes at the firm level.
If 50 of those 100 firms suddenly revise their internal sales forecasts down this week, the aggregate model instantly reflects that broad pessimism.
We run right back into that challenge of sampling bias.
You do. If your sample of firms isn't truly representative of the entire economy, say you missed all the cash-heavy traditional businesses, your macro forecast aggregated from the bottom will be structurally skewed. The micro noise contaminates the macro output.
And finally, the most advanced approach, the one that tries to capture the best of both worlds. Approach 3. Mixed data models.
This is where models become computationally intensive and truly sophisticated. They involve combining variables that operate at fundamentally different levels.
Aggregate labor market trends versus individual household debt levels.
And critically, at different frequencies. Think about trying to model quarterly GDP data alongside daily high-frequency credit card swipe data within one model.
How does that even work?
Well, these models often utilize advanced techniques like dynamic factor models or DFMs and Bayesian estimation. Let me just clarify what a DFM does for you because it's a game changer.
Please.
It allows the model to estimate an unobservable common driver, a statistical factor that influences both the macro data, like national consumer sentiment, and the microdata, like an individual store's sales, simultaneously.
That's fascinating. So instead of forcing a top-down or bottom-up structure where one level dictates the other,
the mixed data model uses statistics to find the underlying hidden pulse of the economy that is driving both aggregate movements and individual decisions at the same time.
so they're modeled together.
Precisely. They model the relationship between the macro and micro simultaneously, allowing them to influence each other within the same mathematical framework. This avoids the forced consistency of top-down and the representativeness pitfalls of bottom-up, yielding much more robust results.
Provided you have the computational power.
Provided you have the computational power.
Okay, let's delve into the powerful advantages that justify all that complexity and cost of embracing this level of integrated forecasting.
The first, and maybe most obvious advantage, is improved robustness. When your forecast is derived from two completely different data streams, one reflecting the aggregate whole, one reflecting the fast-moving parts, it is much less likely to be completely derailed by a single data anomaly.
Or a temporary statistical quirk.
Exactly. If the latest preliminary macro CPI number comes in and it looks suspiciously low, the forecaster can immediately check the firm-level price-setting data and specific supplier cost indices.
And if the firm-level data confirms the decline?
The forecast is robust. You can trust it. But if the firm data dramatically contradicts the macro number, the forecaster knows the initial macro release might be a statistical fluke.
Maybe due to some temporary government discount program that got captured in the survey?
Right. and they can confidently adjust the forecast accordingly.
This integration also delivers a better understanding of transmission mechanisms. This has to be the single most important benefit for policymakers and strategic planners.
That's why they do it. The integrated model doesn't just predict that an outcome will happen, it maps the precise pathway of how it will happen.
For example, an integrated model can show how a specific increase in monetary policy like raising interest rates actually filters down and affects household spending at the micro level.
It can show you, through the microdata components, that rising rates disproportionately impact young households with variable rate mortgages and high consumer debt,
Leading to consumption slowdowns that are concentrated in specific metropolitan areas with younger demographics.
The model captures heterogeneity. It doesn't assume every dollar spent reacts identically to interest rates. It understands that households with high equity and fixed-rate mortgages are barely affected, while highly leveraged, younger households are immediately crunched.
That detailed mapping of impact is crucial for designing policies that are targeted and effective.
And building on that, integrated data enables enhanced scenario and stress testing. If you only have macro data, your stress tests are limited to these broad shocks like, what if GDP falls 1%?
Which is pretty blunt.
Very blunt. But with integrated data, you can model complex, sector-specific what-if situations.
Like what?
You can model what if the cost of natural gas spikes by 50% only for chemical manufacturing industries in the Midwest due to a regional pipeline disruption. How does that specific shock affect the overall national labor market, given that those specific firms have low profit margins?
Those targeted stress tests would be invaluable for financial regulators assessing systemic risk.
And for large multinational businesses managing highly complex global supply chains.
Which ties directly to the final point, a stronger link to decision-making. Because these models capture both the aggregate forces and the individual responses, the results are immediately actionable.
For both policymakers and business operational teams.
Policymakers get the distributional impact, and businesses get segmented, specific forecasts derived from the micro disaggregation.
It translates economic prediction into tangible, segmented action points.
As powerful as that all sounds, we have to be realistic. This brings us to part 4, the reality check. Let's address the core challenges in achieving this ideal combination.
Because it is anything but simple.
The challenges start with the fundamental difficulty of data consistency and definitions. This is just a massive headache for anyone trying to merge two data streams from different collectors. You have to ensure that the definition of a firm used in a specific microdata set, say a small business survey that explicitly excludes sole proprietorships, actually matches the definition used for a macro aggregate like national payroll data collected by the government.
And if the definitions of the fundamental unit of analysis don't align, combining them is, well, it's meaningless. One might define investment as only capital machinery. The other might include intangible assets and R&D spending.
So you have to spend significant time just standardizing classifications before you can even begin the modeling process.
This issue is compounded by the problem of different frequencies and time spans. We are dealing with everything from annual government census data on capital expenditures to high-frequency market data.
Daily stock trades, hourly sales figures.
Second-by-second sentiment analysis from social media. How do you integrate annual, quarterly, monthly, and daily data without sacrificing the integrity of the slower-moving bedrock variables?
Or overwhelming them with the noise of the high-frequency variables.
You often have to employ interpolation or aggregation techniques, effectively smoothing or guessing at the missing data points to synchronize the timelines. But every time you do that, you're introducing a potential source of error and sacrificing the precision that made the microdata valuable in the first place.
Then there is the pure technical hurdle, computational complexity.
Microdata sets are truly massive. We're talking tens of millions, sometimes hundreds of millions, of individual observations that need to be run, linked, stored, and rerun iteratively.
So integrating and running these advanced mixed data models on data of that size...
It's computationally demanding. It requires specialized infrastructure. This isn't something you can just run on a laptop. It introduces significant costs and processing delays that limit your ability to generate rapid forecasts.
And this leads to perhaps the most dangerous challenge for forecasters, especially those who are new to leveraging big data, the severe risk of overfitting.
The great temptation.
Explain this. Microdata, because it's so detailed and voluminous, gives models a massive opportunity to model historical data too closely.
The model becomes a historian, not a predictor.
That's the perfect analogy. The model is like a student who memorized the answers to the practice test perfectly, including all the typos and mistakes.
But when you give them a new test, the future, they fail.
Because they never learned the underlying principles of economics, only the historical idiosyncrasies of the training data set.
Right. If a model is overfit, it performs brilliantly on historical data, showing R-squared values near 1, but when you ask it to predict the future, or out of sample data, it fails spectacularly. Managing this risk requires immense statistical discipline and rigorous testing.
Building on those methodological hurdles, let's focus on data quality and measurement issues inherent in both worlds. This forces forecasters to constantly manage a difficult, almost philosophical balance.
The primary tightrope walk is balancing detail versus reliability. Microdata offers the maximum available detail, but it often comes with lower statistical reliability due to sampling issues and reporting variance. Macrodata is statistically robust and reliable, eventually after revisions.
But it fundamentally lacks the nuance and detail needed to inform policy or business operations.
Let's focus first on the specific microdata pitfalls. These often include simple, non-malicious reporting errors.
Like what? A typo?
A typo or a firm might accidentally misstate its inventory figures in a quarterly survey due to an administrative mistake. A household might misreport its actual income or debt out of suspicion or just simple memory failure.
And because these are specific observations, these errors can be highly magnified when aggregated.
Especially in bottom-up models, yes.
And we have to return to the problem of limited representativeness.
It's a constant battle. If a major government agency surveys consumers via specific methods, say, relying heavily on landline phone calls, they might systematically miss entire segments of the population.
Specifically younger, more mobile demographics.
Exactly. That structural sampling bias means the detailed microfindings don't truly capture the universe of behavior, which makes the aggregate conclusions faulty.
And I have to wonder, how is a forecaster supposed to get truly representative data when almost every large-scale survey is inherently flawed? I mean, it suffers from non-response bias or self-selection. It feels like chasing an impossible ideal.
That's a fundamental question. And the best practice isn't to eliminate the bias, which is, as you say, impossible, but to model the bias.
So you account for it.
Forecasters use statistical weighting techniques and demographic calibration methods to adjust the raw microdata to better reflect the known population structure. They don't assume the data is perfect. They assume the data is flawed in predictable ways, and then they adjust for it. That's the core skill.
Meanwhile, the seemingly more reliable macro data has its own unique pitfalls. We already mentioned the issue of frequent revisions.
This is a deep systemic issue. The historical record you're building your models on is constantly shifting under your feet.
If last year's GDP was initially reported at 3% and then it's later revised down to 2%.
Any model trained on that 3% figure is inherently based on a past that didn't actually exist. You're constantly building a new forecast on a moving historical foundation.
Furthermore, macro data is subject to methodological changes over time.
All the time. Governments constantly update how they measure inflation or how they calculate GDP. For instance, changing the base year for prices, or suddenly including previously excluded items like spending on R&D as fixed investment.
So when the rules of measurement change, comparing data across decades requires extensive, often proprietary adjustment.
To ensure you are comparing apples to apples.
So ultimately, the skill of the forecaster in this integrated world lies not just as running the models, but in exercising judgment.
It's an art as much as a science. Knowing which data source to trust more heavily when there's a contradiction, understanding the specific biases of each dataset, and crucially, communicating those limitations clearly to the decision makers who rely on the final output.
Now for our final part, let's wrap this up by looking at the real-world impact. Let's demonstrate how this sophisticated, integrated approach actually guides strategic and operational decisions in both the policy world and the business world.
Starting with policymakers. They rely heavily on macro data to guide stabilization policy.
The big levers.
The big levers. When a central bank decides whether to raise or lower interest rates or buy government bonds, they are looking at aggregate inflation, aggregate unemployment, and aggregate growth, the blunt instruments of the economy.
But the real power of integration shines when they use the microdata to assess distributional effects.
Absolutely. For example, if the government is considering a new tax policy or a massive infrastructure spending bill, macro data tells them the overall impact on national GDP, the efficiency measure.
But the microdata.
The microdata, however, tells them which specific geographic regions, which sectors, or which income groups will be most severely impacted or will benefit the most.
This distributional analysis is vital for moving policy from just simple economic efficiency to economic equity.
If the macro data suggests a tax cut is beneficial, but the microdata shows that 95% of the benefit goes to the top 1% of earners, the policy conversation shifts entirely. This integration allows policymakers to tailor relief programs or investment geographically, ensuring maximum impact where it's needed most.
And for businesses, the use case is equally dual-layered, distinguishing between long-term strategy and short-term execution.
They use macro forecasts for strategic planning. A CEO looking 5 to 10 years out to determine whether to enter a new country, build a massive new production facility, or expand capacity.
They need a long-term, stable view of inflation, interest rates, and overall market size.
But they rely almost exclusively on microdata for operational decisions. This is the day-to-day stuff.
Optimizing supply chains.
Managing inventory levels or hiring and marketing in specific geographic markets. If a macro forecast suggests mild national retail growth, but the microdata for a specific metropolitan area shows massive population growth and high disposable income among specific targeted demographics.
A regional manager knows exactly where to allocate additional marketing spend and staffing resources.
The integrated forecast prevents the business from treating the national average as its actual target. It turns an abstract economic prediction into tangible, segmented action points tied to specific product lines or territories.
To conclude our deep dive, let's outline the crucial best practices for forecasters who are mastering this synergy of scale.
Right.
If you are a learner stepping into this field, these are, well, the commandments.
The first rule is simple, but so often violated. Start with clear economic questions. You must define the specific problem you are trying to solve, whether it's predicting the impact of rising student debt or forecasting copper demand in the next 3 years, before you dive into the sea of available data.
Because if you start with the data,
you risk finding spurious correlations that answer a question nobody even asked.
Second, always use theory to guide integration. We mentioned this earlier, but it is the foundational principle of sound forecasting.
It bears repeating.
Data should not dictate the model without a sound economic rationale. If your microdata suggests a completely counterintuitive macro outcome, for instance, that a massive corporate tax cut will immediately reduce investment.
Economic theory should force you to question the data quality or the sampling bias, not simply accept a statistically derived but economically nonsensical result.
Third, and perhaps the best defense against that risk of overfitting we discussed, validate forecasts out of sample.
Best practice mandates rigorously testing models on data they haven't seen during the training phase.
So if the model works brilliantly on historical data, but falls apart when predicting the last 6 months, which you held back from the training set,
it's overfit, and you must simplify the model structure. No exceptions.
Fourth, savvy forecasters combine models where appropriate.
Successful forecasting teams don't rely on a single massive methodology. They often utilize multiple structures, running a top-down forecast, a bottom-up forecast, and a mixed data model simultaneously, and then they average or weigh their results.
Combining methodologies helps smooth out the idiosyncratic errors inherent in any single approach.
And leads to significantly more reliable final forecasts.
And finally, because we are dealing with complex, noisy, and frequently revised data, forecasters must communicate uncertainty clearly.
A good forecast is never a single definitive number. It is a range of probabilities, a cone of uncertainty, accompanied by a transparent explanation of the risks, the inherent limitations, and the specific potential biases built into both the macro and the micro components.
Acknowledging that risk is a sign of predictive confidence, not weakness.
Absolutely.
What an incredible journey. We've moved from that panoramic forest view to the nuanced health of the individual trees and then back again. We've really seen that integrated forecasting is the evolution of economics.
It is.
It moves beyond simply tracking the economy's aggregate vital signs, that macro what, to truly understanding the complex behaviors and distributional decisions, that micro why, that drive them.
It's the critical shift from diagnosing the symptom to understanding the full pathology of the disease. The forecasters using both macro and micro data isn't just predicting that the ship will slow down,
They're telling you which specific engine in which sector has failed.
and which specific localized currents are pushing against the hull. That depth of understanding changes everything.
So, here's our final thought for you to chew on as you continue your learning. Since forecasters must constantly balance that critical trade-off between detail versus reliability, the key high-stakes challenge for the future isn't just collecting more data. It's mastering the computational complexity and managing that persistent risk of overfitting as more real-time, high-frequency, micro-data think, moment-to-moment transaction streams becomes instantly available.
The question for the next generation of economic modelers isn't if they can integrate more data, but rather, how much detail is truly helpful, and at what point does that overwhelming influx of high-frequency micro-detail cross the line and become simple, counterproductive noise?
That boundary between information and noise is where the next breakthrough in economic modeling will be forged.
Welcome back to the Deep Dive. Today, we're tackling something that is, it's really the foundational engine of modern economic thought, microeconomic analysis. Okay, let's unpack this. The source material you gave us for this deep dive is just phenomenal. It's not just a definition of microeconomics, is it? It's like an operational manual for how modern economists actually work.
That's a great way to put it.
It takes you from these, abstract ideas about choice all the way down to the really sophisticated math they use to filter out all the noise in the real world.
That's absolutely right. And our mission today, I think, is really critical for you, for the learner. We are going to take that theoretical framework, all those conceptual models of how people behave, and we're going to connect them really rigorously to the empirical method.
The tools.
The tools, exactly. The econometric tools that people actually use today. The goal is to demystify it all. How does an economist go from this big idea, like people maximize utility, to a hard number that can inform policy on, say, minimum wage?
Exactly. It's like we're decoding the blueprint. And our sources, they lay out this incredibly clear roadmap. They're very focused on the technical challenges, the real hurdles. So we're going to cover what microanalysis is, why we even do it, and maybe most importantly, how the toolkit, econometrics, big data lets people overcome these huge intellectual problems.
Yeah, things like endogeneity, sample selection, all the stuff that keeps economists up at night.
Right. We're moving way beyond those simple supply and demand graphs from your first-year textbook. This deep dive is about the intellectual machinery you need to actually test those relationships in a world where, well, everything's moving at once.
And where every single person, every single firm is unique. I think the core tension we're going to explore today is that constant, really rigorous battle to separate true causality from just mere correlation.
Okay, so let's start by establishing the terrain. When we say microeconomics, it's easy to confuse it with, just economics in general. But its scope is actually very, very precise.
It is. We're not talking about things like national debt or GDP or inflation rates. Not at all.
So what are we talking about?
The core definition, really, is that microeconomic analysis studies the behavior and the decisions of individual economic units. It is fundamentally disaggregated. It's analysis at the most granular level you can get.
And defining those units seems pretty important. Who exactly are we talking about when we say individual economic units? Is it just people?
Well, it starts with people. We're primarily looking at about 4 specific agents or maybe arenas. So first, yes, the individual, making choices about what to buy, whether to save, how much to work.
Should I take this job or that one? Things like that.
Exactly. Then second, you have the household, which isn't just a collection of individuals. It often acts as a single unit, making these big decisions about, buying a house or saving for education.
Right, allocating resources among the family.
Precisely. And the analysis, of course, doesn't stop there on the consumer side. It has to include the production side, too.
So firms.
Correct. The third unit is the firm. The analysis here is tracking how they decide what to produce, how to price their goods, whether to invest in new technology or hire more people, all of those optimization problems.
And the fourth.
The fourth is specific markets. So this is the arena where all these other agents interact. We're not talking about the market in some abstract sense. We're talking about the market for rental apartments in Chicago, or the market for pediatric nurses, or the market for coffee beans. Very specific.
Okay, so it doesn't matter if it's a single person making a $10 decision or a huge corporation making a $1 billion one. The source material really hammers home this one central theme that unites all of it: constraint.
Absolutely. This is the bedrock. You could say it's the single defining characteristic of the whole field. The focus is always, always on how choices are made under constraints.
Because you can't have it all.
You can't. Resources, whether it's your time, your income, a company's budget, they are all scarce. And because of that scarcity, every single decision involves a trade-off.
So if there were no scarcity, if resources were just infinite,
Well, then there'd be no need for choice, would there? No trade-offs. And frankly, no need for microeconomics. The entire field gets its purpose from that fundamental problem. The fact that a family has to choose between a vacation and a new car, or a firm has to choose between R&D and marketing. That scarcity forces them to optimize.
and that optimization, that's what we're studying.
That's the behavior we're trying to model and predict. So yeah, we're really studying optimization strategies in the face of this inevitable scarcity.
That gives the field a really clear intellectual boundary. So given that, what are the actual objectives? What is a microeconomist trying to achieve?
Well, the objectives flow, very naturally from that foundational idea of constrained choice. The analysis really has three primary goals.
And the first one seems like the most obvious one. It's about understanding how these agents allocate those scarce resources.
That's right. Allocation is just the distribution mechanism. If a household has $1,000 of disposable income this month, how does it get allocated across groceries and rent and entertainment and savings?
Or a company's investment budget.
Exactly. If a firm has a limited capital budget, how does it decide between opening a new factory, launching a marketing campaign, or training its workforce? We're building models that try to predict that distribution.
Okay, and the second goal, this seems to be where the behavioral science part really comes in. It's about understanding how agents respond to incentives.
Yes, this is the crucial link to policy. Incentives are basically the levers that outside forces, usually governments, can pull to try and change behavior.
So a classic example would be a tax credit for buying an electric car.
A perfect example. The tax credit is the incentive. A microeconomic analysis would then try to measure the behavioral change that results. How many more people bought electric cars than would have otherwise? And did it affect their other behaviors, like how much they drive?
But it's not just about policy, is it? The analysis has to look at, more organic shifts in the world.
It does, and that connects directly to the third objective, which is understanding how agents react to changes in these big external factors, things often outside their control, like changes in prices, income, and policies.
So if the price of gas suddenly doubles.
Exactly. How does that spike in the price of fuel filter down? How does it affect a trucking company's logistics? And how does it change a commuter's decision about whether to drive, take the train, or work from home? We are trying to quantify the elasticity of that response.
So to put it all together, if, say, the average rent in a city jumps by 20%, a microanalysis doesn't just say, rent is more expensive. It tries to put numbers on it.
Right. It tries to quantify how many people are forced to move out, how many potential newcomers decide not to move in, and then what are the knock-on effects.
Like, does that change affect demand for local restaurants or public transit ridership?
That level of detail is precisely why the outcome has to be at that highly disaggregated individual or firm level. You have to understand the micromechanisms. If you don't get the individual pieces right, the big aggregate picture just won't make any sense.
Okay, that focus on the constrained individual decision, that brings us right into the core intellectual pillars. This is where the models get built, right? Setting the stage for all the empirical testing we just talked about.
Yes, exactly. Microeconomic analysis, it's built on a really strong theoretical foundation. We don't just jump into a pile of data and see what we find. We always start with a conceptual model, a theory, that gives us a roadmap for how we expect rational economic agents to behave.
So the theory is the structured hypothesis. These are those classic, sometimes very idealized models that we hear about.
The canonical models, yes. They're almost always models of optimization. For individuals and households, the main one is utility maximization.
The idea that people are always choosing the thing that gives them the most satisfaction or happiness?
Essentially, yes. The idea is that agents choose the option from the set of things they can actually afford, their budget constraint, that provides them with the highest level of personal satisfaction, or what we call utility.
Now, I have to stop you there because this is where a lot of people, especially from fields like psychology, push back. This idea of utility maximization, of people as these perfectly rational calculating machines. It's been pretty heavily challenged by behavioral economics,
It has.
which shows that people are, full of biases. They're affected by how choices are framed. They often make choices that are objectively irrational. So how does microanalysis square that clean theory with the messy reality of human beings?
That's a really fundamental and, I think, a very necessary challenge to the field. And the defense of the model is really twofold. First, the theory gives us a quantifiable starting point, a necessary one. If we didn't start with an assumption of rationality and optimization, it would be almost impossible to generate structured, testable predictions. We're creating a benchmark.
A benchmark of optimal behavior.
Exactly. And second, modern microanalysis doesn't just ignore irrationality, not at all. It uses that classical theory as the baseline, and then it uses the empirical methods we're talking about to actually quantify the deviation from that optimization.
Ah, that's a fascinating pivot. So the theory isn't meant to be a perfect picture of reality. It's the framework we use to measure reality's imperfections against.
Precisely. And for firms, the model that's analogous to utility maximization is profit maximization. The theory says that a firm will choose its production level, its mix of inputs, its pricing strategy to maximize its bottom line, all subject to its technology and its costs.
And that provides the testable prediction.
It provides the framework, yeah. If this cost goes up, then that behavior should follow. And microeconomic analysis then takes that, goes to the real-world data, and its job is to test these theories, and just as importantly, to quantify the size of those relationships.
So it's not just about confirming, yes, the theory is right. It's about parameterizing it. We need to know the number. What is the precise numerical value of the change in hiring if the minimum wage increases by $1?
Precisely. And it's econometrics, the application of these statistical methods to economic data, that provides that essential, really rigorous bridge between the clean conceptual theory and the messy, noisy, observed data we actually have.
Okay, now we have to talk about the concept that is, I think, the absolute linchpin for any kind of sound economic interpretation, and that is ceteris paribus.
Literally, all other things being equal.
Right. And in a science like physics or chemistry, you can actually do this. You can run an experiment in a controlled lab where you genuinely hold everything else constant. But in a social science like economics, achieving this is the central methodological battle.
It's not just a footnote in a textbook. Ceteris paribus is the absolute methodological demand for any behavioral interpretation to be meaningful. The world is just too dynamic. Incomes, prices, policies, people's tastes, they're all changing all at the same time.
So if you see that a company's profits went up last year,
how do you know why? Was it their new marketing campaign? Or was it because their main competitor went out of business? Or was it just because the overall economy was booming and everyone's sales were up?
if you change three things at once, you can't credit the outcome to any single one of them. The data is just muddled.
And that's why the core mission of regression analysis, which is the main tool we'll get to, is to mathematically replicate that ceteris paribus condition. The coefficients that come out of a regression are specifically designed to measure the partial effects of the explanatory variables.
That word partial is doing a lot of heavy lifting there.
A huge amount. It means we are trying to quantify the impact of just one variable, let's say one more year of on-the-job experience, while statistically isolating and holding constant every other relevant factor we can think of that also influences a person's wage.
Like their level of formal education, their industry, their age.
All of it. We hold all of that constant statistically. The analogy I always like is from medicine. If you're testing a new drug, you have to have a control group that gets a placebo. You need to make sure the only systematic difference between the two groups is the drug itself. That isolation is what allows you to say the drug caused the improvement. It's the exact same logic. We just use statistical control instead of a physical lab. And if we fail to enforce ceteris paribus, what we get is just a simple correlation. And the resulting estimate is what we call biased, which means any policy based on it could be useless or even harmful.
This inherent complexity, it leads right into the next core pillar, which I think is one of the great intellectual strengths of microanalysis, and that's the focus on individual heterogeneity. We just have to accept the fact that the units we're studying, people, firms, they're all fundamentally different from one another.
Heterogeneity is simply the reality of the economic world. Individuals are different in so many ways. Their preferences, how much risk they're willing to take, their skills, their innate abilities, their access to technology or information. And firms are just as different. Management quality, brand recognition, production efficiency.
So in macroeconomics, you might get away with talking about the consumer as this single average entity, But micro can't do that.
It can't afford that simplification. Microeconomic analysis, because it uses individual-level data, can explicitly account for this heterogeneity. We can model it and control for these differences.
So, for instance, if you're studying how people respond to a higher wage,
You can estimate how that response differs between, say, a single parent who has huge demands on their time versus a young single professional who might value an extra hour of leisure very differently.
and that ability to drill down into those different responses is what makes the analysis so powerful for actually tailoring policy, right?
Precisely. You know, if a government brings in a new policy, like a carbon tax, to try and change behavior, a good microanalysis doesn't just give you the average reduction in fuel consumption. It tells you who responded. Do people in rural areas with long commutes who have very few alternatives respond less than people in cities with great public transit?
And once you know that,
Yeah.
you can design better policy, maybe with rebates for those rural residents.
Exactly. You can design it with compensatory mechanisms. And the danger of ignoring this variation is huge.
Why is it so dangerous?
Because if you only look at the average effect, you might conclude a policy was a modest success. But you could be completely missing the fact that it worked great for half the population and was actually harmful for the other half. The average number would be a terrible guide to what's really happening. The strength of empirical micro is its commitment to modeling these differences, not just averaging them away.
Okay, so we've set this incredibly demanding goal. Quantify constrained choice, make sure ceteris paribus holds, and account for everyone being different. Now, let's get into the machinery, the actual tools that make this possible. We're moving from the idea of quantifying to the nuts and bolts of how it's done.
Right. And the first thing to understand is that modern microeconomics is it's intensely empirical. It's defined by it. I mean, since the late 20th century, the field has gone through this huge revolution driven by two things: the explosion in the availability of data on individuals and the computing power to actually analyze it.
So this requires massive inputs. We're not talking about small surveys anymore. We're talking about, tracking millions of people through their store loyalty cards, or using decades of government administrative records from the IRS or the census.
Absolutely. The field relies on large data sets and sophisticated econometric techniques. You need both. Without both, the challenges we've been talking about, like causality and heterogeneity, would just be insurmountable.
And econometrics, just to be clear, is that statistical link between the theory and the data.
It's the bridge. That's its job. It's what allows us to go from a sort of abstract idea like education improves wages to a very specific policy-relevant finding like one additional year of college education increases wages by 8.5% after controlling for experience, gender, and innate ability.
And to get that number, to achieve that level of control, the sources are crystal clear. Regression analysis is the primary empirical tool. It's the absolute workhorse.
It's fundamental. And the reason it's fundamental is because regression is the mathematical engine that enforces the ceteris paribus condition. The most common type, which is called ordinary least squares, or OLS, it essentially finds the line of best fit through a cloud of data points.
But the real power isn't just in drawing one line between two variables. It's that it can do this while juggling many variables at once.
That's the magic of it. It's multiple regression. The coefficient you get on your main variable of interest is mathematically calculated to represent the change in the outcome for a one-unit change in that variable, assuming all the other variables in your model are held constant. That is the statistical isolation right there.
Let's go back to that classic example. The effect of education on wages. If you just plot years of schooling against earnings, you get a positive line. A simple correlation.
You do. But that correlation is almost certainly biased upwards. It's polluted. We know that people who get more education are often, on average, more motivated or have higher innate ability or come from backgrounds with more resources. And all of those things also independently raise wages.
So how does the regression untangle the pure effect of just the schooling?
By adding control variables into the model, you add in a variable for years of experience, for age, maybe a set of variables for which industry they work in, and if you have the data, maybe even a proxy for ability, like an old standardized test score. The regression then statistically peels away the influence of all those other factors.
And what you're left with, hopefully, is the clean, independent, partial effect of just that one extra year of school on wages.
That's the goal. Without regression's ability to do that, to enforce ceteris paribus, any kind of causal inference in a non-experimental setting like this would be basically impossible.
And to run these powerful regressions, the structure of the data itself is just. It's paramount.
Yeah.
The kind of data you have, really dictates the questions you can even try to answer.
It dictates everything, and there are two main structures that are essential in microeconomics. The first and simplest is cross-sectional data.
It's a snapshot.
Exactly. You're observing a group of individuals or firms at one single point in time. It gives you a great picture of the variation across the units at that moment, how someone in California is different from someone in Ohio, but it tells you nothing about how the person in Ohio changed from last year to this year.
And it has a big weakness, which is those unobserved characteristics we talked about. Things like innate talent or drive.
It struggles mightily with that, because if those unobserved traits are correlated with your variable of interest, like education, then you have an omitted variable problem and your estimates are biased.
Okay, here's where it gets really interesting, because the second structure, panel data, is often called the gold standard because it's specifically designed to solve that exact problem.
Panel data, or what's sometimes called longitudinal data, is where you observe the exact same units, the same people, the same firms over multiple points in time. And that one simple difference, tracking the same unit over time, gives you this enormous methodological power.
Okay, but I'm still trying to get my head around how that solves the problem of unobserved talent. I mean, if a person's talent is unobservable this year, it's still unobservable next year.
But this is the genius of the technique you apply to panel data, which is often called a fixed effects model. The key assumption you make is that those unobserved traits like talent or family background are fixed for that person. They're constant over time.
Right.
So by looking only at the change in that person's outcome, like the change in their wage from one year to the next, and relating it only to the change in an explanatory variable like they got one more year of experience, those fixed unobserved things mathematically drop out of the equation?
Oh, I see. So the individual becomes their own control group. You're not comparing a talented person to a less talented person anymore.
You're comparing the talented person in year one to themselves in year two after something has changed. All that static, time-invariant heterogeneity that plagues cross-sectional studies just gets wiped away. And this is incredibly powerful for policy evaluation.
Because if a new law comes into effect in 2024,
panel data lets you measure the behavior of the very same firms in 2023 before the policy and in 2024 after. That ability to look at within-unit change, not just between unit differences, gives you a much, much more credible path toward real causal inference.
okay, that transition from theory to the practical power of panel data, it brings us right to the real-world impact. Where do we see this technical rigor actually making a difference? And what are the brutal challenges that economists still have to face to deliver that credible result?
Well, the application is everything. I mean, micro-level evidence is really the engine room of modern evidence-based policymaking. It's used for both policy design and for impact evaluation.
Because policymakers need specific answers, not just, did the program work? But
Who did it work for? By how much? And maybe most importantly, through which mechanisms did the change happen?
the mechanism is everything. It's the difference between saying spending more money on schools is good and saying spending more money on hiring specialized reading tutors for first graders causes a measurable increase in long-term literacy rates.
That specificity is the entire policy payoff. And we can break down the applications into a few core fields. First, you have labor economics. This field is just completely dependent on microanalysis. It's all about wages, employment, why people choose to work or not. Think about the minimum wage debate. Researchers use huge micro data sets to test the causal effects of a wage hike on employment, not just for everyone, but specifically for, say, teenagers in the fast food industry. They're trying to nail down the elasticity of labor demand.
Okay, then there's consumer behavior. This is that classic household choice problem.
Yeah, this is all about demand analysis, spending patterns. These micro models are critical for governments to estimate things like price elasticities. For example, how sensitive is the demand for cigarettes to a tax increase? They use that number to forecast tax revenue and predict the public health benefit.
Then you have the other side of the coin, firm behavior.
This is about production, costs, pricing, and market competition. A huge area here is antitrust regulation. When two big companies want to merge, economists build micro models to predict the outcome. Will it lead to higher prices for consumers because of less competition? Or will it lead to lower prices because of new efficiencies? That evidence is what regulators use to approve or block the merger.
And finally, there's the really broad field of public economics.
which is the direct intersection of micro behavior and government policy. It uses all these tools to analyze the effects of taxes, of education programs, of healthcare reforms. For instance, what's the effect of a change in the top marginal income tax rate on the number of hours that high earners choose to work? The stakes are huge, so the evidence has to be at that micro level.
And as we've hit on again and again, none of this policy analysis is worth anything if the relationship you find isn't causal. The entire game is about identifying causal relationships. Correlation is a starting point, but causality is what you can act on.
That distinction is the intellectual core of the field. You know, the classic example. Ice cream sales and shark attacks both go up in the summer. That's a correlation. Causality is understanding that the summer heat is the confounding factor causing both.
But in economics, you can't usually run a perfect, clean experiment. You can't randomly assign half the country to get a tax cut and the other half not to.
Exactly. So economists have to be incredibly careful when they use this real-world, non-experimental data. And the intellectual rigor for claiming you found a causal link requires really three things. First, careful model specification. The math has to accurately reflect the economic theory of how people behave.
So if the theory says a relationship is a curve, you can't just model it with a straight line.
You'll get the wrong answer. Second, you have to robustly control for confounding factors. This is the ceteris paribus battle all over again. And third, there has to be strong economic reasoning. You need a plausible story, a mechanism for why X should cause Y in the first place, not just a statistical fluke.
And policy is just totally dependent on getting this right.
Completely. A government can waste billions on a program that's based on a simple correlation. Credible causal inference is what ensures that you're spending public money effectively. And this brings us right to the four big monsters that econometricians spend their careers trying to slay.
Okay, these methodological challenges, they're not just small problems. The sources make them out to be existential threats to the whole project.
They really are, and overcoming them is what has pushed the field to develop these incredibly advanced methods. The first and most common is omitted variables bias. OVB.
This is when you leave something important out of your model.
Exactly. You leave out a variable that influences both your cause and your effect. And because it's missing, its effect gets wrongly soaked up by one of the variables you did include, which biases your result.
Let's use an example. Say you're studying the effect of hospital spending on patient health. You find that hospitals that spend more have better outcomes.
But what if the hospitals that can afford to spend more are also located in wealthier areas where the patients are, on average, healthier to begin with? If you omit the initial patient health from your model, you're going to give way too much credit to the hospital spending.
So you mistakenly attribute the effect to the wrong thing.
You do. The solution is either to find data on that omitted variable and include it, or, as we said, use panel data with fixed effects to control for all those constant, unobserved hospital characteristics.
Okay, challenge number 2. Measurement error. This sounds simpler, just bad data.
It is, in a way. It's the reality that in surveys, people don't perfectly remember their income or how many hours they worked. This noise, this measurement error causes problems. If you mismeasure your outcome variable, it mostly just makes your estimates less precise.
But if you mismeasure the explanatory variable, the thing you think is the cause, it's worse.
Right. It's much worse. If you have measurement error in your education variable when you're estimating its effect on wages, the coefficient you get will be biased, almost always towards 0. It's called attenuation bias. The true effect gets diluted by the noise in the data.
Okay, third hurdle, sample selection issues. This is about who ends up in your data set in the first place.
Right. This happens when the group of people you're studying is non-random, and the reason they're in your sample is related to the outcome you're studying. The classic example is estimating the return to education for women.
Because you only observe the wages of women who choose to be in the labor force.
Exactly. The sample is selected. Women who choose not to work might have very different potential earnings than those who do. If you just run a regression on the workers, you're not getting an estimate for all women, just for the selected group. You'd likely overestimate the average potential wage.
So how do you fix that?
There are advanced methods, like the Heckman selection model, that essentially try to model the selection process itself and then use that information to correct the bias in the main analysis.
Okay, and that brings us to the final, biggest beast, endogeneity.
This is the toughest one. It's when your cause and effect are actually a two-way street. They influence each other simultaneously.
Like health and income.
The perfect example. Does being poor cause bad health? Yes. Does having bad health make it hard to work and cause you to be poor? Also, yes, it's a feedback loop.
So if you just run a regression of health on income, the coefficient is a complete mess. It's capturing both directions of causality at once.
It's totally contaminated, so you need a way to surgically cut that feedback loop. And the main advanced tool for this is called instrumental variables, or IV.
And the goal of an instrument
Is to find some third variable, let's call it Z, that is strongly correlated with your problematic variable X, like income, but, and this is the critical part, it only affects your outcome, Y, health, through its effect on X. It has no direct path to Y.
That sounds incredibly hard to find in the real world. You need something that randomly pushes some people's income up or down, but has no other conceivable effect on their health.
It requires a lot of creativity. A famous one in economics was using the quarter of the year a person was born in as an instrument for their years of schooling. Because of school entry age laws, people born late in the year get slightly less schooling on average. So your birth quarter affects your education, but it's hard to argue it has any direct effect on your future wages other than through that education channel.
Wow. So you use that little random nudge from birth timing to isolate a cleaner causal effect of education on wages.
That's the logic. It's this level of ingenuity and rigor that really defines modern empirical microeconomics. The commitment to finding these clever ways to get around these massive problems is what makes the field so powerful.
Okay, so we've gone from the big ideas all the way down into the most sophisticated econometric techniques. Let's zoom back out and place microeconomics in its broader context, especially relative to its sibling, macroeconomics.
The distinction really just boils down to one thing: the level of aggregation. As we've said, microeconomic analysis is all about the individual units, the consumer, the firm. It's trying to explain behavior at that really disaggregated, granular level.
And macroeconomic analysis is about the totals. It's looking at the big aggregate outcomes: GDP, national unemployment, inflation, the economy as a whole.
Right, but, and this is so important, these are not two totally separate fields. They are deeply, intimately related through what we call micro foundations.
Meaning that the big macro trends are just the sum of all the little micro decisions.
That's it, exactly. Modern macroeconomics absolutely recognizes this. The total national savings rate is nothing more than the sum of every single household's decision about how much to save. The overall unemployment rate is the result of millions of individual firms' decisions about whether to hire or fire someone.
So if your macro model has a flawed idea about how individual firms make investment decisions, which is a micro question, then your big macro prediction about national investment is going to be wrong.
It will be fundamentally flawed. You have to get the behavior of the individual agents right. The health of the forest depends entirely on the mechanics of the individual trees.
So to kind of synthesize this whole deep dive, modern microeconomics is just defined by this incredible empirical rigor. Its whole identity is about tackling these really complex methodological problems head on.
That's the ultimate takeaway. It relies on large data sets, often panel data, and these sophisticated econometric techniques we've discussed. Regression, 4, fixed effects. The goal is always to move beyond just talking about theory and to rigorously test those theories to establish credible causality.
It really sounds like the field has shifted from being a branch of philosophy to something much more like data-driven engineering.
I think that's a fair description. Empirical microeconomics plays an absolutely central role in evidence-based economics today. When policymakers or businesses need to know how a price change or a new tax will actually affect behavior, they are looking for these highly detailed, methodologically sound microeconomic studies that have used these advanced tools to isolate a clean causal effect.
So what does this all mean? We started out by defining microeconomics as the study of constrained choice. And we've seen that the entire empirical side of the field is built on one single commitment: trying to mathematically enforce that condition of ceteris paribus.
And we saw how that commitment is brought to life through the power of tools like regression and panel data, which let economists climb that ladder from simple correlation up to the much harder, much more valuable prize of causal inference.
And we learned that getting there requires this immense technical skill to overcome these huge challenges: omitted variables, sample selection, and especially that monster, endogeneity, which requires these really elegant and creative solutions like instrumental variables. It's a technically hard field because the world is messy.
But that rigor is what delivers the insights. It gets you to the mechanism of choice.
And that leads us to a final provocative thought for you, the learner, to consider. We spend a lot of time emphasizing this concept of individual heterogeneity, the fact that everyone, every firm, is fundamentally different. So if our base microanalysis keeps showing us that the effect of policy is different for every different type of person, how much precision can we really expect when we try to predict the aggregate outcome of millions of those unique individual decisions?
In other words, if our most rigorous evidence is telling us that the optimal policy actually depends on the unique circumstances of the individual you're targeting, what are the real practical limits of designing a single national one-size-fits-all policy? It leaves you to think about how you can genuinely tailor policy when individual differences are so profound, but the entire machine of government is built to work with averages.
Imagine for a moment you're sitting in the executive suite of a huge multinational corporation.
Okay.
And you are facing a truly monumental decision. The question on the table is whether to commit, say, $10 billion with a B
Right.
to build this specialized, state-of-the-art manufacturing factory in a completely new geopolitical region.
So you're basically doubling your global capacity for a critical product line?
Exactly. And this isn't a decision about, next quarter's profit forecast.
No, not at all.
This determines whether your company even exists as a dominant global leader 5, 10, maybe even 20 years from now.
The stakes are just immense.
And the risk of failure it's existential.
And you've just hit the nail on the head. Decisions of that magnitude, the ones that commit these massive amounts of irreversible capital and that fundamentally shape the competitive viability of a massive corporation, well, they just can't be left to intuition.
Or what you did last time.
Exactly. Or historical precedent, or some simple return on investment calculation based on, overly optimistic projections. They demand a rigorous, systematic, and I think most importantly, an evidence-based strategic framework.
That systematic framework, that profound fusion of microeconomic theory and advanced business analytics, that is precisely what we are diving into today.
It's the operating system.
It's the operating system for modern corporate strategy. Yeah.
Today's deep dive is really custom-tailored for you, the learner, to quickly grasp this structural foundation.
Okay.
We've synthesized sources that focus specifically on the conceptual marriage of these two fields.
So how should we think about that marriage?
Well, think of it this way. Microeconomics provides the underlying theory of how markets are supposed to operate.
Right, the model.
The model. It tells you how rational actors, firms, customers should behave, and what the optimal outcome should be in a perfect world.
And analytics, where does that come in?
Analytics provides the data-driven proof.
Got it.
It's the empirical engine that takes those complex microeconomic theories, concepts like elasticity or marginal cost, and it quantifies them.
So it makes them real.
It makes them real. Precisely. It estimates their real-world impact using historical data, running complex simulations, and really transforming those theoretical models into practical, actionable forecasts.
So you're moving past, we think this is how the market works,
to, we know the market will react this way with 95% certainty.
Okay, let's unpack this then. Before we get into all the mechanics, we have to define the mission.
The North Star.
The North Star, exactly. When we talk about corporate strategy, what is the ultimate goal? It's tempting to define success as just maximizing short-term profit.
Of course. That's what the quarterly reports focus on.
But the sources we looked at repeatedly emphasize that the core objective for virtually every public company is maximizing long-term firm value.
Absolutely. The focus has to remain on the long term. And this is why, microeconomic analysis is the perfect foundational lens for this.
Why is that?
Because it inherently zooms in on decision-making at the firm level, the supply side, the demand side, the whole competitive environment. It provides that essential understanding of market fundamentals. So it's not just what should our price be today.
It's bigger than that.
It's what should our optimal capacity be in 2030. Based on anticipated cost efficiencies and long-term demand growth. It's a whole different level of questioning.
So if the goal is maximizing that long-term firm value, we really need to distinguish a truly strategic decision from something that's just merely tactical.
Or operational.
Or operational.
Right.
What elevates that $10 billion factory decision above, say, running a promotional discount next Thursday?
And the source material gives us 3 defining traits that really give these decisions their enormous strategic weight.
Okay, what's the first one?
The first characteristic is that they are inherently long-term.
Okay.
We are talking about setting the fundamental course for years, often a decade or even more. A major market entry, a multi-billion-dollar R&D commitment.
Or that massive capacity expansion.
That's right. It isn't paid off in one fiscal year. The consequences, both positive and negative, they ripple through the balance sheet for generations.
And the second trait.
They are high impact. The success or failure of these moves dramatically changes the company's trajectory. It literally alters the DNA of the business.
Like, you give us an example.
Sure. A successful strategic pivot, like when Apple transitioned from just computers to whole mobile ecosystems, that's the kind of high-impact move that fundamentally redefines the firm and the industry.
Right. And on the flip side.
Conversely, a poor decision like Blockbuster dismissing Netflix can ensure the company's eventual disappearance.
It's an extinction-level event for the company.
Precisely. And the third, which is perhaps the most paralyzing for executives, is that strategic decisions are often irreversible.
This brings us right back to my initial example.
Exactly. Once that capital is committed, once that $10 billion specialized factory is built, the concrete is poured, the specialized machinery is installed.
There's no undo button.
There is no undo button. It is extraordinarily difficult and costly to reverse that commitment. Most of the capital invested becomes what economists call a sunk cost.
It can't be recovered.
It cannot be recovered by simply selling the asset. You can't just put a factory like that on the open market.
And that concept of irreversibility, the sunk cost, that's crucial because it raises the risk of massive operational leverage.
Can you break that down?
Sure. If you build that factory, you have just locked in a gigantic, new, fixed cost base. So if demand then falters, you still owe the interest payments. You still pay for security. You still pay for maintenance.
Right.
That operational leverage works beautifully when times are good, but it becomes a millstone around your neck in a downturn.
Forcing you to operate near capacity simply to cover costs.
Even if you have to slash prices to do it.
Exactly. And this is why we distinguish strategy from tactics. A tactical price cut can be reversed tomorrow. A strategic factory commitment cannot.
So when we combine these three characteristics, long-term, high-impact, and irreversible, we can see how these decisions just fundamentally shape the firm.
They absolutely do. First, they dictate market positioning.
So where the company chooses to compete.
Exactly. Are they competing on price in high-volume emerging markets, or are they competing on proprietary technology and speed in the premium segment?
And that positioning determines everything that follows.
Everything. Second, they define the firm's sustainable competitive advantage.
The thing they do better than everyone else, it's hard to copy.
And that's the one. Is it a proprietary distribution network? Is it superior intellectual property?
Or could it be just the ability to produce goods at a 10% lower cost than any rival because of superior scale and efficiency?
Yes, exactly. And finally, and most tangibly, they govern resource allocation.
Because in a large organization, resources, capital, talent, management, time are always finite.
Always. So a strategic decision is fundamentally an allocation decision. It's saying, we are committing 80% of our R&D budget to this area and only 20% to that area.
You're betting on one future path over another.
You are. Let's make sure we ground this with some more practical examples beyond just the factory.
Good idea.
We are talking about the strategic core here. This could include setting the permanent long-term pricing structure for a core service, which dictates profitability for a decade.
Or deciding whether to undertake a massive technological transition.
Like what?
Like, say, shifting an entire fleet from fossil fuels to electric power.
That's a huge one. Or deciding on a complete vertical integration strategy. Do we acquire our critical suppliers and control the entire value chain?
Or do we rely on the open market?
Right. These are choices that involve massive capital commitment, competitive risk, and a high degree of irreversibility.
All of which require the kind of quantified, evidence-based approach that microeconomics combined with analytics provides. So, strategic decisions ultimately boil down to predicting and optimizing the relationship between future revenue potential and future cost reality.
And we have to start with revenue.
Which means we have to intimately understand demand. And this isn't just, pulling customers.
No, it's far more sophisticated. It's an analysis aimed at quantifying how customer behavior shifts based on 4 key variables.
The 4 drivers of the demand curve.
Exactly. First, and most obviously, are direct price changes. How sensitive is the market to our specific price?
Second, we look at income levels, which often tie back to macroeconomic factors.
Right, but they're critical for segmenting the market, understanding which customer group will trade down or trade up based on their disposable income.
Third, you have product attributes, which is really the core work of the firm.
Features, quality, service, convenience.
All of it. If we improve the quality rating of our software by 10 points, what is the measurable change in customer acquisition?
And fourth, and perhaps the most strategically challenging, are competitor actions.
So specifically, the pricing and availability of substitutes.
And this immediately leads us to the heart of microeconomic demand theory, elasticity.
Right. Strategic firms don't just know that demand exists, they have to quantify its sensitivity.
Which raises an important question. When companies talk about controlling their pricing power, are they fundamentally talking about manipulating elasticity?
They absolutely are. That's
Yeah.
what it is. Pricing power is the ability to raise your price without losing a disproportionate amount of customers.
And if you can do that,
If you can do that, you have succeeded in making your demand inelastic. That's the entire strategic goal of branding, of patenting, of creating switching costs.
and this is where analytics just shines.
How so?
Price elasticity is the precise quantification of how demand changes relative to price changes. For example, if we use machine learning models trained on millions of historical transactions,
Right.
we can empirically estimate that a 5% price hike will result in a 6.2% drop in sales volume.
So you get an elasticity coefficient of negative 1.24.
Exactly. And knowing that number is everything because it allows the firm to instantly calculate the net effect on total revenue.
Because if demand is elastic, so the coefficient is below negative 1, a price increase actually reduces total revenue.
Making it a terrible strategic choice.
But the truly complex strategic move comes when we look outward at the whole market ecosystem.
Which brings us to cross-elasticity.
This is fascinating stuff.
It really is, because cross-elasticity measures how the demand for your product A changes when the price of competitor product B or even a related complementary product changes.
So it's key for anticipating competitor moves and understanding platform strategy.
Yes. Give us an example that connects this to long-term strategy.
Okay, consider the massive tech ecosystems, Apple, Google, Microsoft.
Right.
They understand that while the demand for the iPhone itself might be relatively inelastic, the demand for third-party apps and services that run on the iPhone is highly complementary.
So the cross-elasticity between the device and the value of the apps is positive and extremely high.
Exactly. If Apple makes its device easier to use or adds features that boost the utility of those complementary goods, the demand for the entire platform becomes stronger and more inelastic.
So the core strategy is using high cross-elasticity in complementary goods to lock customers in.
Which thereby makes the core platform highly inelastic against competitive pressure. It's a beautiful example of microeconomic theory guiding multi-trillion-dollar strategic lock-in.
That really moves us seamlessly to the other side of the equation, understanding the cost engine.
Moving from potential revenue to cost reality.
Right. Strategic decisions hinge on a deep grasp of the cost structure. And for our audience, we assume they know the basic difference between fixed costs and variable costs.
Sure. But the strategic challenge is knowing what high levels of either mean for the business.
That's the appropriate level of analysis here. When we look at fixed costs, the rent, the core R&D, the $10 billion for that new factory, the strategic issue is managing that operational leverage. Industries with very high fixed costs, like semiconductors, airlines, or pharmaceuticals, are extremely sensitive to volume changes.
So they're forced to operate near capacity, regardless of immediate demand fluctuations.
Just to spread that immense fixed cost base thinly enough to survive.
And conversely, you have variable costs, raw materials, direct labor,
which fluctuate directly with output. A firm needs to monitor these obsessively because they directly determine the floor for pricing.
which brings us to the critical short-run metric, marginal costs.
The cost of producing one additional unit.
And this is where it gets really interesting for operational strategy.
Because in the short run, any price above marginal cost contributes positively to covering those fixed costs.
But strategically, marginal cost doesn't stay static, does it?
No, not at all. It often systematically declines due to two extremely important long-term strategic concepts that go beyond just basic cost definitions.
Okay, what's the first one?
The first is learning curves. For many complex products, as a firm gains cumulative experience in production, as the volume grows,
Right, people get better at their jobs.
people get faster, processes become optimized, supply chain inefficiencies get rooted out. This systematically drives down the marginal cost of production over time, and often it does so predictably.
So strategically, if a company can forecast its learning curve accurately,
Then they can engage in something called strategic pricing or experience curve pricing.
right? What's that?
They price their product based on the anticipated future marginal cost, not the current higher one.
So they're sacrificing short-term profit.
They are, but it accelerates volume, which drives costs down faster and gives them a decisive long-term cost advantage over rivals who price conservatively based only on their current costs.
And the second concept related to complex cost structures.
Economies of scope.
This is crucial for multi-product firms.
It is. Economies of scope exist when producing multiple different goods is cheaper than producing them separately.
I think we need an example here.
Okay, think of Amazon. They use their massive, specialized logistics network, a huge fixed cost, to deliver not just their own e-commerce goods, but also to provide cloud services with AWS and streaming media.
I see. So the core infrastructure cost is spread across vastly different product lines.
Exactly. Which leads to lower average total costs for all units, giving them a significant strategic advantage over any single product rivals.
So understanding cost behavior, therefore, directly informs these major irreversible production decisions.
It dictates optimal output levels, the volume where the firm's efficiency peaks and its average total costs are minimized.
And it drives the essential make-or-buy choices.
Right. Should we outsource that specialized component or produce it in-house? It's a microeconomic comparison.
Is our internal marginal cost, adjusted for quality and risk, lower than the external supplier cost?
Strategic firms are constantly modeling that trade-off, adjusting their supply chain dynamically based on cost fluctuations and their own internal capacity utilization.
And finally, it defines the necessary scale of operations.
Which brings us back to the factory. Whether to build that $10 billion factory is fundamentally an assessment of the long-run average cost curve.
The question is, will the sheer scale allow us to achieve efficiencies, economies of scale, that our rivals just cannot match?
And thereby ensure long-term competitive advantage.
Once we have quantified market demand through elasticity metrics, and we know our cost floor through marginal cost analysis, the next logical step is, well, it's setting prices.
Setting prices to maximize the distance between those 2 points, revenue and cost.
And pricing isn't just a marketing exercise, it's the central strategic lever.
And poor decisions here can absolutely destroy value, even if the product demand is strong.
How so?
Well, if you set the price wrong, you either leave money on the table, failing to capture that consumer surplus, or you unnecessarily alienate customers and shrink your market share.
So microeconomics systematically links pricing to the 3 strategic pillars we just established.
The first one we have to return to is demand elasticity.
Right. If your product is highly differentiated and inelastic, you possess genuine pricing power.
Allowing you to focus on high margins.
But if your product is basically a commodity and highly elastic, your focus has to shift entirely to high volume and relentless cost leadership.
The second is the cost structure. Pricing decisions must, in the long run, cover your total average cost.
But strategically, pricing must always be evaluated against marginal cost in the short run.
Right. A firm may temporarily price below total average cost, but never sustainably below marginal cost.
Otherwise, they're actively destroying wealth with every single sale.
And the third pillar is competitive intensity. The strategies of your rivals define the constraints.
So if your product is easily substituted, the competitor's price becomes the de facto ceiling.
Regardless of your internal costs or your own elasticity metrics.
Now, analytics steps in to enable pricing strategies that are far more sophisticated than just, calculating cost plus margin.
Much more sophisticated.
The most visible technique is probably dynamic pricing.
This is the real-time adjustment of price based on instantaneous demand, fluctuating inventory levels, and observed competitor prices.
So dynamic pricing is basically microeconomics in action, powered by big data.
It is. Think of it as exploiting localized, momentary changes in elasticity.
Well,
When a sudden rainstorm hits, the local elasticity for ride-sharing services becomes highly inelastic.
because the value of immediate transport just went way up.
Dramatically. So dynamic pricing algorithms quantify that temporary shift and adjust the price upward, maximizing revenue capture by exploiting that momentary willingness to pay.
They're maximizing consumer surplus capture.
The firm is taking more of the value the customer places on the service.
Yes. Then there is price discrimination.
This is charging different customers different prices for the exact same good based on their estimated willingness to pay.
Which is a sophisticated analytical exercise.
It is. It requires segmenting the market by geography, time of purchase versioning, like first class versus economy seats,
And accurately estimating the price sensitivity of each distinct group.
and successful price discrimination relies on two things. First, the inability of the customer to just resell the product to another segment.
Think second.
The analytical ability to correctly identify the optimal price for that specific segment's elasticity profile.
And finally, we have highly informed promotional pricing.
Right. Discounts aren't just random clearance events anymore. They are strategically timed and quantified.
So analytics determines the precise consumer responsiveness.
Knowing exactly how much sales volume is gained for a temporary 15% price drop and whether that gain outweighs the immediate revenue loss.
Which allows firms to maximize short-term cash flow or aggressively drive market share during specific periods.
And what's fascinating here is that every decision we just discussed, pricing, capacity, R&D, it all depends entirely on the competitive market structure a firm operates within.
If you drop your price, what is the rational response of your rival?
And the answer depends entirely on the sandbox you are playing in.
So we have those four traditional competitive landscapes. We have perfect competition.
Many small players, homogeneous products.
In that environment, strategy is simple but brutal.
Focus entirely on cost efficiency. Firms are what we call price takers. The strategy is to constantly innovate production to achieve the lowest possible marginal and average costs to maximize a tiny margin on massive volume.
And on the opposite extreme is the monopoly.
A single dominant player.
Here, the strategic focus shifts entirely to managing the price-quantity relationship along the overall market demand curve.
Right. The monopolist is constrained only by the overall market's willingness to pay and, of course, regulatory scrutiny.
So their strategy centers on maintaining barriers to entry and finding that profit-maximizing point where marginal revenue equals marginal cost.
Then there's monopolistic competition,
Which has many firms, but the products are differentiated.
So strategy here is all about differentiation branding, marketing, feature development to create a niche market where they can extract a small degree of temporary local monopoly power.
So they're trying to make their local demand curve inelastic through superior product features.
Exactly. But the most strategically complex environment, where the real money is often made or lost, is the oligopoly.
A few large players dominate the market.
And strategic interdependence is extremely high. Every move by firm A instantly impacts firm B, C, and D.
So in an oligopoly, the key insight is that unilateral action often leads to suboptimal outcomes for everyone.
Right. If one firm cuts prices, the rivals have to follow to prevent market share collapse, which leads to a price war that just destroys industry profitability.
So anticipating competitor responses is paramount.
And this intense strategic interdependence brings us directly to the conceptual tool used to model it, game theory.
Yes. Game theoretic thinking provides the mathematical framework for modeling these complex interactions.
Assuming competitors are rational and calculating, we move beyond simple elasticity curves and start thinking about payoffs.
For an audience that knows and follows this, let's illustrate how this applies to something fundamental, like a capacity expansion decision, using the structure of the prisoner's dilemma.
Excellent. The optimal scenario for two major oligopolistic rivals is usually tacit collusion, both maintaining high prices and low to moderate capacity.
So let's say the payoff matrix shows the best long-term outcome is for both rival A and rival B to not build massive new capacity, maintaining pricing stability.
Right. However, the short-term dominant strategy for both firms is to secretly build new capacity and flood the market. Why?
Because if rival A doesn't expand, but rival B does, rival A loses massive market share and profitability when rival B cuts prices using its new cost efficiencies.
So the highest individual gain comes from cheating on the tacit agreement.
Precisely. The Nash equilibrium, the stable, non-cooperative outcome, is often that both firms expand capacity.
Which leads to industry oversupply and lower overall profits for the entire sector.
Despite the fact that mutual restraint would have been the optimal collective strategy.
Exactly. Game theory forces strategists to calculate these payoffs and understand that their rivals are thinking several moves ahead. They also calculate market concentration, how power is distributed, often using tools like the Herfindahl-Hirschman Index, or HHI, to gauge regulatory risks or the likelihood of that tacit collusion holding firm.
So strategy is inherently future-oriented. It's constantly anticipating growth, identifying new market opportunities, and managing these massive long-horizon investments.
Which requires detailed microeconomic risk assessment that accounts for time and uncertainty.
Absolutely. Deciding whether to enter a new market, like launching operations across the Asia-Pacific region or abandoning an unprofitable one, that involves extremely high-level risk assessment.
And microeconomic analysis attempts to quantify the entire venture. We assess expected returns forecasting potential profit years into the future, often discounting it back to a net present value.
We also have to assess risk, the volatility and uncertainty associated with that new market's regulatory stability, customer acceptance, and demand volatility.
And of course, the competitive dynamics.
Not just what the market looks like today.
But precisely how existing players will react to a new intruder. Will they engage in a localized price war? Will they launch a preemptive advertising blitz?
You have to model those reactions using game theoretic thinking.
They do. And the fourth factor, which ties back directly to Section 1, is evaluating the massive barriers and costs.
This is where the irreversibility of strategy really hits home.
We have to analyze entry barriers, the high capital requirements, the stringent regulatory hurdles, the complexity of developing distribution channels,
And the existing brand loyalty held by the incumbents.
and we must assess the equally critical exit costs.
So what costs would the firm incur if the venture fails?
We're talking about contractual obligations, severance packages, and the inability to recoup sunk capital, that specialized $10 billion factory that can't be easily converted to another use.
Which is why analytics dramatically improves the forecasting accuracy.
It models hundreds of scenarios to determine not just the expected return, but the probability of needing to exit and the potential cost if that scenario materializes.
Given the sheer irreversibility and magnitude of these investments, strategists can't just rely on standard discounted cash flow analysis.
No, you can't. You need tools designed specifically to manage this high-stakes uncertainty.
So what does that look like?
This is where advanced methods like real options analysis become essential. When a strategic decision is irreversible and uncertain, the firm should often try to defer the decision until more information is available.
So real options analysis treats the investment opportunity not as an immediate commitment.
But as an option, the right but not the obligation to invest later.
So instead of immediately sinking $10 billion, the firm might sink $500 million now on, say, land acquisition, permitting, and pilot plant construction.
Like a sort of option premium.
Exactly. The firm has bought time and information.
So if market conditions rapidly improve, they exercise the option and build the full factory.
And if conditions worsen.
They abandon the $500 million, which is far less catastrophic than losing $10 billion. This analytical tool applies microeconomic principles of financial option valuation to capital investment decisions, specifically helping manage high risk and irreversibility.
Okay, next, let's look at the core of what the firm actually offers. Product and innovation strategy.
Right. What products should be offered and how much should be spent on improving them. This links microeconomics directly to the creation and capture of customer value.
The overarching goal is product differentiation.
Making the offering distinct and superior. If you're successful, differentiation shifts the demand curve out and makes it steeper, less elastic, allowing the firm to charge a premium over its marginal cost.
But you need data to know which differentiation actually matters to people.
You do. And the central concept the firm is trying to capture is consumer surplus.
Consumer surplus, as we briefly mentioned, is the economic gain a customer gets.
It's the difference between what the customer is maximally willing to pay for the product and what they actually pay.
So if a firm sells a product for $100, but analytical modeling shows the customer was willing to pay $150.
The firm failed to capture $50 of value.
So data-driven innovation becomes critical because analytics helps identify precisely which product features customers value most.
Allowing the firm to capture more of that surplus, we use methods like conjoint analysis or hedonic pricing models powered by analytics to decompose the product into its attributes.
So battery life, speed, design, brand reputation.
And we assign a quantifiable monetary value to each attribute from the customer's perspective. This ensures innovation spending is targeted for maximum return.
Why spend millions developing feature X that the data shows customers value at $5?
When they would willingly pay an extra $50 for a 20% improvement in feature Y, strategy has to follow the value curve identified by the data.
Finally, we turn to capacity and investment decisions. These capacity choices are often the largest capital investments a company makes.
And they're existential because they determine cost efficiency and the ability to meet demand, which ties back to long-term market share.
These are the high-stakes decisions driven by long-term demand forecasts.
They embody what you could call the Goldilocks problem. Capacity needs to be just right, a balance of scale and flexibility.
And we face two main strategic risks here. First, overcapacity.
If demand forecasts are overly optimistic or if a recession hits, the firm is locked into those unnecessarily higher fixed costs for years.
The factory is sitting half empty, and the firm's low capacity utilization means high average costs.
Making it vulnerable to leaner competitors.
And conversely, there's undercapacity.
Which means lost sales when demand exceeds what the firm can physically produce. The consequence is customer frustration, extended lead times.
And competitors swooping in to grab permanently damaged market share.
Strategically, this is often the worst mistake, as it actively cedes the market to your rivals.
The choice isn't just how much capacity, but also what kind of capacity.
That's right. Strategy forces a trade-off between flexible capacity and dedicated capacity.
So we face the cost efficiency versus flexibility trade-off.
Exactly. Does the firm invest in modular capacity, smaller, less efficient units that are easy to turn off, or quickly pivot to manufacturing a different product?
Which maximizes flexibility and minimizes the risk of stranded assets, but typically results in a higher variable cost per unit.
Or do they invest in highly specialized fixed capacity, that massive, dedicated $10 billion factory?
Which offers incredible economies of scale and the lowest possible average cost, but is rigid and almost impossible to adapt if the market fundamentally changes.
And to mitigate this inherent risk in multi-billion-dollar decisions, firms use rigorous forecasts and scenario analysis.
They don't just rely on a single prediction.
No. They use analytic models to test the robustness of their investment under multiple possible future states. A sustained downturn, a competitor collapse, rapid technological substitution, you name it.
So the goal is to choose the capacity strategy that performs acceptably well across the widest array of potential futures. We've established the theoretical concepts, elasticity, marginal cost, game theory, and we've seen how they guide these massive decisions like pricing and capacity. So what does this all mean when we talk about the synthesis?
How does microeconomic theory truly meet analytics in the strategic decision room?
Yeah.
Well, microeconomic theory provides the conceptual why and what of market behavior. It tells the strategist which questions to ask.
It's the foundational model.
It is. It's the conceptual framework for understanding the optimal relationship between price, cost, and output.
And business analytics transforms that theory into practical, actionable tools.
Right. And the sources highlight that analytics doesn't just estimate numbers, it fundamentally changes the nature of the decision itself through three key contributions.
Okay, sure.
The first, empirical estimation. It turns theory into hard numbers. Analytics uses regression models, time series analysis, and deep data mining to estimate elasticity coefficients, determine the precise shape of the marginal cost curve at different output levels, and quantify the risk profiles of various investment options.
And the second contribution is forecasting.
Analytics predicts future states of demand, cost inputs, or competitor movements with far greater precision than traditional methods.
So it allows strategists to make forward-looking rather than rear-view mirror decisions.
And third, scenario evaluation. This is testing those crucial what-if outcomes.
What if a competitor merges? What if raw material costs spike by 50% due to a geopolitical event?
Analytics allows the firm to run millions of simulations to see which strategic path is the most resilient.
So the result of the synthesis is pretty clear. The combination enables true evidence-based strategic decisions.
And the systematic quantification of trade-offs before the irreversible commitment is made.
But this marriage isn't always smooth, is it? Doesn't this approach run into trouble when the real world doesn't follow the tidy rules of microeconomic theory?
It absolutely does. The theoretical foundation of microeconomics relies heavily on the assumption of the rational actor.
That consumers and firms always make choices that maximize their utility or profit.
Right. But massive amounts of data generated by modern analytics often contradict this. And this brings us to the emerging tension with behavioral economics,
which is a microeconomics subdiscipline itself, but one that actively challenges that strict rationality assumption.
Precisely. Behavioral economics, fueled by observational analytics, shows that customer decisions are often driven by heuristics, biases, framing effects, cognitive limitations, not pure calculation.
And strategic analytics has to integrate this reality.
It does. For example, a purely rational microeconomic model might suggest one optimal price point.
But
But behavioral analytics might show that customers react disproportionately negatively to a price ending in 99 cents versus an even dollar, leading to a strategically superior, slightly different price point.
every major strategic decision involves inherent uncertainty about demand, costs, and competitor actions. So this raises an important question. If we acknowledge market irrationality, how do we choose when we can't know the future with certainty?
We have to shift heavily to risk-adjusted decision-making.
Okay.
We use analytics combined with our models to evaluate not just potential raw profit, but the risk-adjusted returns.
So, for example, two strategies might have the same expected profit of $1 billion.
But strategy A might have a small chance of huge failure and a small chance of huge success. High variance, high risk.
And strategy B might have a very reliable, narrow band of outcomes, low variance, low risk.
And a strategic firm, especially one managing stakeholder expectations and debt obligations, will often choose strategy B,
The slightly lower expected profit path.
if it is significantly more resilient to downside risk and provides higher certainty.
It's a strategic bias toward resilience.
It is. Furthermore, analytics provides the ideal scenario, but strategy has to exist within the real world. Decisions are always constrained by three very powerful non-economic factors.
First, regulations.
Legal, governmental, and increasingly international requirements limit what a firm can do.
So antitrust laws govern mergers and pricing power.
Environmental regulations govern where and how that $10 billion factory can be built and operated.
What's the second constraint?
Second, and critically and often underestimated, are organizational capabilities.
Does the company have the necessary talent, culture, and operational structure to execute the strategy?
Strategy must align with capacity. If the optimal strategy requires rapid, agile innovation, but the organizational structure is rigid and bureaucratic, the strategy will fail, regardless of what the microeconomic models predict.
It's the maxim that structure follows strategy.
And if the structure is lacking, the strategy must be limited.
And third, capital availability.
Can the firm afford the investment without compromising necessary reserves?
So even if the model predicts a 40% return on the new factory,
If the capital market is tight, and the firm cannot responsibly raise the necessary funds without taking on excessive leverage, the strategy is simply infeasible.
and this leads to the crucial caveat that the sources really emphasize.
That analytics informs decisions but does not replace necessary managerial judgment.
Right. The data points the way, but a human ultimately has to interpret the risk, factor in the non-quantifiable elements like organizational culture, and commit the capital.
And that interpretation process often centers on navigating strategic trade-offs.
Where firms have to choose between mutually exclusive goals.
Analytics helps evaluate these systematically, allowing managers to move beyond just intuition and weigh the costs of either path.
So the first and most enduring trade-off is price versus volume.
Do we lower our price to gain market share and high volume of growth strategy, or maintain a high price for smaller volume and higher per unit margins?
Which is more of a harvest or differentiation strategy.
And that decision is entirely dependent on the analytical quantification of elasticity. If elasticity is high, the volume strategy is viable. If it is low, the margin strategy wins.
The second is cost efficiency versus flexibility, which we touched on with capacity decisions.
Do we build that massive, hyper-optimized, rigid cost structure that gives us the lowest possible marginal cost?
Or do we maintain more costly operational flexibility so we can rapidly adapt our product lines or scale down quickly if a sudden recession hits?
It's a trade-off between maximizing efficiency in a known environment versus maximizing resilience in an uncertain one.
And finally, the classic strategic tension. Short-term profit versus long-term market share.
Should we make a decision that maximizes earnings this year, perhaps by slowing R&D or cutting marketing spend?
Or should we invest heavily in R&D or aggressive loss-leading pricing that sacrifices immediate earnings for sustained competitive advantage 5 years down the line?
And analytics provides the systematic framework for forecasting the eventual long-term payoff of that sacrifice.
Forcing the management team to quantify the value of future market dominance against immediate profitability. This has been an incredibly deep and crucial journey into how the largest players in the global economy actually make their most important decisions.
It has.
We've moved from the theoretical foundations, what is elasticity, why does marginal cost matter, to the practical, evidence-based applications.
Things like dynamic pricing, real options analysis, and the strategic evaluation of capacity trade-offs.
The value here, for you, the learner, is the ability to instantly recognize the underlying economic logic driving any major corporate announcement you read in the news.
That's right. You now see the factory expansion as a high fixed cost, irreversible strategic decision requiring risk-adjusted returns rather than just another press release.
So this framework provides an immediate shortcut to being deeply well-informed.
It's no longer a mystery. It's quantifiable analytical strategy, even when dealing with real-world constraints and, human irrationality.
We spent this deep dive focusing almost entirely on maximizing the traditional definition of long-term firm value.
Right, which historically prioritized financial returns and market share.
However, considering the rapid global rise of ESG, environmental, social, and governance factors in investment and public scrutiny, here is a final provocative thought for you to explore.
How might microeconomic models need to evolve to quantify the value derived from non-financial strategic decisions, such as a major commitment to reducing carbon emissions or improving global labor practices?
And what new analytical methodologies would be required to actually measure the positive return on that non-financial strategic investment?
And integrate it into the long-term HERF value calculation.
Something substantial to mull over next time you read the business section. Thank you for joining us for this deep dive into the microeconomic foundations of corporate strategic analytics.
We look forward to exploring the next topic with you.